Here, we'll explore the hydronic distribution systems used in data centers, focusing on designing, constructing, commissioning, and operating variable flow water systems. These systems are essential for cooling equipment like CRAH units, fan wall units, cooling distribution units, and StatePoint liquid cooling solutions. The module covers key plant topologies including CRAH and FW setups, two-loop CDU configurations, and advanced StatePoint SPLC designs. We'll also dive into critical controls such as pressure-independent control valves paired with differential pressure monitoring and variable speed drive controls to optimize system performance. Understanding these components is fundamental to ensuring efficient, reliable cooling in modern data centers. Here, we start with the role of the design consultant, who defines critical parameters like temperatures, diversity, topology, index circuits, valve ranges, and pump duty to establish a solid foundation. Then, the construction contractor takes that design intent and transforms it into practical implementation by installing cleanable pipework, accessible equipment, calibrated instruments, and properly tagged valves. The hydraulic outcome is then managed by operations and maintenance, who test and operate the system by protecting set points, monitoring the hydraulic signature, diagnosing any drift, and ensuring safe failure recovery. It's important to remember that without sensors verifying requirements or acceptance limits to close tests, and without retaining trend data, effective operation and maintenance would not be possible. Let's go over the non-negotiable hydronic rules that are essential for proper system design and operation. First, the thermal mandate emphasizes that we must calculate flow based on the useful thermal duty and the specified temperature difference, or delta T. We should never rely on legacy pipe sizes for flow calculations, as that can lead to inefficiencies or errors. Next is the index rule, which tells us to build pump head from a single, complete index circuit instead of adding up every parallel branch. This approach gives us a more accurate and manageable design. Moving on to the control boundary. It's critical to treat bypass flow as a controlled equipment protection state rather than normal distribution. This mindset helps prevent system imbalances and protects equipment. Lastly, the operational proof rule reminds us that pump speed alone doesn't prove capacity, and valve command alone doesn't guarantee flow. We must always pair these controls with actual flow, pressure differential, and temperature sensors to confirm the system is operating correctly. These rules ensure reliable, efficient, and safe hydronic system performance. Here, we're diving into the physics of flow in a thermal system, focusing on what happens when the temperature difference, or delta T, is low. The core formula shows that the mass flow rate equals the thermal power divided by the product of density, specific heat capacity, and the temperature difference. Simply put, the thermal duty depends on both the flow rate and the temperature difference. In the ideal state example, a 4 megawatt load with a 10 Kelvin delta T requires about 95.6 liters per second of flow. However, in a degraded state, where the delta T drops to 5 Kelvin, the flow needed doubles to 191.1 liters per second. This doubling of flow when delta T causes a fundamental shift in the system's operating point, impacting head, efficiency, and ultimately the plant's capacity. Understanding this relationship is crucial for optimizing performance under varying conditions. Here we have the anatomy of an index circuit, which breaks down the different components and their associated pressure losses. Starting with the pipe and fittings, we see a combined friction loss of 28 plus 12 kilopascals. Then, the Y strainer adds another 10 kilopascals, accounting for a clean state allowance. Moving on to the cooling coil, it introduces a significant 45 kilopascals due to equipment thermal transfer. At the PICV minimum, a pressure-independent control device, there is a required drop of 30 kilopascals. When we sum all these losses, the index total comes to 125 kilopascals. Adding a 10% design allowance brings the design head to 138 kilopascals. The golden rule here is crucial. If an engineer cannot name the index circuit and clearly show every pressure loss, then the pump duty is not ready for procurement. This ensures full understanding and accuracy before moving forward. Here we have some key concepts to understand about pump operation. First, the shutoff head is the maximum head the pump can produce when there is zero flow. At this point, the pressure is at its highest but no liquid is moving. Then we have the pump curve, which shows how the pump's head decreases as the flow increases. On the other side, the system curve represents the resistance the system applies, which increases exponentially mainly due to friction losses, proportional to flow squared. The operating point, or duty point, is where these two curves intersect. This is where the pump's capability matches the system's requirements. It's important to note that static head, which is fixed, contributes to the overall head, but doesn't change with flow. Understanding these relationships helps us predict how the pump will perform under different conditions. Here, we're looking at the affinity laws and how they relate to variable speed operation in pumps. The key takeaway is how changes in frequency or speed impact flow, head, and power. Flow scales linearly with speed, meaning if you reduce speed to 70%, flow drops to 70%. Head, which is the pressure the pump produces, scales with the square of speed, so dropping speed to 70% lowers head to about 49%. However, head is limited by the fixed static head of the system, so it won't drop below that point. Finally, power scales with the cube of speed. Reducing speed to 70% cuts power consumption significantly, down to roughly 34%, offering huge energy savings. It's important to note that these laws show ideal behavior. Real-world power savings can be tempered by motor and variable speed drive efficiencies. The system curve illustrates how head and flow interact in practice, and the control insight reminds us that dropping speed reduces absorbed power quickly, but only if the pump operates along the correct control curve without starving the circuit. This ensures efficient and stable operation while maximizing energy savings. This slide covers the PICV revolution and how it addresses legacy problems in HVAC systems. Traditionally, manual balancing was used, but this often led to hunting and overflow situations due to system pressure changes. The PICV, or ABQM valve, revolutionizes this by maintaining a strict, steady flow even when pressure fluctuates behind it. Key principles to note include starting the selection process based on flow rather than conventional KV or authority calculations. Also, the minimum available valve pressure drop is incorporated into the pump head index calculation. This approach effectively prevents overflow and significantly reduces the risk of low delta T syndrome, improving system efficiency and stability. Here we have the valve hierarchy, which is crucial for managing flow and pressure in HVAC systems. First, the PICV, or Pressure Independent Control Valve, is designed to modulate and limit terminal flow regardless of pressure changes. You'll typically find these in CRAH units, fan coil units, and cooling distribution unit branches. The key proof of their function is that a 100% command always results in the scheduled flow, even when the pressure differential is at its minimum. Next is the DPCV, or Differential Pressure Control Valve. Its main role is to maintain a steady differential pressure across a downstream zone. You'll usually see these installed in risers or shell and core zones. The proof here is that the zone's pressure differential stays consistent at set point, even accounting for diversity in the system. Lastly, we have manual balance valves, mostly found in legacy systems or at strict isolation points. Their function is to measure and set a fixed resistance, but they do not provide dynamic protection for neighboring circuits. So, while important in some setups, their limitations mean they're less versatile than the other valves in this hierarchy. Here we're looking at the concept of pressure zoning in multi-story data centers, which is critical for maintaining stable and efficient cooling. The system is divided into zones, from Zone 1 up to Zone 4, each representing different segments or floors of the data center. At the core of this setup are the terminal PICVs, or Pressure Independent Control Valves, which manage local flow control independently from the main riser. This independence is key to precise regulation on each branch. Then we have the main riser DPCV, standing for Differential Pressure Control Valve, which plays a vital role in protecting the entire floor or zone from sudden or massive static pressure changes. This ensures the system remains balanced and prevents damage or inefficiency due to pressure fluctuations. Finally, the phased fit-out rule reminds us that any future branches in the system must have proper isolation and flushing provisions in place. This means you should never simulate future loads by leaving bypasses open, as that practice disrupts the carefully established baseline performance and compromises system reliability. Overall, these measures keep the pressure zoning controlled and predictable across all levels of the data center. Here, we're looking at the closed-loop hydronic control workflow, which is all about sequential flow regulation and system balancing. It starts with the load demand, where a sensor detects room or coolant temperature requests that determine the terminal cooling flow. Then, the terminal flow is controlled by an electronic PICV valve, which regulates branch flow and confirms the commanded position. Next, the index proof comes from a remote differential pressure sensor that measures usable pressure across the active circuit. The pump command, managed by a variable speed drive, modulates pump speed within validated limits to meet this remote pressure requirement. This entire control loop ensures that the temperature request leads to precise valve positioning and flow rates, validated by pressure and pump speed measurements, allowing for alarms and recovery tests to maintain system reliability. This tight control and verification process is crucial for efficient and stable hydronic system operation. Here we're looking at the trim and respond differential pressure logic, which is crucial for optimizing pump operation. The key idea here is finding the true index that balances energy use and system demand. First, let's talk about the header DPT. This approach is incorrect because it measures total pump head, causing rigid overpressurization near terminal units. It doesn't adjust to varying conditions, which wastes energy. Instead, using a remote load DPT is the right method. This sensor accounts for variable pipe losses as flow changes, allowing the pump to save energy by adjusting pressure more efficiently. The logic here works like a seesaw: trim slowly and respond quickly. We start by reading the most open terminal valve. Then, the system trims by slowly decreasing differential pressure when all valves maintain their pressure margin. But if a valve starts to starve and opens fully, the system responds rapidly by increasing pressure to meet demand. This dynamic balance ensures efficient and reliable operation. On this slide, we're focusing on safe harbors and staging rules, which are essential for efficient pump operation. First, we have the best efficiency point, or BEP, which is the peak hydraulic efficiency for a pump. Operating close to the BEP ensures we get maximum performance and energy savings. Next, the preferred operating region, or POR, is the continuous operating band where the pump runs smoothly without stress. We aim to keep pumps running within this region to avoid wear and premature failure. Outside the POR, there's the allowable operating region, or AOR, which is intended only for transient or infrequent duty to prevent damage. When running pumps in parallel, the staging rule is critical. Two pumps merge their performance curves to handle higher flow, but it's crucial to keep the lead pump inside its stable region. Only start the lag pump before the lead saturates and leaves the AOR, and always match speeds before opening isolation valves to maintain system stability. This approach helps ensure safe, efficient, and reliable pump operation. Here we have the Topology decision engine, which helps us evaluate different system configurations based on several key criteria. First, looking at the primary flow, it can be variable, step primary, primary secondary, or legacy. Each of these impacts system efficiency and complexity differently. When it comes to efficiency, the highest levels are achieved with variable primary flow systems, while legacy setups tend to have moderate efficiency and often result in high energy waste. Complexity varies as well, with advanced and clear designs offering better control, whereas legacy systems can be inefficient and introduce low delta T issues. Regarding risk, variable primary flow systems pose low risk when properly controlled, but primary-secondary setups may face challenges like bypassing at part load or decoupler mixing, increasing risk. Based on this analysis, variable primary flow is recommended for most applications due to its balance of high efficiency and manageable complexity. Primary-secondary is acceptable, while legacy systems are not recommended because of inefficiency and higher risks. Here, we're looking at the concept of variable primary flow, or VPF, which is a key approach in optimizing chilled water systems. The primary VSD, or variable speed drive, pumps handle the entire facility's cold supply and main distribution, eliminating the need for secondary pumps. This setup achieves the highest efficiency because it simplifies the system and reduces energy consumption. However, it requires chillers that can operate with variable flow, which means they need VSD compressors to handle these changes effectively. To protect the chillers, the system includes a measured bypass control that ensures the minimum flow is maintained, preventing any potential damage. An important design consideration here is that the bypass valve is carefully sized and controlled based solely on the chiller's minimum flow requirements, rather than just an arbitrary percentage of the design flow. This precise control is critical for maintaining system reliability and efficiency. Here we have the primary-secondary system and the role of the decoupler, highlighted by this flowchart. The cold supply from the facility feeds into the primary supply header, which then connects to the secondary supply header through the common decoupler. The delta P sensor monitors the pressure difference between these two sides. When the primary flow is greater than the secondary by about 14.3 liters per second, we have a stable supply with any excess plant flow safely returning. If the primary and secondary flows are equal, that's the ideal perfect balance situation. However, the most critical condition to watch for is when the primary flow falls below the secondary flow, indicated here as negative 59.8 liters per second. This imbalance causes the warm return water to flow back into the cold supply, a dangerous scenario. The alarm logic is designed to flag this persistent negative decoupler balance combined with a rising mix supply temperature, which points to a staging fault rather than an issue with a terminal valve. Understanding these relationships ensures safe and efficient operation of the system. Here we have the concept of the CDU hydraulic firewall, which separates two crucial systems: the facility water system, or FWS, and the technology cooling system, known as TCS. The FWS operates at high pressure and turbulence, designed with a 10,000-degree temperature difference, with the main goal of providing heat rejection capacity while minimizing the pump head needed at the facility. On the other side, the TCS handles a much more delicate process, maintaining strict chemical limits and operating under a 15,000-degree temperature difference design. Its primary objective is to keep the server inlet temperature, flow, and pressure tightly controlled within the IT equipment's operational envelope. This separation ensures both systems can function efficiently without interference, protecting sensitive technology while optimizing overall cooling performance. Here we have a 600 kilowatt thermal energy load, and we're calculating the flow rates for two different systems. First, for the freshwater system, or FWS, we divide 600 kilowatts by the product of 4.186 and a temperature difference of 10 Kelvin. This gives us a flow rate of 14.33 liters per second, which is controlled by the facility terminal PICV. Next, for the thermal control system, or TCS, we use a temperature difference of 15 Kelvin. Dividing 600 kilowatts by 4.186 times 15 Kelvin results in a flow rate of 9.56 liters per second. This flow is managed by the internal CDU N+1 variable speed drive pumps. The key takeaway here is the boundary rule. The flow rates differ because the temperature differences in each loop are different. The CDU heat exchanger transfers energy, not equal volumetric flow, so the system's capacity is confirmed through heat balance and approach temperature rather than pump speed. Here we have an overview of the StatePoint liquid cooling system, or SPLC. At the heart of this setup is the return air plenum, which plays a crucial role in managing airflow. The SPLC distribution network is designed to provide controlled variable flow distribution, serving key components like fan walls, CRAH units, RDHX, or other liquid cooling interfaces. You'll notice the cold supply, marked in cyan, where the temperature is tightly controlled based on the ambient state to ensure optimal cooling performance. On the other side, the warm return, shown in crimson, maintains its temperature by preventing overflow and bypass leakage through precise control using PICVs. The core principle driving this system is an intelligent ambient logic that selects the production mode, while terminal demand and the pressure differential index control the distribution pump speed, ensuring efficient and responsive cooling operation. Here we have the SPLC operating modes, which are crucial for understanding how the system adapts to different ambient conditions. Mode 1, the economizer or sensible mode, works when ambient conditions can meet cold water targets without evaporation. This means the system can cool efficiently without using additional water. Moving to Mode 2, the adiabatic mode, here evaporative assistance is applied to the intake air to better control the water supply set point, providing enhanced cooling when needed. Finally, Mode 3 is the super-evaporative mode, where the system uses the microporous hydrophobic membrane directly to handle extreme ambient conditions. It's important to note the intake air, exhaust air, water flow, and membrane core all play key roles throughout these modes. A critical point to remember is the transition discipline. Fans and supply temperature set points must be ramped carefully, while the pump differential pressure control remains locked to avoid flow or temperature excursions. These mode changes impact production and must never compromise terminal flow independence. Here we focus on 4 key types of measurements essential for system monitoring and diagnostics. First, hydraulic measurements, which include flow meters and suction or discharge pressure, as well as remote differential pressure sensors. Placing bypass flow meters strategically helps us identify low delta-T waste points. Next, thermal measurements involve monitoring supply and return temperature pairs to calculate the heat balance accurately using the formula with density, specific heat, flow, and temperature difference. Moving to mechanical measurements, we track vibration, speed, bearing and seal temperatures, and detect leaks to ensure equipment reliability. Lastly, electrical measurements cover true kilowatt readings, voltage, and the status of power sources. It's important to note that when sensor data isn't available, sensorless fallback methods estimate hydraulic head from power consumption. But this approach cannot confirm if a branch is closed or if terminal starvation is occurring. Here we have 4 key response classes, from R1 to R4, each representing a different level of system resilience. Starting with R1, known as ride-through, this means there is no material loss of flow or differential pressure. The system uses dual or UPS control power with active-active pump trains to maintain continuous operation. Moving to R2, or hot standby, the system recovers to over 90% flow within seconds. Here, the pump is primed, with check valves coordinated and local automatic start mechanisms in place for quick recovery. R3, warm standby, covers a longer recovery time, tens of seconds, while staying within the thermal buffer. During this phase, the pump is stopped but the source remains available and sequence delays are managed. Lastly, R4, cold standby, involves manual or planned recovery with a service level agreement, serving more as a capacity recovery rather than maintaining thermal continuity. It's important to note the resilience warning. Even with redundant pumps, if components like the control panel, cooling unit, or PLC share the same failure point, redundancy is compromised. This highlights the need for true separation in critical system elements. On this slide, we're focusing on troubleshooting the signature of a system, starting with 3 common symptom root cause action scenarios. First, if you observe the valve fully open at 100%, but there's low flow and a low remote differential pressure, the root cause is usually insufficient pump head or a blocked path. The recommended action is to check strainers carefully and avoid the temptation to just increase the pump speed without investigation. Next, if the symptom is a low valve command alongside high flow and low temperature difference, it often points to a PICV setting fault or bypass leakage. In this case, performing a stroke test and closing any supervised bypasses will help address the issue. The third scenario involves high pump speed with normal flow, but rising differential pressure loss, which typically indicates fouling. Here, it's important to trend the strainer and coil differential pressure, then clean and update your baseline accordingly. Finally, an essential operating rule to remember: never attempt to troubleshoot a low delta-T alarm based solely on temperature readings. Always first determine if the cause is excess flow, bypass flow, or insufficient heat transfer before taking any corrective action. Here we have the key elements of the handover standard, starting with 1 tagged object and 1 drawing reference to ensure clarity and traceability. Next, there's 1 point name, which helps us identify specific measurement locations, followed by 1 calibrated result that guarantees accuracy. Importantly, the standard includes 1 approved baseline trend, providing a reliable benchmark for performance. The engineering conclusion here is crucial. Advanced hydronics focuses on maintaining effective heat transfer throughout every operating condition. It's not about having the highest pump head, but rather about proving that every load receives the required flow at the lowest stable head possible. This approach ensures efficiency and reliability in system operation. In this module, we focus on engineering the complete hydraulic outcome for hydronic distribution in data center MVAC systems. The key task of the system is to deliver the required mass flow at the design temperature difference while maintaining terminal control authority as valves modulate and load shifts. It's crucial to protect minimum equipment flow without turning bypass flow into a permanent load, and to ensure the system can recover from pump, sensor, controller, or power failures without losing effective cooling. As engineers, we must prove several aspects throughout the project lifecycle. During design, we verify the indexed pressure loss schedule, valve envelope, pump duty, and control sequence. In construction, attention to pipe cleanliness, straight runs, sensing ports, actuator access, and valve orientation is essential. Commissioning requires measurement of flow, remote differential pressure, temperature difference, pump speed, and staged failure responses. For operation and maintenance, establishing baselines and alarm logic is critical to differentiate between load changes and hydraulic degradation. Ultimately, success is defined by maintaining the minimum differential pressure that satisfies the indexed load at every credible operating condition, ensuring reliable and efficient cooling performance throughout the system's life. Here we see the essential roles and responsibilities in managing the hydronic distribution within a data center MVAC system. 3 distinct audiences, design consultant, construction contractor, and operations and maintenance, each own a critical link in the process. The design consultant defines all key parameters like temperatures, valve ranges, and acceptance criteria. Then, the construction contractor transforms that design intent into the physical system, ensuring all components are accessible and properly documented. Finally, operations and maintenance protect set points, monitor system behavior, and handle any issues safely. This chain from design to operation relies heavily on accurate measurement and testing, since a requirement without a sensor can't be verified, and tests without trends can't support operations. The handover standard ensures consistency by linking one tagged object to one drawing, one point name, and one approved baseline result. This integrated approach is crucial for reliable and efficient system performance. On this slide, we focus on important abbreviations and the technical foundations for hydronic cooling systems in data center MVAC applications. First, the key abbreviations. VSD stands for Variable Speed Drive, and PICV means Pressure Independent Control Valve, both critical components in fluid control. The hydronic logic here is based on a single, sole technical baseline, mainly derived from the Danfoss Hydronic Applications Guide. This guide covers PICVs, DPCVs, manual balancing, VSD control, and plant topologies, ensuring our approach is grounded in solid manufacturer-verified methodology. It's important to note that Danfoss ratings are only reproduced where officially published, and calculations shown are first principles examples, not hidden manufacturer selections, which means they're transparent and reliable. Equipment insights come from official sources like Vertiv and Nortec, but do not override this Danfoss baseline for pressure and flow control. Lastly, every significant claim or asset you see in this module is traceable to official sources or manufacturer URLs in the slide notes, providing full transparency and credibility. This slide sets the stage for understanding the technical rigor and source discipline that underpins our training. Here we have an overview of the hydronic distribution systems in a data center MVAC setup. This module covers one integrated system with 4 connected hydronic loops, each operating at different temperature levels but sharing the core principles of flow, pressure, control, and proof. You'll notice abbreviations like VSD, which stands for Variable Speed Drive, and PICV, or Pressure Independent Control Valve, both critical components in managing efficient system operation. The 4 key areas include the chiller plant, utilizing VPF with step primary and primary secondary configurations, the air side with CRAH and FW units managing heat removal through terminal PICVs, the liquid system, which includes a heat exchanger separating facility and server loops, and the StatePoint SPLC network managing cold supply and warm return flows. Pay special attention to the system boundary note. Even if loops share similar calculated flow units, they shouldn't be combined without considering differences in temperature, chemistry, and pressure. This ensures accurate control and system integrity throughout. On this slide, we focus on the essential rules for hydronic system design and operation in data center MVAC systems. Starting with the hydraulic rules, the key point is to always calculate flow based on the actual thermal duty and declared delta T, rather than relying on outdated pipe sizes. When building pump head, you must consider one complete index circuit instead of summing all parallel branches. Selecting a pressure-independent control valve, or PICV, should be based on the required flow and the available differential pressure envelope. It's crucial to position delta P sensing at the critical circuit and only reset the pump head with a verified control strategy. Also, treat bypass flow as a controlled state for equipment protection, not as normal distribution. On the operating side, remember that valve command alone doesn't guarantee actual flow. You should monitor trend data for calculated or measured flow. Likewise, pump speed alone isn't proof of capacity. It must be considered alongside flow, differential pressure, and temperature readings. A low delta T indicates a system issue such as overflow, bypassing, sensor bias, fouled coils, or load mismatch. Effective failure recovery needs to be both timed and validated under a representative thermal load. Lastly, approved baselines are essential as configuration-controlled operating assets. To emphasize, if an engineer can't name the index circuit and identify every pressure loss, the pump duty isn't ready for procurement. This test ensures that the design is thoroughly understood and properly prepared before moving forward. On this slide, we have a comprehensive overview of key calculations and assumptions used throughout the Data Center MVAC system training. Let's start with some important abbreviations. VSD stands for Variable Speed Drive, and PICV means Pressure Independent Control Valve. These components play crucial roles in controlling flow and pressure in the system. Moving on to flow calculations, we see that flow rate in liters per second is derived from thermal duty divided by 4.186 times the temperature difference in Kelvin. This formula allows us to convert thermal duty directly into design flow. For pipe sizing, the internal diameter is calculated based on the flow rate and velocity, but always remember to check velocity before finalizing the nominal size to ensure efficiency and avoid issues. Valves are checked using the kV value, which is flow divided by the square root of pressure drop. This helps confirm the valve's suitability, especially for PICVs, which are selected according to flow and pressure envelope requirements. Pump power is another critical calculation, determined by flow rate times pressure difference divided by pump efficiency and converted to kilowatts. This converts hydraulic duty into electrical power input required by the pump. The affinity laws are also shown here, which help us estimate how flow, head, and power change relative to pump speed changes, allowing us to predict turndown performance accurately. Finally, mixing flows are calculated by subtracting secondary flow from primary flow, with the sign indicating flow direction within the decoupler loop. And an important assumption here is that example calculations use standard water properties with specific heat capacity of 4,186 and density about 1,000 kilograms per cubic meter. For glycol or high-temperature loops, we adjust these values accordingly to maintain accuracy. Together, these formulas and principles form the backbone of our hydronic distribution and cooling system design and analysis. Here we have a worked baseline example that demonstrates how to convert a thermal load into a practical, buildable branch for a hydronic distribution system in data center cooling. Starting with a coil duty of 200 kilowatts and a temperature difference of 10 Kelvin, we calculate the flow rate by dividing the load by the product of specific heat and temperature difference, resulting in about 4.78 liters per second. Next, we convert this flow to cubic meters per hour, giving 17.2 cubic meters per hour. Then comes the pipe sizing check. Using a velocity of 1.5 meters per second, the corresponding internal diameter rounds to approximately 64 millimeters, which matches the DN65 pipe size used in this project example. This step ensures the selected pipe size balances flow velocity and pressure drop effectively. Finally, it's crucial to verify actual bore dimensions and confirm final duty with equipment submittals to ensure everything matches in the real installation. Remember, a comprehensive branch schedule should include load, temperature difference, flow, pipe size, valve specifications, pressure allowances, and sensor tags all together for accurate design and operation. On this slide, we focus on how the Pressure Independent Control Valve, or PICV, changes the design workflow for air handling units. Unlike traditional methods, the Danfoss AHU application eliminates the need for valve authority calculations and manual balancing by using a controlled flow setting. The key advantage here is maintaining the required flow despite pressure fluctuations in the system, which enhances stability and efficiency. This means selection starts directly from the flow requirements, rather than relying on conventional kV and authority calculations. The PICV's minimum available valve differential pressure becomes an integral part of the pump head calculation. This stable control also helps prevent overflow and reduces the risk of low delta T conditions. While commissioning is simplified to a set-and-forget approach, it still requires verification based on measured results at the design minimum pressure. Lastly, the design change identifies the index circuit as the branch with the highest total loss at the required flow, including the PICV minimum differential pressure, which is critical to ensuring proper system performance. On this slide, we focus on the Danfoss equipment selection envelope, which helps us identify each device and understand its specific role. First, when choosing equipment, start by reading the product family, generic equipment type, hydraulic layer, and the required evidence before selecting the nominal size. Looking at the ABQM, it's a pressure-independent balancing and control valve, or PICV. Its main function is to regulate the declared flow at terminal branches, even when the available differential pressure changes. To select this device, you schedule the design flow, minimum valve differential pressure, pressure class, and consider the fail position. Next is the NovoCon, a digital valve actuator designed specifically for the ABQM PICV. It controls valve position and sends back position and flow data to the building management system. For selection, specify valve size, protocol, power, input-output, fail behavior, and commissioning feedback. The ASVPV is a differential pressure control valve, or DPCV, used on main riser pressure zones. It limits the differential pressure across that distribution envelope. Selection here means using one controller per pressure zone riser and avoiding duplication at every floor branch. The sonometer is an ultrasonic energy and flow meter. It measures flow, temperatures in and out, and checks the hydronic heat balance. For this, you need to schedule the flow range, accuracy class, straight run requirements, temperature sensors, and communication protocol. Finally, the VLT HVAC drive FC102 is a variable speed drive, or VSD, for pump control. It modulates pump speed based on signals from a validated remote differential pressure transmitter. When selecting this drive, consider motor current, overload protection, enclosure type, harmonics, bypass philosophy, and feedback systems. Remember the procurement rule here. Always state the generic equipment name, hydraulic function, design range, minimum differential pressure, control protocol, fail position, and acceptance evidence. This approach ensures proper specification and successful integration of every component in your hydronic distribution and air-liquid cooling systems. Here, we're looking at the control architecture where demand translates directly into pump speed. The process starts with the load demand, typically captured by an RTD temperature transmitter, or BMS, which measures room or coolant temperature and requests the necessary terminal cooling flow. This flow is then regulated by an electronic PICV with a digital actuator, which not only controls the branch flow, but also confirms the commanded valve position. From there, a remote differential pressure transmitter measures the usable pressure across the active circuit, providing what we call an index proof. Using this data, the HVAC variable speed drive's closed-loop controller modulates pump speed, ensuring it stays within validated limits. The plant response is verified through the inline VSD pump combined with a magnetic flow meter, which checks speed, flow, head, and power consumption all on one-time base. The system also includes a reset sequence to qualify the remote differential pressure transmitter and index branch, adjust differential pressure set points, and ensure useful flow is maintained. In case of sensor failure, the control falls back to an alarmed, validated set point, carefully maintaining speed limits and verifying recovery once the signal returns, rather than simply dropping to minimum speed silently. This comprehensive control proof links the entire sequence, from temperature request to flow and pump speed verification, ensuring reliable and efficient operation. On this slide, we focus on selecting the right topology for hydronic distribution based on operating constraints. Danfoss provides recommended starting points, but the final choice depends on your project's specific needs and limitations. First, consider plant flow and pump configurations. For variable primary flow, the use of a primary variable speed drive, or VSD, is recommended, especially since chillers can handle variable flow and controls protect minimum flow rates. Alternatively, a common VSD setup is also recommended when chillers require dedicated constant flow pumps, but share a common header to avoid secondary pumps. The primary-secondary topology, which involves a constant primary flow and secondary VSD, is acceptable but requires hydraulic separation and close monitoring of mixing risks. Constant flow systems are generally not recommended, as they carry energy penalties and low delta-T performance issues, though they might be retained in legacy systems. Finally, when dealing with district cooling or thermal energy storage, a constant plant flow with secondary or tertiary VSDs is recommended to handle multiple buildings or storage requirements, ensuring hydraulic separation and precise energy transfer measurement. Before issuing PNIDS, it's crucial to record flow limits, redundancy needs, temperature levels, failure modes, and control ownership at the selection gate, so the system architecture aligns perfectly with project goals. Here we focus on plant hydronic topologies within a data center MVAC system. Selecting the right plant arrangement involves considering factors like chiller flow constraints, load diversity, redundancy, and control complexity. The measurable minimum flow strategy is also crucial in this selection. The process follows a clear sequence: select, calculate, sequence, fail, and prove. Remember, the plant topology fundamentally sets every downstream pressure and control boundary, which directly impacts system performance and reliability. Also, keep in mind key abbreviations such as VSD, which stands for Variable Speed Drive, and PICV, meaning Pressure Independent Control Valve. Here we have Danfoss's approach to a variable primary flow system designed for the highest efficiency plant architecture. The key takeaway is that there are no separate secondary pumps. Instead, the primary pumps handle the entire distribution circuit, simplifying the system significantly. Chillers in this setup must be capable of accepting variable flow and often use variable speed compressors to match the load efficiently. A critical feature is the bypass valve, which protects the chiller's minimum flow during part load operation, ensuring stable operation without damage. Control of the variable speed drive pumps is managed from the critical differential pressure point, which is mandatory for maintaining system balance and efficiency. Additionally, terminal pressure-independent control valves and extra pumps are included to support system stability and reliability. One important design consequence is that the bypass valve is sized and controlled based specifically on the chiller's minimum flow requirements, rather than on an arbitrary percentage of the overall design flow, which enhances precision and performance. Here we have a variable primary flow plant configuration where each active primary pump supplies both the evaporator and the distribution head. The system uses a remote differential pressure transmitter to reset the pump speed, ensuring precise control. A measured bypass flow meter protects the chiller by maintaining the minimum required flow only for the active chillers, preventing issues like chiller trips or damage. This setup eliminates the need for booster pumps, as the active pumps handle the necessary head and flow directly, avoiding complex interactions or the need for hydraulic separation. Key components include magnetic flow meters on each chiller circuit, inline primary pumps with variable speed drives, and terminal electronic pressure-independent control valves, all working together to maintain optimal flow and energy efficiency. The process involves reading the active flow path, calculating any required bypass to meet minimum flows, and resetting pump speeds while verifying stable operation and power consumption. This advanced method ensures reliable and efficient chilled water distribution in data center MVAC systems. Here, we're focusing on the flow calculation and turndown for a variable primary flow system in a data center MVAC setup, designed for a 4 megawatt load with a 10-degree Kelvin temperature difference. The key calculation shows that for this design load, the flow rate needed is 95.6 liters per second, or 344 cubic meters per hour. At 65% load, this drops to 62.2 liters per second, maintaining the same temperature difference. We also see the effect of reducing pump speed to 70%, which ideally reduces power consumption to just 34.3%, significantly improving efficiency before real-world adjustments. It's crucial to confirm the final system duty with the actual equipment specifications and respect control limits to ensure flow never drops below minimum operational requirements. This balance between load proportional flow and equipment constraints is fundamental to optimized hydronic distribution in modern data center cooling. Here we focus on determining the pump duty by building it from the complete critical path at the design flow. First, we sum the index losses from each component. The coil contributes 45 kilopascals, pipes 28 kilopascals, fittings 12 kilopascals, strainer 10 kilopascals, and the PICV minimum adds 30 kilopascals, totaling 125 kilopascals. Then, we apply a 10% project allowance to accommodate potential variations, increasing the design pressure drop to 138 kilopascals. Using the design flow of 95.6 liters per second and a total efficiency of 0.78, we calculate the pump input power to be 16.9 kilowatts. It's important to confirm this final duty against the selected equipment submittals, ensuring the procurement duty is based on the submitted system curve, stable operating range, redundancy state, and minimum speed, not just one isolated duty point. This comprehensive approach ensures reliable system performance. On this slide, we're focusing on the VPF sequence along with safeties and failure recovery in the Data Center MVAC system. Every state transition, starting, staging, and stopping, is conditional on proof from valves, pumps, and measured flow. When starting, we first confirm common isolations, then open the active chiller's pressure-independent control valve and isolation valve, proving their positions before starting the variable speed drive pump at a validated low speed. The chiller is only enabled after the measured flow exceeds its minimum threshold for a required delay. Additional chillers stage in as the load demands, with valves and pumps ramped carefully to avoid flow shock. Stopping is done in reverse order, isolating idle chiller branches to prevent unwanted flow. In terms of fault response, several safeguards are in place. For example, if the remote differential pressure sensor is lost, an alarm triggers and the system switches to a tested fallback pressure set point. Losing the flow meter prohibits unsafe staging and holds a conservative state, while a pump trip starts a standby pump that must prove speed and flow before recovery is accepted. If the bypass valve fails open, the system alarms based on flow and temperature signature, protecting cooling during repairs. Additionally, any low-flow alarms require thorough verification of valves, flow meters, staging, and bypass logic rather than simply increasing pump speed. Finally, the integrated test requires demonstrating each declared failure under thermal load while maintaining synchronized trends within 1 to 5 seconds during recovery, ensuring reliability and safety throughout operation. On this slide, we're looking at the step primary plant design with dedicated pump trains, positive isolation, and measured minimum flow. Each chiller is paired with its own variable speed drive pump, creating a matched hydraulic train. This setup allows capacity to be added or removed in discrete steps, with only the active pumps modulating within the chiller's certified evaporator flow range. Motorized isolation valves, or MIVs, are placed at both the supply and return boundaries of each train. These valves must be verified open before the pump and chiller enable and prove closed when inactive, which ensures no unintended flow through idle branches and allows for proper isolation during maintenance. A modulating flow control valve, or FCV, is installed downstream of a bypass flow meter, normally closed. It only opens when the measured terminal demand falls below the combined minimum evaporator flow of active chillers, protecting the chillers from insufficient flow. Importantly, this valve is not for controlling terminal pressure differential, and if it's frequently open, that signals either excess staged flow or load instability. Finally, the remote differential pressure transmitter provides feedback to finely adjust pump speed, maintaining the right pressure at the critical system point without compromising minimum flow requirements. This architecture ensures efficient, reliable operation with precise flow management in your chilled water system. On this slide, we're looking closely at the detailed equipment sequence for a single active step primary chiller, pump train. This sequence shows the exact order of inline components for one train, with the understanding that identical trains are always added or removed as full match stages. Starting with isolation valves, MIVR and MIVS, they define the boundary for the train's operation. The suction and discharge pressures, along with the variable speed pump, set the necessary operating head. The non-return valve ensures there's no reverse flow through a pump that's stopped, which is critical for system protection. Next, a magnetic flow meter confirms that evaporator flow is adequate before the chiller is enabled. This proof of flow is a key commissioning step. The whole train's permissive condition requires both isolation valves to be open, the pump running, and confirmed flow from the meter. Additionally, there's a focus on minimum flow management. A bypass flow meter and a flow control valve work in tandem to handle any deficit, ensuring the chiller always operates within its certified flow envelope. Terminal units like CRAH and FW use electronic PICVs to control flow independently from changes in distribution pressure. Finally, a differential pressure transmitter located at a remote critical point continuously adjusts the pump speed to maintain the correct pressure, helping optimize system efficiency. If the flow control valve remains persistently open, it signals possible issues like excess staged flow, low system load, or incorrect minimum flow settings, which would need addressing. Here we have a worked example focusing on step primary staging and bypass flow involving three 1.50 megawatt chillers with a 10 Kelvin design temperature difference. We're asked to evaluate a 2.40 megawatt operating point and confirm the bypass flow direction. First, for each chiller stage rated at 1.50 megawatts, we calculate the flow using the formula Q equals power divided by the product of water's specific heat and delta T, giving us 35.83 liters per second per chiller. Since the 2.40 megawatt load exceeds one chiller stage, we enable two chiller pump pairs working together, effectively doubling the available flow to 71.66 liters per second. Next, we determine the actual load flow at 2.40 megawatts, which equals 57.33 liters per second. By subtracting this from the available active flow, we find a positive bypass of 14.33 liters per second, flowing from chilled water supply to return. This positive bypass is expected right after the second stage kicks in, but if it remains large, it means pumping is wasted and the return temperature suffers. The solution is to trim the active pump flow within the chiller's operating envelope. Conversely, if the bypass becomes negative, it indicates the load flow exceeds the evaporator's capacity, requiring staging adjustments or correction of demand errors. Finally, control systems should monitor key parameters like stage count, individual evaporator flows, bypass flow and its direction, chilled water temperatures, pump speed and power, and differential pressure. Alarms should trigger on negative bypass combined with rising supply temperature, helping maintain system balance and efficiency. On this slide, we're looking at a primary-secondary plant design that uses hydraulic separation with independent pump control. The key point here is that each chiller operates with its own dedicated primary pump and associated components, including motorized isolation valves, check valves, and flow meters. This setup ensures the chilled water flow through the evaporator stays within certified limits, protecting the equipment and maintaining efficient operation. The low-loss decoupler acts as a hydraulic separator between the primary and secondary circuits. It carries only the instantaneous flow difference between the primary and secondary sides, which helps to prevent interference between the two circuits. When the decoupler flow is positive, it indicates a primary surplus. When it's negative, the secondary side is demanding more flow than the primary is supplying, causing some mixing and slight warming of the secondary supply. Downstream of the decoupler, the secondary circuit features a variable speed drive pump bank that modulates to match terminal demand independently of the primary pumps. Terminal units like computer room air handlers and fan wall units use electronic pressure-independent control valves to precisely regulate flow. Additionally, a remote differential pressure transmitter feedback loop adjusts the secondary pump speed to maintain just enough pressure for valve control. This coordination between flow, pressure, and chiller status ensures efficient staging of pumps and chillers, while avoiding unnecessary water mixing and energy waste. Here we are focusing on how signed decoupler flow reveals hydraulic imbalances before temperature alarms are triggered. The key diagnostic rule involves verifying the difference between primary and secondary flow, confirming flow direction, calculating the mixing temperature, applying a time delay, and then staging or destaging complete primary trains accordingly. When the signed decoupler flow, which is the difference between total primary and secondary flow, is positive, it indicates a primary surplus. This means excess primary chilled water supply flows down the decoupler to the chilled water return, causing wasted pumping energy and reduced system delta T. The recommended action here is to destage one complete primary train, but only after minimum runtime and flow envelope checks to ensure stability. If the signed decoupler flow is approximately zero, we have hydraulic balance. Here, the primary and secondary flows are closely matched, the decoupler flow is negligible, and the secondary supply temperature stays close to the primary chilled water supply temperature. In this case, the system should hold staging and keep monitoring sensor plausibility and differential pressure remotely. When the sign decoupler flow is negative, we have a primary deficit, meaning the common chilled water return moves upward and mixes with the primary chilled water supply. This causes the secondary supply temperature to rise even if the chiller leaving water temperature is correct. The response required is to stage proven primary capacity or reduce secondary flow, investigating the cause if the condition continues. It's critical not to rely on a single sensor reading. Always cross-check the sign decoupler flow against measured primary minus secondary flow, consider meter uncertainties, and validate flow direction using mixing temperature. Pay attention if the sign decoupler flow is near zero but the mixing temperature rises, as this may indicate meter zero drift, reverse signals, sensor bias, or other faults. Control actions should use persistence and deadband to avoid chasing temporary fluctuations. Only stage or destage full matched chiller and primary pump trains, respecting minimum runtimes and flow limits to maintain stable and efficient system operation. This approach ensures early detection and correction of hydraulic imbalances before temperature alarms become an issue. Here, we're working through an example focused on the primary-secondary decoupler flow and mixing in a data center MVAC system. First, we establish the signed flow by calculating the decoupler flow as the difference between primary and secondary flows. Positive values indicate supply water spilling back to the return. In the normal surplus case, the primary flow exceeds the secondary, resulting in a downward spill of 14 liters per second. Conversely, in the deficit case, the secondary flow pulls 14 liters per second of warmer return water upward. This leads us to the mixed supply temperature calculation, where with a 6 degrees Celsius primary supply and 14 degrees return, the mixed temperature comes out to 7.56 degrees. It's important to understand that a negative decoupler flow doesn't necessarily mean a pump speed problem. It could signal issues like an unavailable primary stage, closed isolation valves, or excessive terminal demand. To address this, we must verify primary branch flow and adjust system capacity before increasing pump head. During commissioning, we test secondary flow at stable points to confirm flow direction, energy balance, and the accuracy of mixed temperature measurements. This thorough approach ensures the decoupling and mixing operate reliably and efficiently in your hydronic system. Here we have a constant flow distribution system using a terminal three-way valve bypass that preserves flow but sacrifices efficiency. This approach is a technically valid legacy or OEM exception where each terminal diverts unused chilled water around its coil, so total pump flow remains roughly constant regardless of load changes. However, this is not the preferred baseline for new data center designs. The key decision here is to retain this setup only if there's a documented OEM minimum flow requirement or legacy constraint, and only when the annual penalty in pumping energy and low temperature difference, or delta T, has been quantified. Otherwise, the better approach is to use two-way PICV terminals with variable flow pumping. The plant control intention is to stage complete chiller pump trains where each enabled pump holds its commissioned flow, without any remote differential pressure speed resets. At each terminal, the three-way valve shifts water flow between the coil and the bypass so that the total flow, coil plus bypass, stays approximately constant. This means as thermal load falls, the valve closes the coil path and opens the bypass by the same amount, maintaining a steady flow but mixing warmer bypass water with cooler coil return, which reduces the overall system delta T. To illustrate why this is less efficient, consider an example where the plant flow is 200 liters per second, split into 120 liters through the coil and 80 liters bypassed. About 40% of the pumped water serves no cooling load. With chilled water supply at 7 degrees Celsius and coil return at 15 degrees, mixing results in a return temperature around 11.8 degrees, dropping system delta T from the coil's 8 degrees down to 4.8 degrees. This reduced temperature difference forces an increase in flow and pumping energy per useful kilowatt of cooling. So while this method keeps flow steady, it sacrifices efficiency substantially compared to a variable flow pumping system with two-way valves. On this slide, we're diving into the details of pumped stratified thermal energy storage, focusing on controlled charge, controlled discharge, and a direct bypass strategy. The plate heat exchanger, or PHE, plays a crucial role by separating district and facility water systems. We have dedicated TS pump paths and motorized isolation valves that establish the flow direction, while the distribution pump bank operates independently, matching the demand from the computer room air handlers and fan wall units. The system's functional proof involves verifying valve positions, pump operation, flow direction, temperature stratification across 5 levels, and energy balance within the PHE. We monitor the state of charge through temperature transmitters and use differential pressure transmitters remotely to reset pump speeds. This setup ensures fail-safe operation by defaulting to a direct bypass if abnormal conditions are detected, allowing the PHE to serve the load without interruption. The TS pumps are essential because they regulate charging and discharging flows separately from the distribution pumps, maintaining optimal thermal stratification and flow control in the TS tank. The 5-level temperature profile confirms proper stratification, with warm water at the top, cold water at the bottom, and a thermocline in between. Alarms are set for temperature inversions or other irregularities, ensuring system integrity and reliable cooling performance. On this slide, we're focusing on the plant topology decision matrix for hydronic distribution in air and liquid cooling systems. The key here is to score the architecture against real operating constraints before finalizing the PNID. This matrix helps us evaluate different configurations like variable primary flow, step primary, and primary secondary setups. We consider important decision factors such as whether variable chiller flow is permitted, the level of distribution pumping energy, and strategies for minimum flow and bypass. Control and commissioning complexity also plays a big role, ranging from simple but inefficient to advanced and clear. Finally, the matrix includes Danfoss position, highlighting which topologies are recommended, acceptable, or not recommended. As a consultant deliverable, it's essential to issue the selected topology along with a 1-page rationale, index duty schedule, control narrative, and a failure state matrix to ensure clarity and proper implementation. Here, we're focusing on the CRAH and FWU distribution systems within hydronic distribution and air and liquid cooling. The key challenge is to translate plant flow into pressure-independent terminal branches. This ensures these branches remain controllable even during diversity, phased fit-out, maintenance, or pump failure. The process follows a sequence from load to branch, then index, followed by delta P reset, and finally a functional test. Remember, the terminal valve acts as the control boundary, while the index circuit is responsible for setting the pump head. This approach ensures reliable and efficient operation of the cooling system under varying conditions. Here we focus on a serviceable CRAH terminal branch with pressure-independent control, ensuring service access and measurable thermal duty. One critical requirement is that the branch must deliver its declared coil flow without a permanent bypass, while maintaining vent, drain, and flush provisions for proper maintenance. In the acceptance process, we verify isolation and flush proof by cleaning the strainer and venting the coil. Then we command the E-PICV to confirm its position and flow through the flow meter. We measure differential pressure across the PICV, as well as incoming and outgoing water temperatures, alongside fan or load status, to establish thermal balance and conduct failure tests. The design for this particular CRAH coil is 200 kilowatts of sensible duty, with a flow rate of 4.78 liters per second at a 10-degree Kelvin temperature difference. The calculated flow rate translates to 17.2 cubic meters per hour. The control strategy uses a single electronic pressure-independent control valve, or E-PICV, which ensures the valve alone governs flow with verified minimum differential pressure. This avoids the need for a permanent coil bypass, branch differential pressure control valve, or any secondary balancing or control valves. Flow direction moves from chilled water supply through the coil and E-PICV back to the chilled water return. The index pressure budget allocates 90 kilopascals across coil, strainer, flow meter, piping, and valve loss components. The control intention is a single valve with one feedback chain, where the CRAH fan or load status enables the valve to modulate flow to meet cooling demand. The building management system records command signals, actuator position, flow meter readings, and entering and leaving water temperatures. Distribution pump differential pressure is reset based on this verified worst-case branch to maintain stable hydraulic conditions. Commissioning includes isolating and flushing the branch, cleaning the strainer, venting air from the coil, and verifying drain valve shutoff. Full valve opening confirms design flow and minimum differential pressure. We then record all pressure and temperature readings, verify control stability through part load sweeps, check sensor plausibility, fail-safe valve positioning, alarm function, and return to service protocols. All these steps ensure reliable hydronic control and measurable thermal performance for optimal data center cooling operation. Here we focus on naming and specifying CRAH equipment by hydraulic function first, rather than relying solely on manufacturer or model references. The key is to use a clear schedule format that moves from the common engineering name to equipment tag, manufacturer and model, connection sizes, design flow, and control details. For example, the pressure-independent control valve, or PICV, combines a few crucial functions. It maintains stable terminal flow despite pressure changes by regulating differential pressure and limiting design flow. When selecting a PICV, we choose the exact valve size and model based on more than just pipe diameter. It's about flow, pressure class, and actuator compatibility. Typically, the PICV is placed in the CRAH return branch and acts as the main automatic hydronic control device. Importantly, if the PICV is properly selected and commissioned, manual balancing valves or additional pressure control valves shouldn't be added in series. For actuation, smart digital controllers like the Danfoss Novocon convert building management system commands into precise valve positions. These actuators communicate diagnostics and settings digitally and must be matched carefully to the valve size, protocol, and installation requirements. Finally, manual balancing valves, often called double regulating valves or DRVs, serve a different purpose. They provide fixed hydraulic balancing with manual presetting and shutoff, but don't adapt automatically to changing pressures. These are used where a fixed flow setting and commissioning measurement point are required. However, they must never be used as a substitute for PICVs or installed redundantly alongside correctly designed PICV terminals. Understanding these distinctions and following the correct naming conventions ensures accurate specification and smooth operation in data center MVAC hydronic distribution systems. Here we have a worked example for a computer room air handler, focusing on flow, pipe sizing, PICV selection, and calculating the index head. We start with a 200 kilowatt terminal requiring a design flow of 4.78 liters per second. This flow rate equates to 17.2 cubic meters per hour, calculated by dividing the power by the product of specific heat and temperature difference. Next, we trial a pipe size of DN65, which yields a velocity of about 1.45 meters per second, and verify that this meets velocity, noise, and friction criteria for the project. Then we calculate the index circuit losses, which include pressure drops across the coil, the PICV at minimum setting, associated pipe and fittings and strainers, totaling 125 kilopascals. Applying a design allowance of 10% brings this to 137.5 kilopascals, or 14 meters of water head. We then determine the pump input power at this duty, using flow, pressure, and pump efficiency. This results in 0.88 kilowatts. Importantly, we do not add building height, because in a closed-loop system, elevation gained on the supply side is recovered on the return, making the pump head equal to the dynamic pressure loss around the circuit plus the design allowance. Finally, the duty point is plotted on the certified pump curve to confirm parameters like operating range, net positive suction head margin, motor loading, minimum speed, control stability, and that the PICV maintains its minimum differential pressure at the most remote terminal. This transparent calculation chain ensures the pump selection is fully auditable and prevents errors, such as incorrectly adding static elevation to the pump head. Here we have a clear example of calculating flow, pipe sizing, PICV, and index head for a CRAH unit. We start with a 200 kilowatt terminal and a design flow of 4.78 liters per second. First, we calculate the water flow by dividing the terminal load by the product of specific heat and temperature difference, which gives us that 4.78 liters per second or 17.2 cubic meters per hour. Next, we select a pipe size, in this case DN65, because it provides an acceptable velocity around 1.45 meters per second, which meets noise and friction criteria. Then, we estimate index circuit losses, including the coil, PICV minimum differential pressure, pipes, and fittings, totaling 125 kilopascals. We add a design allowance of 10%, increasing the pressure drop to 137.5 kilopascals, equivalent to 14 meters of water column. To find the pump input power, we use the flow rate, pressure drop, and pump efficiency, resulting in 0.88 kilowatts. Importantly, we do not add building elevation since, in a closed-loop system, elevation gained in supply is recovered on return. The pump head reflects the dynamic pressure loss around the entire index circuit plus the allowance. Finally, we validate the selected pump by plotting the duty point on the certified pump curve and confirming factors like point of operation range, net positive suction head margin, motor loading, minimum speed, stability of control, and the PICV minimum differential pressure at the farthest terminal. This transparent calculation chain ensures proper, auditable selection and prevents mistakes in adding static elevation to closed-loop pump head. On this slide, we focus on the CRAH control sequence, which is designed to maintain a stable temperature difference at minimum pump head. First, the CRAH controller initiates a load request by signaling the need for cooling based on return and supply air conditions. Once cooling is requested, the valve control comes into play. The Novocon actuator modulates the ABQM valve to restrict flow to a set design maximum, ensuring proper distribution without overload. Next, the pump responds through remote differential pressure control, adjusting speed to meet the circuit's requirements rather than holding a fixed discharge pressure. Then, the system resets by using validated valve positions or flow data to fine-tune the pressure set point, maintaining stable system control. Finally, limits are established to trigger alarms if conditions like high flow, low temperature difference, sensor errors, or actuator failures arise. This prevents unnecessary increases in pump head. The key is achieving a tuning target where the index PICV valve remains properly open at stable load, demonstrating low available head without causing oscillations or hunting. This coordinated control sequence optimizes airside demand, terminal flow, and pump pressure effectively. On this slide, we focus on the comprehensive construction and commissioning proof process for the CRAH, or computer room air handler, within a data center's MVAC system. Every requirement must be closed with a measurable record, not just a visual inspection. Starting with the clean gate, it's crucial to have flushable branches, accessible strainers, drains at low points, and vents at high points to maintain system cleanliness. We verify this with cleanliness records and differential pressure across strainers, supported by signed flushing sheets and baseline pressure drop readings. Moving to install, we check that flow arrows are correct, actuator service spaces are clear, and sensors are properly immersed and insulated. This step includes a thorough tag walkdown, point-to-point checks, and temperature comparisons, all documented with a redline PNID and calibrated point list. The hydraulic stage ensures all branches are available and isolation positions controlled, demanding 100% command at design minimum differential pressure and scheduled flow values, monitored through flow, pressure, and position trends. Control verifies sequences are loaded, fallback set points approved, and critical failure scenarios like pump failover are tested, with timed event trends and pass/fail reports recorded. Finally, at handover, settings are locked, spares and training completed, and a repeat baseline established after final cleaning, culminating in an approved operating baseline and detailed change log. Importantly, there's a hold point, where valve settings or VSD set points must not be accepted until the final strainers are clean and all flow paths are correctly positioned, ensuring system reliability and performance. On this slide, we're focusing on diagnosing CRAH units using hydraulic signatures, which is essential for effective maintenance. We use a combination of flow, temperature differential, valve position, remote pressure, and pump speed to pinpoint issues. For example, if the valve is fully open but flow and remote pressure are low, it often indicates insufficient pump head or a restricted path. Here, we check pressure differences and inspect strainers and isolations before restoring the flow path. Another common scenario is a low valve command paired with high flow and low temperature difference, suggesting possible actuator faults or bypass leakage, which we confirm by testing stroke and feedback. We also look for signs like high pump speeds with rising pressure loss that could signal fouling or blockages. Trending the differential pressure across strainers and coils helps us detect this early. Additionally, flow and temperature fluctuations, or hunting, might stem from sensor noise or unstable loop tuning. So high-resolution trend analysis is key to correcting these problems. Finally, when all branches overflow, it's usually due to sensor or pump setpoint errors, requiring us to compare sensor readings and restore proper control sequences. Remember, never troubleshoot a low delta T alarm based solely on temperature. First determine whether excess flow, bypass flow, or inadequate heat transfer is causing it to effectively solve the problem. On this slide, we're focused on the fan wall unit branch, which represents a single controlled thermal circuit. The key here is how isolation allows for servicing without disrupting the whole system. The electronic pressure independent control valve, or E-PICV, plays a crucial role by precisely metering the design flow. We also rely on paired water measurements to verify the actual coil duty delivered. Notice the process for commissioning. First, ensure the coil is clean, vented, and isolation valves are open. Then, command the E-PICV to 100% and verify it's achieving the design flow. Next, confirm the valve's minimum differential pressure at its ports. Finally, record the entering and leaving water temperatures along with the declared fan or load state. Only after achieving thermal stability should you trim the flow, because accepting thermal duty, not just flow alone, is essential to proper operation. This systematic approach ensures accurate control and efficient performance in data center HVAC systems. Here we have a worked example focusing on a fan wall unit, specifically examining flow, pipe sizing, and terminal authority. The key to this approach is a transparent calculation chain, which ensures the pump selection is fully auditable and prevents the common mistake of incorrectly adding static elevation to closed-loop pump head. Starting with the terminal load, we have a 120 kilowatt demand, which translates to a design flow of 3.58 liters per second. This flow rate is calculated by dividing the power by the product of specific heat and temperature difference, confirming the required volumetric flow of 12.9 cubic meters per hour. Next, when trialing pipe sizes, a DN50 pipe yields a velocity of about 1.82 meters per second. This velocity must be verified against noise criteria, friction losses, and project standards to ensure suitability. Then we calculate index circuit losses. These include pressure drops across the coil, the electronic PICV at its minimum differential pressure, pipes, fittings, strainers, and meters, totaling 118 kilopascals. To accommodate any uncertainties, a design allowance of 10% is applied, bringing the required pressure to approximately 129.8 kilopascals, or 13.2 meters of water column. The pump input power at this duty point is then determined by multiplying flow by pressure drop and dividing by pump efficiency, resulting in about 0.64 kilowatts. Importantly, we do not add building height to the pump head in a closed-loop system because the elevation gained in the supply is recovered on the return. Thus, pump head represents the dynamic pressure losses around the entire index circuit plus the design allowance. Finally, the selected pump duty point, 3.58 liters per second at 129.8 kilopascals, is plotted on the certified pump curve. Key checks include ensuring pump operating range, net positive suction head margin, motor loading, minimum speed, control stability, and that the PICV minimum differential pressure is met at the farthest active terminal. This detailed step-by-step process ensures accurate pump selection and system reliability for the data center's fan wall unit. Here we focus on the commissioning and operating limits of fan wall units, or FWUs, in data center MVAC systems. First, compact branches, despite their size, still require full hydraulic proof and carefully controlled failure states to ensure reliable operation. During commissioning, we need to confirm the final valve model and flow settings in line with the approved FWU duty schedule. It's essential to verify actuator commands, feedback, fail positions, and communications both locally and in the building management system. We measure flow at the design command, while maintaining the remote differential pressure at a validated minimum, and supply and return sensors must be cross-verified before accepting the delta temperature. After cleaning the strainer, all these measurements should be repeated and the final baseline trend retained. Regarding operating limits, there are several key points to watch for. A high valve command paired with low flow likely indicates insufficient available pressure or some restriction. On the other hand, a low command with high flow points to incorrect settings, actuator issues, or bypass leakage. If normal flow occurs with low delta T, then the problem is likely on the heat transfer, load, or air side, rather than the pump itself. Also, running a high pump speed while many valves are barely open may suggest an excessive set point or sensor errors. Finally, any disabled FWU must be prevented from experiencing uncontrolled ghost flow through open valves or bypasses. Maintaining an operating baseline is crucial. Record flow, delta T, command and feedback signals, remote differential pressure, and pump speed at least at 3 representative load states to ensure ongoing system performance. Here we're examining the impact of low delta T syndrome on system performance. The key figures show a useful load of 2 megawatts, with a design temperature difference of 10 Kelvin, but the observed delta T is only 6 Kelvin. This leads to a significant increase in flow rate, specifically from 47.8 liters per second in the design state to 79.6 liters per second in the low delta T state, a 7% rise in flow for the same load. If the system were dominated by friction, power consumption could theoretically increase by a factor of 4.63 times, though this is just an illustrative upper limit. The takeaway here is to carefully verify the system performance by checking for issues such as overflow, bypass leakage, sensor errors, fouling, or load mismatches before making any decisions like increasing pump head or adding capacity. Addressing these problems first is crucial to maintaining efficient and reliable cooling performance. Here, we're focusing on some key abbreviations crucial to understanding this module. CDU stands for Coolant Distribution Unit, FWS is the Facility Water System, and TCS refers to the Technology Cooling System. It's important to recognize that a CDU is not just a single pump package, but actually consists of 2 hydraulic systems connected through heat transfer. This design allows the facility water system to reject heat effectively, while the technology coolant system maintains the server inlet conditions. We apply variable flow pressure control across the heat exchanger boundary to optimize this process. The sequence of capacity in the FWS, the heat exchanger approach temperature, TCS flow rates, leak response, and proofing all play vital roles in ensuring efficient and reliable cooling in the data center. Here we have the Vertiv CoolChip CDU 600, a liquid-to-liquid coolant distribution unit designed for data center cooling. This equipment has a capacity of 600 kilowatts, measured at a 4 degrees Celsius heat exchanger approach. The physical dimensions are 2,000 by 600 by 1,200 millimeters, covering height, width, and depth. Key features include redundant variable speed pumps for reliability, integrated filtration, and dual power feeds to ensure continuous operation. It also offers a touchscreen interface and remote monitoring capabilities, along with Modbus ArcEU and TCP communications for seamless integration. The CoolChip family covers a wide range from 70 to 2,300 kilowatts, with several models suitable for liquid-to-liquid cooling. A crucial design caution is to remember that the 4-degree value refers to the heat exchanger approach, not the loop temperature difference. Therefore, it's essential to select facility water system and technology cooling system flows based on their specific temperature programs. This ensures optimal hydraulic performance in your cooling setup. On this slide, we're looking at the critical boundary between the facility water system and the technology cooling system, separated by a liquid-to-liquid plate heat exchanger. The key point here is that energy transfers across this boundary, but fluids, pressure, and chemistry do not. This means each loop operates independently with its own flow control, pressure control, and water quality management. Starting with the facility water system, or FWS, this loop is responsible for rejecting heat through the plate heat exchanger. It uses an electronic pressure-independent control valve to modulate flow based on temperature demand, and the magnetic flow meter confirms the heat transfer by measuring flow and temperature difference. On the other side, the technology cooling system, or TCS, protects the IT coolant network. It uses N+1 variable speed drive pumps to maintain differential pressure for the racks while ensuring stable supply temperature, filtration, and coolant quality. Leak detection here is crucial and coordinates with system isolation and server protection to ensure safety. For acceptance, each side must be verified independently. Thermal performance is checked via heat balance and approach temperature. Hydraulic parameters like valve authority and differential pressure must be proven, and system integrity is confirmed through pressure tests, coolant quality verification, and leak detection readiness. Altogether, this boundary design ensures reliable and safe operation by strictly separating energy transfer from fluid and chemical cross-contamination, while maintaining precise control and monitoring on both sides. This slide covers the CDU two-loop control system, highlighting its thermal, hydraulic, and safety paths, which all operate independently. The FWS valve manages heat rejection across the plate heat exchanger, while the TCS pumps maintain the rack differential pressure, with leak logic overriding both control loops to ensure safety. The system physically separates two hydraulics. The facility water system isolates, strains, measures flow, temperature, and pressure, then transfers heat through the plate heat exchanger, modulating the return flow. Meanwhile, the technology cooling system establishes expansion pressure, circulates coolant with N+1 variable speed pumps, prevents reverse flow, filters coolant, and supplies the rack manifolds and cold plates. Notably, the plate heat exchanger transfers energy only, keeping facility water and technology coolant separate, and allows service on either loop without opening the other. Control intent is divided into 3 signals and 3 outputs. The blue thermal loop controls the facility flow valve, the green hydraulic loop adjusts TCS pump speed and staging, and the red safety loop oversees isolation, pump stop, and alarms based on leak detection. The system's sequence and resilience focus on proving isolation valves and pressure readiness, operating with continuous monitoring of flows, temperatures, pressures, and safety inputs, and failing safely by transferring control, isolating leaks, and maintaining stability in pump operation and heat balance. This integrated control and proof approach ensures reliable, safe cooling for the data center. Here, we're focusing on the technology cooling system, or TCS, which is crucial for controlling the server loop in a data center environment. The TCS flow, chemistry, and pressure are all managed within the boundaries of the Coolant Distribution Unit, or CDU. It's important to note that the server inlet temperature and allowable temperature approach should be set based on IT or OEM requirements, rather than copying the facility water system's temperature difference. When calculating the TCS flow, you factor in the IT heat load and the approved coolant temperature difference, while also accounting for pressure losses from manifolds and cold plates. To maintain proper operation, redundant variable speed pumps within the CDU regulate supply pressure and flow in the technology loop. Key reliability functions like filtration, expansion, air separation, chemistry control, and leak detection are all part of the TCS responsibilities. We also need to limit differential pressure across racks and manifolds, as well as hose and cold plate flow, because simply increasing pressure isn't a substitute for clean and effective cooling distribution. Monitoring trends in pump operation, supply and differential pressure, flow rates, temperatures, filter pressure drops, and leak alarms is essential for maintaining system health. Finally, during TCS acceptance testing, it's vital to verify performance with the hydraulically most remote manifold under the declared server configuration, then confirm continued operation with one CDU pump out of service. Here we have a worked example of a coolant distribution unit, or CDU, dealing with unequal facility and technology flow rates. The key idea here is that a heat exchanger transfers energy, not equal volumetric flow, so each loop's flow follows its own design delta T and fluid properties. For the facility water system, we calculate a flow rate of 14.33 liters per second, based on a 600 kilowatt load and a 4 degrees Celsius temperature difference. Meanwhile, the technology cooling system, with a different temperature delta of 15 degrees, has a lower flow rate of 9.56 liters per second. Notice that the approach temperatures are different on each side, which is why these flow rates are not the same. The facility PICV adapts to the heat exchanger's capacity demand, while technology pumps maintain the required differential pressure in the rack loop. The important takeaway is that both flow values are correct because they reflect different delta T values. And when using glycol or dielectric fluids, you should adjust the specific heat and density to match design temperatures. Finally, the energy balance confirms that the heat input from the facility side nearly equals the heat removed on the technology side, validating the system's performance. Any persistent imbalance could indicate sensor errors, incorrect fluid properties, or other issues affecting accuracy. On this slide, we're focusing on the CDU facility loop pump head through an index loss calculation. The main goal here is to sum up only the dynamic losses within the closed-loop circuit that governs the system. We then apply a transparent allowance before verifying the certified pump curve to ensure accuracy. Starting with the components, the heat exchanger introduces a loss of 70 kilopascals at the design flow, followed by the pressure-independent control valve at a minimum of 30 kilopascals. Next, pipe and fittings contribute 78 kilopascals, and the strainer with meter adds another 12 kilopascals. When we total these losses, including a 10% allowance for safety, we arrive at 209 kilopascals or 21.3 meters of head. For input power, we use the flow rate and pressure drop to calculate the hydraulic duty input as 4.16 kilowatts. It's important to note this is not the final motor selection power, but rather the hydraulic input needed from the pump. Finally, the selection process involves verifying several critical factors: the certified head flow and efficiency curves, net positive suction head margin, motor rating, minimum continuous flow, parallel pump staging, and stable remote differential pressure control during low load conditions. This approach ensures the pump is correctly sized and operates efficiently within the facility water system, maintaining optimal cooling performance in the CDU loop. Here we focus on the CDU technology loop pump head and the index loss calculation. The key idea is to sum only the dynamic losses in the governing closed-loop circuit, then apply a transparent allowance before verifying the certified pump curve. Starting with the components, cold plates and manifolds contribute 150 kilopascals. The CDU heat exchanger adds 82 kilopascals, pipes and fittings account for 70, and filters plus instruments contribute 13. Adding these gives a subtotal of 315 kilopascals, which after applying a 10% allowance becomes 347 kilopascals, or 35.4 meters of head. Next, we check input power using the formula PIN equals flow rate times pressure loss divided by efficiency, which here results in 4.74 kilowatts of hydraulic duty input. This is an intermediate step, not the final motor selection. Finally, we must verify key selection criteria: the certified head flow and efficiency curves, NPSH margin, motor rating, minimum continuous flow, parallel pump staging, and stable remote differential pressure control at low load. Remember, this process ensures optimized pump performance and reliability within the 600 kilowatt CDU operating at a 4 degrees Celsius approach. Here we have key abbreviations to keep in mind. CDU stands for Coolant Distribution Unit, FWS is the facility water system, and TCS refers to the technology cooling system. The CDU plays a critical role in maintaining the TCS operating envelope while working in harmony with the FWS plant to avoid conflicts. Under normal conditions, the CDU modulates TCS pumps to maintain server loop pressure and flow, simultaneously requesting capacity from the FWS based on load and approach. If one TCS pump is lost, the system quickly starts the redundant pump, carefully limiting the ramp rate, confirming remote manifold pressure, and monitoring time for recovery. When FWS flow is low, the priority is to protect the IT outlet temperature by increasing validated requests and checking the plant state and potential capacity risks. If there's a high filter differential pressure, alarms alert staff to progressive restrictions so that filter changes can be scheduled before flow drops too low. In the event of a leak, the system executes approved isolation procedures by leak zone to preserve evidence and prevent uncontrolled refills. Finally, failure testing involves timing pump switchovers, monitoring pressure recovery, temperature excursions, and alarm propagation to ensure compliance with the IT system's thermal ride-through capabilities. This coordinated approach ensures reliability and resilience in the cooling system. On this slide, we focus on the commissioning process for the Coolant Distribution Unit, or CDU, within the Data Center MVAC system. The CDU integrates two critical loops: the Facility Water System, or FWS, and the Technology Cooling System, or TCS. We commission these loops separately at first, then demonstrate effective heat transfer and the system's ability to handle shared failure scenarios. The commissioning is broken down into several stages. The prefill stage includes flushing and sampling the facility branch, ensuring strainers and valves are functional, and preparing the technology loop according to approved coolant protocols. Then during the static stage, Pressure tests confirm there are no leaks or boundary crossovers, with relief and expansion systems verified. Moving to the hydraulic stage, we measure flow rates and pressure drops, reconciling pump curves and set points to actual system losses. The thermal stage verifies heat balance and system capacities at representative loads, checking inlet and outlet temperatures specifically for the FWS and TCS. Finally, the failure stage tests various plant and pump scenarios, recovery times, alarm functionality, and safe state acceptance. All these data points, chemistry, cleanliness, pressure, flow, thermal performance, failover results, and point-to-point tests, are documented and retained under a single CDU asset identifier, ensuring comprehensive traceability and reliability of the system. Here we're focusing on the operation and maintenance of the coolant distribution unit, specifically alarms that indicate hydraulic causes. It's critical to first correlate the facility water system and technology cooling system signatures before making any adjustments, like replacing components or raising set points. Key checks include monitoring flow, supply temperature, valve positions, and potential fouling in both systems. If you notice a high heat exchanger approach or low remote TCS pressure, investigate pump speed, filter differential pressure, and possible leaks to ensure IT flow protection. Another common issue is fouling or restrictions caused by added racks or manifolds, so always compare to a clean baseline. Remember, maintaining a correct heat balance and avoiding unnecessary flow reduction is essential. Never starve the CDU. Lastly, save clean filter and design load signatures for both loops as your O&M baseline, because without these, gradual restrictions can appear as unexplained capacity loss. This proactive approach helps keep the cooling system running efficiently and prevents downtime. Here we focus on the StatePoint liquid cooling network within the Data Center MVAC system. The key idea is to use StatePoint's cold supply and warm return lines as a controlled variable flow distribution network. This network serves critical components like fan walls, CRAH units, and liquid cooling heat exchangers. The ambient state influences the mode, which then determines the supply temperature. From there, the terminal devices control the flow rate, resulting in the warm return temperature we monitor. Modes are essential because they control the water temperature, while hydronic demand primarily controls how much water flows through the system. This approach optimizes cooling efficiency and responds dynamically to changes in data center thermal loads. On this slide, we focus on the Nortec StatePoint system and its unique hydronic distribution approach. The StatePoint liquid cooling, or SPLC, was co-developed with Facebook, now Meta, and features a patented microporous hydrophobic membrane. This membrane allows evaporation for cooling without cross-contaminating water and air, which is critical for maintaining system integrity. The cold water produced serves multiple applications including fan walls, CRAH units, hot aisle cooling, RDHX, and chip-level cooling interfaces. The system integrates both supply water temperature control and distribution pumping, using PICV terminals and remote differential pressure control to ensure flow independence, even as operating modes change. Protecting the warm return temperature is essential here, since uncontrolled bypass flow can directly reduce the temperature differential we rely on for effective cooling. Nortec and Meta define the equipment and operating principles, while Danfoss provides the hydronic distribution and control baseline for this advanced data center MVAC system. On this slide, we focus on the operating modes and control objectives of the StatePoint liquid cooling system, or SPLC. There are three primary thermal modes to select from based on ambient conditions. First, the economizer or cool mode uses sensible heat exchange when outside temperatures allow the system to meet the cold water target without evaporation. Next is the adiabatic mode, which adds evaporative assistance to further reduce the entering air temperature while carefully controlling the water supply set point. Finally, the superevaporative mode employs a membrane-based process to provide additional cooling when ambient conditions demand it. Throughout all transitions between modes, it's critical to maintain stable hydronic flow by ramping fans, water treatment, and mode devices gradually, while keeping pump differential pressure control active and setting alarms for any deviations in temperature or flow. Importantly, control separation ensures that ambient logic governs mode selection, while terminal demand and differential pressure indexes determine the distribution pump speed. This disciplined approach helps achieve efficient and stable cooling performance in varying environmental conditions. This slide covers the StatePoint SPLC mixed-load network, which features one plant with 3 distinct control layers. First, the production layer focuses on selecting the achievable chilled water temperature, operating in ambient mode while targeting the appropriate supply temperature for efficiency. Second, distribution pumps maintain the remote differential pressure of the system, using N+1 variable speed drive pump staging to meet demand reliably. Finally, each terminal branch, whether it's the CRAH, FWU, or CDU, uses electronic pressure-independent control valves to meter and control only the flow required by its specific load, ensuring precise and efficient cooling. The system combines advanced technologies like the SPX membrane exchanger and remote delta P transmitters to optimize hydraulic independence and maintain stable operation. By integrating these 3 control layers, the network achieves both energy efficiency and reliable thermal performance across the entire distribution system. Here we have a worked example of a single network serving multiple terminals, specifically 6 CRAHs for FWUs and 1 CDU. The key focus here is comparing mixed terminal delta T values with a common 32 to 45 degrees Celsius network temperature. Looking at option A, we maintain individual terminal delta T values, which results in a calculated total flow of 57.7 liters per second and a mixed return temperature of 42.27 degrees Celsius. Notice that the flow is 27% higher than the common 13 Kelvin design flow, primarily because the low delta T branches for the CRAH and FW units increase distribution flow. Under option B, we validate each coil assuming a fixed 32 to 45 degree delta T across the board. This leads to a lower total flow of 45.57 liters per second, with a return close to 45 degrees Celsius. This option reduces pump input power, as we see from the index head and pump input calculations, resulting in a pump input of 15.55 kilowatts once flow and head are plotted on the certified curve. The design decision hinges on validating the CRAH and FW coil and airside duties at the 13 Kelvin delta T. If not validated, temperature zoning with controlled heat exchangers and pump loops becomes necessary. The most important takeaway is that a common supply temperature alone doesn't guarantee a common return temperature. Each branch, mixed return, and the governing index circuit must be carefully calculated to optimize flow, temperature, and pump duty. Here we are focusing on the SPLC sequence, which stands for StatePoint liquid cooling, an important process in maintaining stable hydronic distribution in data center cooling systems. The goal of this sequence is to manage mode changes without causing flow shock, ensuring the system stays stable even as the heat rejection process adjusts. The process begins with validating the state by confirming ambient sensors, water inventory and quality, terminal availability, and ensuring the minimum distribution path is clear. Next, we prepare the mode by enabling necessary fans, treatment, and process devices, making sure everything is operational before adjusting the water temperature target. Then we ramp the set point by carefully moving the cold supply temperature at a controlled, validated rate while maintaining remote differential pressure control and terminal PICV authority. After that, we verify the load by comparing flow times delta T with the useful load and monitoring return temperature and valve positions through the transition. If at any point there is sensor disagreement, loss of production capacity, or instability in temperature, the system will abort or fall back, returning to a tested safe mode and triggering an alarm to alert operators. Finally, functional testing involves trending key parameters like ambient state, active mode, supply set point and actual temperature, return temperature, flow, differential pressure, pump speed, and terminal positions to ensure everything runs smoothly. Here, we focus on the construction, commissioning, and operation and maintenance of the StatePoint liquid cooling system, or SPLC, within the Hydronic Distribution and Air Liquid Cooling framework. It's crucial to treat the process equipment and hydronic distribution as a single, tested operating system to ensure reliability and efficiency. During construction and pre-start phases, we emphasize disciplined procedures, followed by commissioning to prove system performance, and establishing an O&M baseline for ongoing operations. Regarding the water path, key components like cleanable headers, strainers, drains, vents, and valve access need to be properly managed, including supervised bypasses to control flow. Accurate design flow and pressure drop indexes at each operational mode are vital, as well as monitoring clean strainer pressure drops, branch flow, and valve positions. For temperature control, matched sensors with correct immersion and insulation are essential. We track supply set points, return temperature differentials, and sensor agreement, all within mode-specific supply and return temperature envelopes. Mode control involves verifying ambient sensors and process devices point-to-point, managing transitions between economizer, adiabatic, and super-evaporative modes, plus monitoring transition times and normal control outputs. In terms of failure management, we document safe states and electrical or control dependencies, monitor faults in pumps, sensors, controllers, and communication, and have procedures for timed recovery and approved fallback modes. Maintenance practices include detailed isolation and access plans, ensuring availability of consumables and spares, retesting for leaks, flow, and temperature after maintenance, and maintaining configuration-controlled settings and trend templates. The essential O&M rule to remember is that a change in StatePoint mode should modify production energy and water temperature state, but must never disrupt terminal flow independence. This ensures stable and efficient operation across all modes. On this slide, we're looking at how an integrated campus cooling system keeps things stable by separating thermal production from hydraulic control. The key idea here is that thermal producers, distribution pumps, and terminal valves all communicate their declared capacity and operational state, but without letting one control loop override another. This balance ensures that the campus cooling remains stable and efficient. We have two essential contracts working together. First, the thermal contract, which declares achievable supply temperatures, available capacity, and how to safely transition between modes. Then, the hydraulic contract, which defines remote differential pressure bounds, the authority of terminal valves, pump availability, and recovery times. By maintaining separate contracts for temperature, capacity, pressure, and terminal flow, with coordinated timestamps and modes, this system can verify bounded transfer and recovery. That means it can reliably handle changes without disrupting cooling performance. In sum, this approach allows the chiller plant, distribution pumps, and terminal units like CRAH and FW to work in harmony through a supervisory coordination strategy that carefully manages demands based on actual conditions, keeping the entire system stable and responsive. On this slide, we focus on the importance of instrumentation and data recording in hydronic distribution systems within Data Center MVAC setups. Every controlled hydraulic outcome requires a measured variable, a limit, and a retained record to ensure accurate monitoring and control. For example, supply and return temperature measurements allow us to calculate delta T and maintain heat balance, which is crucial to protecting the equipment envelope. Flow meters and PICV flow sensors verify that equipment meets minimum and terminal design flow requirements, helping detect issues like overflow, restrictions, or load imbalances. Remote differential pressure sensors control pump head at the index circuit and are essential for sensor calibration and detecting set point drift. Monitoring pump speed and power verifies VSD responses and system redundancy, while valve command feedback helps confirm control states and detect problems like stuck valves or bypass leakage. Additionally, measuring filter pressure differentials allows us to quantify resistance and plan predictive maintenance before significant flow loss occurs. To tie it all together, we standardize trends by using common timestamps with 1 to 5 second intervals for transient tests and 1 to 5 minute intervals for long-term efficiency baselines. This comprehensive instrumentation strategy supports commissioning tests, operational use, and ongoing system health. In this module on hydronic distribution and air and liquid cooling for data center MVAC systems, we emphasize a critical principle. The module only closes when design intent, installed reality, and operating evidence all align perfectly. This means every phase must demonstrate actual, verifiable outcomes, not just documentation. Consultants are responsible for delivering detailed schedules, topology rationales, equipment selections, sequences, and measurable acceptance criteria. Contractors provide coordinated shop drawings, approved equipment submittals, cleaning records, and calibrated instruments to ensure proper installation. Finally, the operation and maintenance team must establish approved set points, baselines, failure response procedures, diagnostic tools, and rigorous configuration control. This role-based approach, combined with strict readiness gates, guarantees that no phase advances without confirmed real-world validation of every system component and function. This thorough process ensures reliability and performance from design through operation. In advanced hydronics, the goal is to maintain useful heat transfer through every operating state. We start by focusing on flow, which we calculate from the useful duty and declared temperature difference, ensuring each branch is capped with the correct PICV family. Next is pressure control. We build a complete index circuit and reset the variable speed drive head based on the critical point to optimize system performance. We also manage boundaries by separating incompatible temperature, chemistry, and pressure domains through controlled heat exchanger interfaces. The sequence of operation is crucial, coordinating valves, pumps, flow-proof, equipment enablement, staging, and safe fallback procedures. Finally, proof of performance comes during commissioning, using synchronized data on flow, temperature, differential pressure, valve position, speed, and timed failure trends. The final standard here is key. The best system isn't the one with the highest pump head, but the one that proves every load receives the required flow at the lowest stable head. This approach ensures both efficiency and reliability in data center cooling. On this slide, we cover important abbreviations and references for Module 06, which focuses on hydronic distribution and both air and liquid cooling in data center MVAC systems. SPLC stands for StatePoint Liquid Cooling, and CDU means Coolant Distribution Unit. These terms are foundational as we discuss the technical baseline and equipment specifics throughout the module. We've based our technical reference on the Danfoss Hydronic Applications Guide, which details key topics like terminal variable flow, chillers, and energy analysis, ensuring our information is solid and industry approved. Additionally, official equipment visuals from manufacturers like Vertiv, Nortec, and Meta Engineering give you a clear understanding of the products we discuss. Calculations in the module use standard water properties for heat capacity and density, but remember that final system design must rely on approved OEM data. Lastly, our approach keeps manufacturer data distinct from project assumptions to maintain traceability and help engineers confidently apply these methods without confusion. On this slide, we're looking at the standards hierarchy, which prioritizes outcomes first, followed by project-specific details. The key idea is to use resilient standards to define the desired performance outcomes, while relying on the owner, OEM, and site testing to determine precise timing. For example, the uptime tier focuses on topology-independent maintainability and fault tolerance, helping us map pump capacity, distribution paths, and shared dependencies. ANSI/TIA 942C sets the framework for rated infrastructure topology and data center cooling and power scope, guiding us to evaluate redundant capacity and independent distribution paths. Then, ASHRAE provides standards for energy, thermal management, measurement, and control sequences, which helps us define efficient pump duty cycles, sensor placement, and system verification. ANSI/HI covers operating regions, NPSH requirements, condition monitoring, and acceptance tests, enabling us to select and test pumps effectively as hydraulic machines. Finally, the owner and OEM collaborate to set project load expectations, response class, equipment limits, and acceptance envelopes, ensuring all timing and system events are declared and verified with synchronized evidence. This layered approach ensures that every aspect, from design to testing, aligns with the ultimate goal of resilience and efficiency in data center MVAC systems. On this slide, we cover several important abbreviations and key Hydraulic Institute standards relevant to pumping and hydronic distribution systems. First, to address the abbreviations. OEM stands for Original Equipment Manufacturer, AHF means Active Harmonic Filter, and VSD refers to Variable Speed Drive. Now, focusing on the Hydraulic Institute Standards map, it's crucial to use the current contractually adopted editions, as the public catalog helps establish the scope for each standard. These standards guide us through essential topics like NPSH margin, operating region, vibration, condition monitoring, rotodynamic testing, and intake design. For example, ANSI/HI 9.6.1 defines system NPSHA, pump NPSCHAR, and the project or OEM margin method, which is fundamental for ensuring proper pump operation without cavitation. Another key standard, ANSI/HI 9.6.3, helps control normal duty inside the approved preferred operating region to maximize efficiency and equipment life. We also have ANSI/HI 9.6.4 for vibration, specifying measurement locations and acceptance criteria depending on pump type. Condition monitoring is covered under ANSI/HI 9.6.5, which guides building trendable mechanical and hydraulic indicators for maintenance and troubleshooting. Rotodynamic testing, under ANSI/HI 14.6, defines test grade, tolerance, and duty point acceptance, critical for validating pump performance. Finally, intake design standards like ANSI/HI 9.8 ensure control of vortices, submergence, and approach flow in open intakes, which helps maintain optimal pump operation and prevent damage. Understanding and applying these standards is essential for designing and operating efficient, reliable data center MVAC systems. On this slide, we outline the critical distinctions between owner criteria and standard mandates within pumping and hydronic distribution systems. First, it's important to recognize that standards focus on general outcomes such as maintainability, fault tolerance, and an energy or measurement framework. These create a baseline for pump operation and testing practices. In contrast, owner targets are much more specific and performance-driven, including metrics like seconds to flow or differential pressure recovery, dual source or bypass philosophies, and expectations around total harmonic distortion, event trends, and alarms. Meanwhile, the OEM limits set essential operational boundaries such as minimum speed and flow, restart and ramp limits, and the motor and VSD's thermal and protection envelopes. All of these elements come together to define acceptance proof, which requires representative load and utility events, synchronized hydraulic and electrical data, and strict adherence to safety, surge, and equipment limits. Finally, it's crucial to note that a seconds target is only valid if the initial state, event, load, measurement point, and pass condition are all clearly defined. This approach ensures clarity and precision in meeting both standard and owner-specific performance requirements. On this slide, we compare chilled water pumping with condenser water pumping in data center MVAC systems. The hydraulic method for both is similar, but the differences come in key factors like load, water quality, intake, and control constraints. Chilled water primarily delivers cooling to terminal units or chiller evaporator loads, while condenser water is responsible for rejecting heat from chillers to cooling towers or evaporative systems. Control targets also differ. Chilled water relies on remote differential pressure and load valve demand, whereas condenser water focuses on chiller condenser flow, tower cell staging, and heat rejection performance. Regarding static head, chilled water systems are usually closed loop, so elevation cancels out after filling, but condenser water systems are often open, including actual static lift. Water quality considerations vary too. Chilled water loops require corrosion, air, and chemical treatment control in a closed system, while condenser water systems are open and need management of solids, biological growth, scaling, and strainer loading. For NPSH or intake conditions, chilled water systems depend on pressurization and proper suction pipe design, whereas condenser water systems must manage basin level, submergence, and vortex control. Finally, failure impact highlights are important. Failure in chilled water pumps poses an immediate risk to distribution flow and thermal conditions. In condenser water systems, loss here can cause chiller trips and affect the chilled water system's operation, creating a cascading failure risk. Understanding these differences is critical for effective system design and operation. Let's talk about how to select the right pump family based on several key factors. Once we understand the duty requirements, operating envelope, service access, and failure strategy, we choose the mechanical form that best fits these needs. For example, the end suction pump is simple, common, and easy to service, making it suitable for smaller chilled water or condenser water duties, often found in packaged skids. However, we need to consider base alignment, footprint, pipe loads, and seal access here. The vertical inline pump offers a compact footprint and makes inline piping straightforward, which is ideal for plant rooms with limited floor space. Just be mindful of motor removal clearance, pipe support, and the local environment when using these pumps. Horizontal split case pumps deliver high flow, good efficiency, and easy service access, fitting well with large chilled or condenser water headers and central plants. but installation requires careful attention to base grout and alignment, coupling, and suction conditions. Vertical turbine pumps are great for wet wells and static lift applications, like open cooling water basins or remote water sources, though issues like submergence, column alignment, and intake vortices need to be managed. Lastly, twin-head inline pumps provide packaged two-pump redundancy in a compact footprint, perfect for zonal or plant groups. Watch out for common casing or header dependencies and ensure service clearance is adequate. Each pump family has its value and specific considerations, so it's essential to match the pump type to the application thoughtfully. On this slide, we focus on the application selection matrix, which is essential for choosing the right pumping equipment in a data center MVAC system. Instead of relying on brand names or form factor preferences, we use a weighted decision approach based on several key criteria. First, hydraulic fit asks whether all duty and staging points fall within the approved curve envelope, backed by certified head flow, efficiency, power, and NPSH curves. Next, resilience considers what single event could disrupt multiple pumps or the entire flow path, analyzed through a failure domain and maintenance lineup matrix. Efficiency is critical too. We evaluate which pump count and speed minimize energy consumption from wire to water over the entire load profile, using detailed pump, motor, and variable speed drive efficiency maps. Serviceability examines if one pump train can be isolated and serviced while others continue running, looking closely at layout, valves, clearances, and spares plans. Environment also plays a role, ensuring motors and drives can handle local conditions like temperature, humidity, altitude, and contamination based on D rating and HVAC data. Finally, integration checks if local controls can maintain operation through network or plant controller failures by reviewing input-output lists, control sequences, protocols, and failure tests. All these elements together ensure we select the most reliable and efficient pumping solution for the system's needs. On this slide, we're focusing on selecting the right pump configurations for variable flow hydronic systems. The key is to start by choosing the correct hydraulic arrangement, which sets the foundation for coordinating the pump, variable speed drive or VSD, sensors, and considerations for isolation and maintainability. We look at 5 common configurations. First, the single inline pump is ideal for a dedicated equipment branch or small zone, operating at one compact variable speed duty point. Next, the duty/standby pair involves one running pump with an automatic standby, best suited for critical branches that need N+1 redundancy, with special attention to failure transfer and valve integrity. Then, the twin-head assembly combines 2 pump elements in a compact body, perfect where space is limited, but requires focus on common body isolation and single failure assessment. In larger systems, we see parallel pump banks, which consist of multiple pumps sharing system flow, typical for large central distribution plants, emphasizing stable staging and managing flow curves. Lastly, primary/secondary pump sets separate production and distribution duties, essential for plants needing stable chiller flow, where we must understand decoupler behavior and remote differential pressure control on the secondary side. This structured approach ensures each component works together efficiently for optimal system performance. This module focuses on pumping and hydronic distribution, highlighting that a single variable speed drive pump is only complete when the entire hydraulic train is provable. To achieve this, it's essential to use one inline pump where the load can tolerate loss of the train, isolating, measuring, and protecting both sides to verify the selected operating point during service. We start with 3 key areas: suction quality and NPSH, the pump and VSD operating envelope, and discharge protection alongside duty proof. Maintaining suction integrity means keeping the suction continuously flooded and ventable, avoiding unproven high points, and confirming that net positive suction head available exceeds net positive suction head required plus project margin under worst conditions. Protection and measurement involve pressure transmitters on suction and discharge to establish differential head and a magnetic flow meter to prove true flow. The non-return valve prevents backflow and reverse rotation, while downstream isolation allows maintenance without shutting down the system. When applying a single train, ensure loss is tolerable or that another system path supports the load, and define minimum flow, maximum runout, and operating limits from the certified pump curve. Installation details like straight pipe runs, reducers, and supports should follow manufacturer specifications, not generic sketches. Control and protection rely on the VSD speed following approved pressure or flow loops, with minimum and maximum speed boundaries and validated sensor loss fallback. Interlocks monitor valve positions, suction pressure, pump readiness, and flow, with alarms for abnormal pressure differential, vibration, temperature, and power consumption. Importantly, avoid throttling the discharge isolation valve for routine control. Use the VSD and system control valves instead. Commissioning evidence requires venting and filling, proving valve travel and NRV direction, then starting at minimum speed while observing suction stability. Record all relevant data: flow, pressures, speed, current, power, vibration, and temperatures, and plot the operating point on the certified curve to verify head, efficiency, NPSH margin, and motor/VSD loading. In summary, acceptance involves confirming valve proof, suction stability, controlled start and ramp, meeting flow and head requirements, curve compliance, and successful alarms and fallback tests to ensure a fully provable and reliable pumping system. In this module, we're focusing on duty and standby redundancy in pumping and hydronic distribution systems. This redundancy requires two complete branches, not just two pump elements, to ensure reliability. While the headers can be common, each train must have independent isolation valves, check valves, drives, power paths, and status and fault containment systems. This allows the standby pump to be credited as fully available. The system features two trains. Train A serves as the duty or lead pump, while Train B operates as the standby or lag pump. Both trains have their own branch isolation valves, strainers, suction and discharge pressure transmitters, variable speed drives, and non-return valves. Power and control for each train are supplied independently, including their respective VSDs, handoff auto switches, and status or fault monitoring. A central aspect is the common suction and discharge headers, which remain shared in the system, but maintenance and valve accessibility must be carefully managed in the resilience model. Redundancy is only credited when either branch can deliver the full duty independently, after the other branch is isolated or under maintenance. In operation, the lead pump carries the full designed load, while the standby pump is ready and periodically exercised under a rotation schedule. The standby starts automatically upon failure of the lead pump, loss of run proof, low flow, or a sustained differential pressure deficit, with delay logic to avoid false transfers. After transfer, the failed train must be isolated against reverse flow, and the healthy train should stabilize without hunting. A worked acceptance scenario illustrates this concept. With two pumps, each capable of 95 liters per second at 28 meters head, one pump runs while the other remains fully available. In the event the lead pump's VSD trips, the standby pump starts, the non-return valve on the failed side closes, total flow recovers, and the pressure index returns within approved levels. Finally, redundancy proof involves independent isolation, non-return valves, VSDs, power supplies, and status monitoring, all orchestrated to trip the lead train, transfer automatically, and maintain stable flow and pressure throughout the event. This ensures system resilience and reliability in critical applications like data center MVAC systems. This slide covers the critical aspects of an N+1 pump gallery designed for pumping and hydronic distribution. An N+1 configuration means we have one more pump installed than the required duty to ensure reliability and redundancy. Here, 3 parallel pump trains are used. 2 pumps handle duty, and the third serves as a standby. It's important to understand that parallel pumps add flow at a common head, and the staging supervisor carefully selects pump combinations to meet remote pressure and total flow demands without pushing any pump beyond its certified operating limits. Flow doesn't simply double as we add pumps. System head increases with flow, and factors like unequal resistance or check valve behavior can cause poor load sharing. To optimize efficiency, staging decisions rely on remote differential pressure, total flow, and pump power rather than just variable speed drive percentages. At intermediate loads, the system compares running one faster pump versus multiple slower pumps and picks the combo with the lowest electrical input. We also use staging controls like minimum run times and timers to avoid frequent cycling during fluctuating demand. The N+1 setup is failure-proof by design. 2 pumps must meet the full duty while one is offline, and the standby pump is rotated, not sitting idle permanently. Testing involves tripping each pump in turn and verifying automatic transfer, stable operation, and no overload. Continuous monitoring of flow, head, speed, and power helps detect imbalances, fouling, or efficiency losses. In summary, this module highlights the practical staging and acceptance evidence necessary to ensure reliable, efficient, and resilient pump system operation in a data center mechanical ventilation application. On this slide, we're looking at the integrated pump room system, which should be treated as one complete hydraulic, electrical, controls, and maintenance system. Starting with the hydraulic train, it includes isolation and straining, the pump combined with a check valve, and monitoring header pressure and flow for evidence of performance. Moving to the electrical train, it involves an independent power source with protection, a variable speed drive that has a bypass policy, and motor protection against thermal and earth faults. The controls train focuses on critical parameters like remote differential pressure transmitters for critical loads, local high-pressure limits, and fallback options for speed, valve, and sensor controls. Finally, the maintenance train ensures safe access and lifting, proper drainage and venting with test points, and a return-to-service functional proof. Remember, the system is only accepted when the entire train performs effectively across design conditions, part load operations, failure scenarios, and recovery states. On this slide, we're focusing on the key considerations for installing an outdoor variable speed pump. First, let's clarify a few abbreviations. OEM stands for Original Equipment Manufacturer, AHF means Active Harmonic Filter, and VSD is Variable Speed Drive. When it comes to environmental protection, it's crucial to strike a balance between preserving cooling efficiency, maintaining sensing accuracy, ensuring serviceability, and enabling safe fault response. Starting with the enclosure, always verify the ingress rating to prevent unwanted contamination. Control solar gain and condensation carefully, and maintain proper VSD cooling airflow to keep the system operating reliably. Turning to hydraulics, protecting the pump against freezing or stagnation is essential. Make sure to route drains and vents correctly, and support pipe loads independently to avoid stress on the connections. For instrumentation, use devices suitable for the weather conditions, shield impulse lines from damage, and provide accessible calibration points to simplify maintenance. Finally, in terms of operations, provide local isolation capabilities, test both remote and local controls regularly, and record the seasonal operating envelope to understand how performance fluctuates over time. Remember, placing the pump outdoors changes the environmental challenges, but does not relax the hydraulic acceptance requirements. So each of these steps is vital for a reliable and efficient system. On this slide, we focus on the critical design criteria for pumping and hydronic distribution in data center MVAC systems. First, it's essential to declare the design basis before starting any calculations. This means we need to consider all operating conditions including normal, maintenance, and faulted states. Thermally, we look at peak and diversified loads, the chilled water supply and return temperatures, as well as the maximum transient envelope to ensure the system can handle variations. From a hydraulic perspective, design flow and index path are key, along with static and friction head, plus ensuring adequate net positive suction head and minimum flow to avoid issues. Resilience is another major factor, requiring us to plan for residual capacity, independent flow paths, and incorporate thermal buffers and recovery classes to maintain system stability. Electrically, we must account for voltage and fault levels, proper power path separation, and coordination between harmonics and motors for smooth operation. Environmental considerations cover temperature, humidity, altitude, potential water or chemical exposure, and protection against ingress and corrosion. Finally, evidence of effective design includes instrument accuracy, detailed trend and timestamp resolution, and strict factory and site acceptance test limits to verify performance. All these elements come together to create a robust, reliable hydronic pumping system. On this slide, we're focusing on the sizing inputs and verification route for pumping and hydronic distribution in data center MVAC systems. Each input requires a designated owner, a clear design value, an understanding of uncertainty, and a defined commissioning method. For example, when evaluating load schedules, we consider mechanical and IT load models, along with heat balance and operational trends, to avoid common risks like coincident peak or diversity errors. Temperature difference must be verified by calibrated supply and return sensors to detect issues such as low delta T syndrome. Pressure loss data, which includes pipes, valves, strainers, and coils, needs to be assessed carefully, considering hidden fittings or fouling that can affect performance. Pump curves and certified OEM selections are critical to ensure the system operates within its intended parameters, supported by factory or site performance tests. Efficiency metrics such as pump, motor, and variable speed drive maps help us compare component efficiency against wire-to-water efficiency, allowing us to pinpoint any mismatches in trim, speed, or fluid. Finally, response time is validated against the owner project criteria through synchronized integrated tests to confirm that the initial state is correctly declared and the system functions as intended. On this slide, we cover key abbreviations and essential formulas used in pumping and hydronic distribution systems within Data Center MVAC systems. First, it's important to know that OEM stands for Original Equipment Manufacturer, AHF is Active Harmonic Filter, and VSD refers to Variable Speed Drive. We use consistent SI units throughout, recording fluid properties and efficiencies at the declared point to ensure accuracy and comparability. The formulas here help engineers convert thermal flow to volumetric flow with Q equals P thermal divided by density, specific heat, and temperature difference. Hydraulic power is calculated as density times gravity times flow rate and head, representing the power transferred to the fluid. To estimate electrical input, we take hydraulic power and divide it by the efficiencies of the pump, motor, and VSD. The system curve formula combines static head and friction loss, and the affinity laws show how flow, head, and power scale with speed changes. Lastly, the NPSH margin formula helps screen for cavitation risk by comparing available and required net positive suction head. Understanding these concepts is crucial for accurate system design and performance evaluation. Here we have a worked example for calculating chilled water design flow based on an illustrative 4.0 megawatt useful cooling load. The key inputs include the thermal duty of 4,000 kilowatts, water density at 1,000 kilograms per cubic meter, specific heat capacity of 4.186 kilojoules per kilogram per Kelvin, and a temperature differential of 10 Kelvin. Using these values, the flow rate Q is calculated as 4,000 divided by the product of 4.186 and 10, resulting in approximately 95.6 liters per second. When the temperature difference halves to 5 Kelvin, the flow doubles to 191.1 liters per second. This doubling of flow with a halving of the temperature difference is crucial because it significantly affects the system and pump operating points. This means the head, efficiency, staging, and overall plant capacity must be recalculated to ensure optimal performance under the low delta T condition. Understanding this relationship helps us design more efficient hydronic distribution systems for data center MVAC applications. On this slide, we're focusing on the condenser water design flow calculation, which is a crucial part of pump and hydronic distribution systems in data center MVAC setups. First, it's important to understand that the condenser water flow is based on the total heat rejection from the chiller, not just the evaporator cooling load. For our example, we have an evaporator duty of 4,000 kilowatts, chiller input of 700 kilowatts, resulting in a heat rejection of 4,700 kilowatts. Using the condenser water temperature range, or delta T, of 5.5 Kelvin, we calculate the condenser water flow rate by dividing the heat rejection by the product of water's specific heat and the temperature difference. This gives us a flow of 204.1 liters per second. It's essential to include factors like the actual chiller operating point, any fouling allowances on the condenser, and the tower cell strategy when finalizing this calculation. Finally, remember that this flow rate should be checked again under both design and off-design ambient conditions to ensure system reliability and efficiency. On this slide, we focus on the calculation of the circuit head for the data center MVAC system. The key idea is to add losses along the single worst required path, and importantly, to retain an explicit margin rather than relying on hidden oversizing. We start with declared inputs, which include the lengths for the supply header at 4.2 meters, index branch pipe at 5.8 meters, coil or heat exchanger at 8.0 meters, control valve at 4.0 meters, and return header at 3.5 meters. We then add a 10% allowance to cover any additional minor losses. Adding these values, we get a subtotal of 25.5 meters, and with the 10% margin, the total selection head comes to 28.05 meters. The final selection is made for a flow rate of 95.6 liters per second at 28.1 meters head. It's crucial to verify the pump operating range, net positive suction head, and minimum flow after selection. Remember, we do not sum every branch loss but focus on the governing index circuit, then confirm that other branches can balance accordingly. Here we have key abbreviations to keep in mind. OEM stands for Original Equipment Manufacturer, AHF is Active Harmonic Filter, and VSD means Variable Speed Drive. This worked example focuses on calculating pump power and wire-to-water efficiency using specific measured and declared inputs. We first determine the useful hydraulic power with the formula P equals density times gravity times flow rate times head, which gives us 26.4 kilowatts. Then, accounting for the efficiencies of the pump, motor, and VSD, we calculate the true input power at 35 kilowatts. The resulting wire-to-water efficiency is 75.4%, reflecting how effectively electrical power is converted into hydraulic power. It's crucial for acceptance testing to ensure alignment of flow, pressure, speed, and true power measurements over time while considering measurement uncertainties. On this slide, we focus on how a system curve predicts the required head at any given flow, and how the pump curve then determines the actual duty point. In a filled closed-loop system, the system head loss due to dynamic friction is represented by HSYS equals K times Q squared, where Q is the flow rate and K is the system resistance coefficient. Notably, we do not add building elevation losses once the loop is filled and pressurized. The actual operating point is found at the intersection of the pump curve and the system curve, which reflects the real flow and head the pump delivers. For example, at the reference duty point, with a flow of 344 cubic meters per hour and a head of 28.1 meters, the system resistance coefficient K can be calculated, allowing us to predict the head at other flow rates. This prediction is crucial because system head varies with the square of the flow, meaning that at 70% flow, the head is only about 49% of the reference, not 70%. Understanding this relationship helps identify issues in the field. If the measured head is higher than predicted, it may indicate added resistance from fouling or blockages. Conversely, a lower head could suggest bypass flow or sensor errors. By continuously comparing operating points to the system curve and the pump's performance envelope, we can ensure efficient, reliable operation and diagnose problems early without just increasing the pump speed blindly. The key takeaway is to build a hydraulic baseline from known conditions, use it to predict system behavior, locate the real operating point, and always verify that this point lies within the pump's preferred or allowable operating region. This approach underpins effective pump control, system diagnosis, and maintenance strategies. On this slide, we focus on the essential concept that the operating point exists only where the pump's capability curve intersects with the system's demand curve. Neither curve alone determines the duty. It's the intersection of these two that sets the sustained flow and head. For a vertical inline centrifugal pump with a variable speed drive, our validated design duty here is a flow of 344 cubic meters per hour at a head of 28.1 meters, which translates to about 95.6 liters per second and roughly 276 kilopascals. The pump operates at approximately 77% efficiency with an input power of 34.2 kilowatts. Calculating the hydraulic power confirms this operating condition. It's important to only accept operating points inside the preferred or allowable operating regions, taking into account minimum flow, net positive suction head, and motor power margins. In practice, when a measured point deviates from the predicted intersection, it signals a need for hydraulic diagnosis before adjusting speed, because higher head at the same flow usually means added resistance, while lower head might suggest leaks or sensor errors. Ultimately, mastering this process means defining both curves clearly, locating their intersection precisely, predicting how changes affect that point, verifying all operational limits, and proving the duty through actual performance trends. This approach ensures reliable, efficient pump operation within the system. On this slide, we're focusing on the pump's H-Q curve and how it defines the pump's operating boundaries. The key idea here is that a valid pump duty stays clear of the shutoff, runout, and unstable regions on the curve to ensure reliable performance. We start with shutoff, which occurs at zero flow and a high head, approximately 42 meters in this example. This is a boundary condition, not a target for operation. Then the duty point where the pump operates normally, in this case at 344 cubic meters per hour and 28.1 meters of head, which translates to about 276 kilopascals of pressure. Finally, runout happens at high flow rates with low head, where efficiency drops and risks increase. The slope of the curve between these points serves as an indicator of stability. We want a sufficiently negative slope to maintain stable operation and control margin. The preferred operating region, or POR, is where continuous duty should occur, while the allowable operating region, AOR, is reserved for limited, OEM-approved conditions. Understanding these curve landmarks helps specify safe and effective pump operation under various speeds and load conditions. In this module, we're focusing on pumping and hydronic distribution with an emphasis on understanding efficiency at the actual duty flow. The key point here is that efficiency must be read at the actual operating flow, not borrowed from the best efficiency point, or BEP. While the BEP identifies the hydraulic optimum with peak efficiency around 84% at 240 cubic meters per hour, the real duty might be different. In this case, 344 cubic meters per hour, with efficiency dropping to about 77%. This difference has important consequences for power calculations. You must use the duty efficiency, not the BEP efficiency, when calculating the input power, because substituting BEP efficiency at other flows can lead to inaccurate power estimates. Beyond efficiency, you also need to check other factors such as the preferred and allowable operating regions, minimum flow limits, NPSH, motor kilowatt rating, vibration, and radial loads to ensure reliability. The takeaway is clear. First locate the BEP, then project the actual duty flow, quantify the penalty from operating off the BEP, and finally use the correct efficiency at the duty for accurate power calculation. This approach helps explain why a pump might meet flow and head requirements, but still operate inefficiently or unreliably, guiding better decisions on pump size and staging. On this slide, we focus on a critical aspect of pump and hydronic distribution systems: motor and variable speed drive sizing. It's essential to size the motor and VSD based on the highest permitted power, not just the design duty point. This means considering every allowed flow, speed, and staging condition to ensure the electrical train never overloads. For example, the illustrated vertical inline centrifugal pump has a duty flow of 344 cubic meters per hour with an input power around 34.2 kilowatts. However, when you scan the full range up to runout at 420 cubic meters per hour, power demand increases to about 38 kilowatts. This difference shows why selecting motor and VSD ratings solely on the design point can lead to overload risks. To calculate this properly, you start by determining the hydraulic power, then apply efficiency to get pump input power. Next, scan the entire allowed operating envelope, considering maximum speed, runout, and potential degraded system resistances. Always coordinate motor, VSD, cable, and protection ratings to cover the worst-case scenarios. Why does this matter in the field? A motor that seems adequate at design conditions might overload when system resistance drops or the pump operates near runout. Thoroughly reviewing the certified operating envelope helps set correct service factors, overload settings, and protection measures. In summary, read the duty power carefully, scan the full permitted flow range, include all efficiency losses, check every operating mode, and select appropriate protection. Make sizing decisions based on the peak allowed power, ensuring reliable and safe performance under all conditions. On this slide, we focus on the critical concept of cavitation margin in pumping systems. The key point is that the cavitation margin is valid only when both NPSH, the net positive suction head available, and NPSH, the net positive suction head required, are evaluated at the same worst-case flow condition. The available suction head comes from how the system is installed, while the required suction head is defined by the pump's performance curve. We must always compare these at a single operating point to ensure accuracy. For example, at a flow rate of 344 cubic meters per hour, the NPSH is approximately 4.3 meters, and the NPSH is about 7.0 meters, giving us a margin of 2.7 meters. It's crucial to use the worst credible suction condition when checking this margin. That means considering factors like the hottest fluid temperature, the lowest fluid level, and any fouling in the suction strainer, since these conditions can reduce NPSHA or increase NPSHR. Remember, meeting the project or OEM specified margin is essential. It's not enough to simply have NPSHA greater than NPSHR. The margin must be verified at every credible duty point, not just the nominal design point, because NPSHR can increase near runout conditions, while NPSHA may decrease due to suction losses. In summary, the procedure is: first, read NPSHR at the common duty flow. Second, calculate the real suction system's NPSHA. Third, find the safety margin. Fourth, stress test the system under worst-case conditions. And finally, accept the system only if it meets the specified margin under those conditions. This approach ensures reliable pump operation and prevents cavitation-related damage in the field. Here's the key principle. One duty flow coordinate must align head, efficiency, power, and NPSH. This means that when selecting a pump, every performance value, head, efficiency, input power, and net positive suction head required, must be read at the same flow rate and speed. Mixing data from different flows or speeds creates inconsistencies and leads to a selection that doesn't physically exist. For example, in this vertical inline centrifugal pump with a variable speed drive, the common duty coordinate is fixed at a flow of 344 cubic meters per hour. At this point, the pump produces a head of 28.1 meters, operates at about 77% efficiency, consumes approximately 34.2 kilowatts of power, and requires an NPSH of roughly 4.3 meters. These values are taken from certified OEM data, ensuring accuracy. It's critical to use one vertical duty coordinate line through every performance curve, head, efficiency, power, and NPSH, and to accept all these readings together as a single, complete duty point. Then, verify essential limits such as operating ranges, motor and VSD compatibility, and NPSH requirements. If any one limit is not met, the whole duty point fails. By following this method, you avoid false selections based on mixed data, ensuring a pump selection that truly matches the system's hydraulic, electrical, and suction demands. The ultimate goal is an internally consistent pump performance that meets all operational requirements at a fixed flow. Here we break down some key terms critical to understanding pump operation. BEP stands for Best Efficiency Point. PUR is the preferred operating region. AOR means Allowable Operating Region, and NPSH refers to Net Positive Suction Head. Reliability largely depends on how often and how far the pump operates away from its best efficiency point. The BEP serves as our main reference for hydraulic efficiency, indicating favorable internal flow and balanced radial loading, though it's not a one-size-fits-all guarantee. The PUR defines the preferred continuous operating band, established using industry and manufacturer data, where we ideally position normal and common staging points. Moving beyond the PUR, the AOR represents a wider but limited region of operation that may cause vibration or wear, so it should only be used for transient or infrequent duty as approved. Ultimately, it's important to specify the required operating envelope across all speeds, impeller sizes, and parallel pump setups to ensure optimal performance. On this slide, we're focusing on important operational limits and controls for pumps, specifically the concepts of shutoff, minimum flow, and runout. First, shutoff refers to the zero-flow head condition, where the pump is running but no water is moving. This can cause rapid heating and internal recirculation, so it's critical to verify that the casing and system pressure limits are not exceeded. Next is the minimum continuous stable flow, which is the lowest flow rate the manufacturer allows for safe operation. Controls and bypass systems need to maintain this flow, since running below it can cause damage, and just reducing speed doesn't remove this requirement. Then we have runout, which occurs at the high flow end of the pump curve. At runout, motor overload and the net positive suction head required, or NPSHR, can increase, so avoiding an uncontrolled low resistance path is key to prevent damage. Overall, these constraints aren't spare capacity, they define safe operating boundaries. For control implications, we need to clamp speeds to stay within minimum and maximum limits, detect any valve or header lineup errors, and stage pumps before entering any adverse operating regions. Understanding and respecting these limits is crucial for reliable and efficient pump operation. In this module, we focus on the process of impeller trimming in vertical inline centrifugal pumps with variable speed drives. Impeller trimming removes excess pump head, but only if the certified trim curve remains acceptable. It's crucial to understand that affinity laws, like head being proportional to the square of the impeller diameter and power to the cube, are useful for initial estimates only. The certified curve from the manufacturer governs the final decisions on efficiency, power input, net positive suction head required, and the allowable operating range. The trim selection workflow involves plotting the required flow and head, selecting the nearest published trim size above the duty, confirming a usable margin, and recording the final impeller diameter. After making a first-pass estimate, it's essential to revalidate all parameters against the OEM published curves to ensure the pump operates efficiently and stably. Excessive trimming can reduce energy consumption by eliminating throttling, but may also cause the pump to operate outside its optimal hydraulic geometry. The key takeaway is to use the OEM data as the final authority, ensuring all specifications align before procurement and commissioning. This structured approach guarantees reliable pump performance in the field while optimizing energy use. On this slide, we're looking at the affinity laws, which are crucial for understanding pump performance in dynamic systems like Data Center MVAC. First, some abbreviations. BP stands for Best Efficiency Point, PUR is the preferred operating region, and NPSH means Net Positive Suction Head. The affinity laws describe how flow, head, and power change with speed for geometrically similar pumps. The first major relationship is that flow changes linearly with speed. When speed doubles, flow doubles. However, this applies to the pump curve only, and the actual system flow is determined by where the pump curve intersects with the system curve, which can shift. Next, head changes with the square of the speed ratio. So if speed doubles, the head increases by a factor of 4. But static head in the system affects this, and can limit how much you can reduce flow effectively. Power, on the other hand, changes with the cube of the speed ratio. Doubling the speed means power increases 8-fold. But actual power consumption also depends on pump, motor, and variable speed drive efficiencies. For NPSH, or net positive suction head required, it's often approximated to change with the square of speed. However, it's best practice to consult OEM data and apply project margin methods across the range for accuracy. Lastly, efficiency doesn't stay perfectly constant as speed changes. Using actual efficiency maps is important for staging and predicting energy use accurately. So, while affinity laws are powerful, they have boundaries, and you need to validate predictions with real system and product data. Here we focus on how affinity laws help us predict the effects of speed changes on pump performance. The key idea is that when you reduce the pump speed, the pump curve shifts accordingly, but the system curve remains fixed as the demand boundary. This causes the operating point to move to a new intersection between these curves. To start, we use the affinity laws, which tell us that flow rate is proportional to speed, head varies with the square of speed, and power changes with the cube of speed. For example, at 80% speed, the new shutoff head is estimated to be about 26.9 meters. However, it's important to remember that these are just first-pass estimates. We must then locate the actual operating point on the original equipment manufacturer's curve to verify parameters such as efficiency, NPSH required, and motor cooling capabilities. Before approving the new speed, confirm the variable speed drive can handle that duty without issues like flow starvation or control instability. In summary, you start with the rated 100% curve, apply the affinity laws to estimate the new curve, find the new duty point where it intersects the system curve, then verify all performance data with certified maps to ensure reliable and efficient operation. In this module, we focus on optimizing pumping and hydronic distribution through remote differential pressure control. The key to saving energy lies in positioning the sensor so it truly spans the critical circuit. Simply relying on plant header pressure can be misleading because it might look healthy, while the farthest terminal is actually starved. Therefore, the pump speed must respond to the hydraulic index that really matters, the one at the critical terminal. We define the critical point by selecting the farthest or highest loss active terminal. The differential pressure transmitter taps should span the entire branch and terminal to capture accurate data. It's essential to validate sensor polarity and taps, and also have a bounded fallback in case the signal is lost. The reset objective here is to maintain the lowest pressure differential that still preserves useful flow and terminal valve authority. Sensor quality is crucial. We must reject frozen, noisy, or isolated pressure inputs and trigger an alarm or use fallback control when the remote DPT is lost. The control response strategy involves three main steps: selecting the real governing terminal circuit, measuring differential pressure across the complete hydraulic path, and resetting pump speed carefully. Trimming slowly when valves are satisfied, but responding quickly to any signs of starvation. Why does this matter in the field? Because controlling based only on the header pressure often causes overpressurization near the pump, but fails to serve remote loads properly. A successful control scheme trends parameters like remote differential pressure, valve position, terminal flow, pump speed, and power consumption together. The system is stable only when the critical terminal retains authority at the lowest stable pressure set point. To summarize what you should take away: first, select the proper index by focusing on the farthest or most hydraulically significant terminal. Second, make sure the differential pressure transmitter taps include the entire terminal and branch losses. Third, reset the set point with a balance of slow trimming and quick response. Fourth, bound the control with limits, sensor validation, and fallback logic. And finally, prove the outcome by trending terminal flow, valve position, remote pressure, pump speed, and power use. Our decision rule is to reset pump speed based on a validated remote differential pressure transmitter reading, always with a bounded fallback. This training aims to help you place the remote sensor correctly, maintain terminal authority, eliminate excess pump head, and ensure safe fallback operation in your data center MVAC system. On this slide, we're focusing on the essential difference between static pressure and operating pump head in a closed-loop system. The key point is that building elevation sets the static pressure, not the pump's operating head. The elevation determines the fill pressure as well as the rating of components, while the pump's job is to overcome only the dynamic losses within the closed circuit. When selecting a pump, it's crucial to trace the entire loop because any elevation gained on the supply side is actually recovered on the return path. This means the pump does not need to add pressure to overcome the building height itself, only the friction losses and other dynamic forces. Here's why this matters. If you mistakenly add building height to the pump head requirement, you end up oversizing the pump, which wastes energy and can cause unstable system control. Instead, use elevation for calculating the fill pressure and component maximum allowable working pressure, but size the pump based solely on dynamic losses. To summarize the process: first, trace the loop and understand where elevation gains and losses occur. Second, sum the dynamic losses from pipes, fittings, and equipment. Third, select the pump based on the dynamic head alone, not static plus dynamic head. And fourth, separately check the static pressure rating to ensure components will withstand fill and top pressures. Following this approach helps avoid oversizing pumps and ensures the system operates efficiently and reliably. As the cooling load falls and terminal PICVs start to close, the total flow in the system decreases, causing the duty point to move left on the system curve. This shift in the active system curve means the pump speed needs to reset accordingly to avoid running at full speed unnecessarily. Two-way PICVs help reduce total flow and adjust the system curve, while a remote differential pressure reset prevents excess head from becoming valve loss and noise. It's important not to hold the pump at 100% speed against closing valves, because this converts excess head into valve pressure drops, leading to acoustic noise and wasted energy. Instead, we preserve the remote differential pressure at lower power by adjusting pump speed. We must also protect intentional minimum flows, coordinating chiller or cooling distribution unit requirements, and carefully measure any bypass flow to ensure accurate system load readings. By monitoring valve positions, branch flow, differential pressure, speed, and power trends, we can verify system performance and make informed decisions. In summary, when PICVs close, the system curve moves left, the pump speed resets to save energy, minimum flow requirements are protected, and careful trend analysis ensures optimal operation without valve throttling or loss of control authority. In this module, we focus on detecting fouling in pumping and hydronic distribution systems by analyzing the system head at equal flow rates. Fouling shows up as a higher required head to maintain the same delivered flow, which means the pump has to work harder. By comparing the head at a given flow against a clean baseline, we can uncover hidden resistance that might otherwise be masked if operators just increase the pump set point. For example, at a reference flow of 344 cubic meters per hour, the system head in a clean condition is 28.1 meters, but when fouled, it rises to approximately 37.9 meters. This increase means the pump consumes more power and might even move outside its preferred operating region, leading to inefficiency or damage. The key is to not just treat the symptom by raising pump speed, but to find the root cause by comparing differential pressures across components like strainers, coils, and heat exchangers. Cleaning or repairing these components before adjusting the pump set point will restore system efficiency and avoid permanent penalties. To summarize the process, first, establish a clean baseline at a known flow. Second, compare the fouled head at the same flow. Third, localize the added loss by measuring component pressure drops. Fourth, quantify the energy penalty caused by the increased head. And finally, correct the issue by cleaning or repairing parts before retuning the pump. This approach ensures you detect fouling early, pinpoint the cause, assess the impact on energy use, and confirm recovery after maintenance, maintaining optimal system performance. Here we focus on series pumping and hydronic distribution, where series pumps add head at one common flow to increase downstream pressure boundaries. Each pump in series handles the same flow rate, so the total head is the sum of the heads of each individual pump. This means the combined pump curve is created by adding their heads together, but while doing this, you must check each pump's casing pressure limit carefully to avoid exceeding design constraints. For example, with a flow of 344 cubic meters per hour, if each pump generates 28.1 meters of head, the combined head is 56.2 meters. This approach is important because it increases system pressure, not flow rate, unlike parallel pumping. Therefore, you must verify the interstage and final discharge pressures against the maximum allowable working pressure of all components to ensure safety. Furthermore, although pumps operate in series, each remains an individual machine, so it's crucial to check their preferred and allowable operating regions, net positive suction head, power requirements, and minimum flow independently. Also, don't assume equal load sharing if pump models or conditions differ. The key takeaway is to hold flow constant, add the heads to form the total head curve, locate the system duty by intersecting this combined curve with the system curve, then verify each pump and every pressure boundary separately to maintain safe and efficient operation. On this slide, we're focusing on pumping and hydronic distribution with an emphasis on identical parallel pump operation. The key concept here is that parallel pumps operate at a common suction and discharge head, and their flows add together to determine the total plant capacity. It's important not to simply double a single pump's duty point when constructing the parallel pump curve. Instead, we sum the flow rates of each branch at the shared header head to create an accurate combined curve. This combined curve intersects with the system curve to define the actual plant duty. However, having a common header does not guarantee equal flow sharing between pumps, so it's crucial to verify each branch individually. We do this by checking for forward flow, confirming that non-return valves are open and functioning, inspecting power consumption in kilowatts, and looking at the preferred and allowable operating regions for each pump. Stable parallel operation requires hydraulic symmetry and proper check valve function, because if one branch is restricted, it may still appear acceptable based on header pressure alone. Therefore, tracking branch flows and power trends will help detect imbalances and ensure each pump shares the load as expected. Balanced identical pumps should show flows roughly equal to half of the total flow. Lastly, in practical terms, the decision rule is to intersect the summed flow curve Q total of H equals 2 times Q single of H with the actual system curve to determine real combined duty, and to verify that all pumps are contributing properly without overload or underperformance. This approach provides a reliable way to design and troubleshoot parallel pumping systems in hydronic applications. In pumping and hydronic distribution systems with unequal parallel pumps, it's crucial that every branch contributes positive flow to ensure safe operation. At the live common header head, each pump must produce forward flow. Otherwise, the weaker branch risks stalling, chattering, or even reversing flow, which can damage equipment. To manage this, we follow the unequal pump rule. At the common header, we calculate each pump's flow at the given head and sum only the positive flows. Protecting each branch with a non-return valve, or NRV, is essential to prevent reverse flow. Before opening any connection, the incoming pump's shutoff head must exceed the live header head to avoid hidden reverse flow conditions. Field practice shows that combined header flow might look acceptable overall, but if one pump isn't contributing, problems arise. So, always match the pump's head before connecting, prove the NRV opens fully, verify positive branch flow, and ensure each pump operates within its preferred or allowable operating region. Don't rely solely on speed commands as proof of flow. The key takeaways are to use the common head to some positive flows, raise the incoming pump head before opening the NRV, confirm forward flow with proof of NRV position and stable flow, verify each pump's operating envelope including NPSH and motor power, and tune load sharing by using compatible pump curves and stable branch controls. Following these steps ensures safe, stable, and efficient operation in systems with unequal parallel pumps. In constant speed pump staging, hysteresis is essential because every time we change the pump count, it creates a sudden step in system head, which can disrupt stability. To manage this, we rely on a reliable sequence that verifies the incoming branch, limits pressure overshoot, and prevents the pump from cycling on and off repeatedly around a single threshold. This means we don't just start a pump on a command. We must confirm the state of the non-return valve, ensure branch flow, and see that the system header recovers properly before proceeding. The staging process involves 3 key steps. First, qualify demand by looking for sustained flow or head requirements, not just momentary spikes. Next, transfer by starting the pump, matching speeds, and proving forward flow. Finally, allow time to settle with a dwell period before making another staging decision. This approach prevents unnecessary wear and pressure swings. Adding stability logic is critical. We use separate thresholds for stage up and stage down, alongside dwell times and hysteresis, to ensure smooth operation. Importantly, every pump count change must result in a stable recovery of system head without hunting or oscillations. By trending variables like differential pressure overshoot, flow, pump count, and valve state, we can prove each step works as intended. Ultimately, this method protects pressure stability, maintains efficiency, and extends equipment life by turning fixed pump count steps into a controlled, stable sequence that responds correctly to real demand in the field. In this module, we focus on the concept of equal speed variable speed drive pumps sharing flow, which occurs only when the branches they serve are hydraulically balanced. The key point here is that while a common speed command generates similar pump curves, actual flow sharing depends heavily on several factors like piping resistance, valve conditions, sensor accuracy, and the condition of the pumps themselves. To ensure proper flow sharing, both pumps operate at the same speed with a target total flow, such as 344 cubic meters per hour, aiming for roughly 172 cubic meters per hour per pump. But equal speeds don't always translate to equal flow, so we need to diagnose any imbalance by comparing flow rates, suction and discharge pressures, and power consumption for each pump. Make sure that branch valves, non-return valves, and strainers are in good health, as any faults here can cause persistent differences in flow or power. Investigating deviations helps identify issues such as valve misposition, fouling, sensor bias, or mechanical degradation. Ultimately, using real branch flow measurements, not just drive frequency, is essential to prove fair and efficient sharing between pumps. On this slide, we're focusing on the critical process of staging unequal speed pumps in hydronic distribution systems. The key point to understand is that an incoming pump must build enough shutoff head to overcome the live header head before its branch valve opens. This ensures the non-return valve can open fully, preventing issues like valve chatter or reverse flow, which can destabilize the system. Before connecting, it's essential to measure the live header differential head accurately and verify the pump's correct rotation. Then, we accelerate the incoming pump to achieve the matched head condition. Only after confirming the pump can provide stable positive flow, and the check valve is open should we release any isolation. This isn't just about sending a start command. It's a dynamic interaction where we continuously monitor speed, pressure differences, valve states, and flow to ensure smooth load sharing. Following these steps prevents unstable operating conditions and ensures both pumps operate within their safe and efficient zones, maintaining overall system stability. Here we focus on optimizing pump selection for a given system duty by comparing 1-, 2-, and 3 pump configurations. The key point is that the best pump count is not automatically the fewest pumps, but rather the option with the lowest compliant total electrical power consumption in kilowatts. We analyze each possibility while applying important constraints like operating regions, redundancy requirements, and motor limits. For example, at a required flow rate of 344 cubic meters per hour, using 3 pumps results in about 33 kilowatts while maintaining reliability with an N+1 redundancy. It's crucial to reject any setups that violate preferred operating ranges, net positive suction head, or motor performance limits. We also incorporate dwell time to avoid rapid cycling for minor energy savings. Ultimately, the goal is to select the configuration that delivers the required flow and head with minimum total wire-to-water energy, while ensuring reliability and stability in operation. On this slide, we're focusing on the important concept of minimum speed constraints for pumps in hydronic distribution systems. The key point is that the lowest permissible speed command is determined by the most restrictive limit from 4 categories: hydraulic, mechanical, motor or variable speed drive, and controls. This ensures safe and efficient pump operation. Starting with hydraulic constraints, the pump speed must be high enough to overcome static head, maintain the minimum required flow for the process, and keep check valves stable to prevent damage or performance issues. From a mechanical perspective, minimum speed helps ensure proper bearing and seal lubrication, avoids harmful internal recirculation which can damage the pump, and maintains stable vibration levels to extend equipment life. Considering motor and VSD constraints, minimum speed protects motor cooling capabilities, respects VSD switching and thermal limits, and keeps operation within torque and current envelopes to avoid electrical faults. Finally, controls impose constraints through sensor range and resolution, valve authority to reliably modulate flow, and ensuring stable PID control with appropriate staging deadbands. Altogether, these factors work in concert to define the safe operating minimum speed, preserving both equipment integrity and system performance. Let's dive into the key concept of affinity laws as they relate to pump power and speed. Pump power decreases roughly with the cube of the speed reduction, which means even a small cut in speed can lead to a significant drop in power consumption. For example, running a pump at 80% speed ideally reduces power use to about 51.2%. However, this is an ideal calculation and real-world savings need to be verified. The affinity laws give us a nonlinear relationship. Flow scales linearly with speed, head with the square of speed, and power with the cube. This is crucial because it shows why variable speed drives can save so much energy. But remember, real systems are more complex. Static head, efficiency changes, and system curve interactions all affect actual performance. It's important to define the speed ratio, scale the flow, head, and power according to the affinity laws, and then always verify these predictions against the OEM's certified pump curves and measured power data. This way, you'll understand the true energy savings and operating point in the field. The key takeaway is that affinity laws provide a first-pass energy prediction, but certified curves and actual measurements must confirm those estimates for accurate system optimization. On this slide, we're focusing on the concept of wire-to-water efficiency, which is crucial because it exposes losses that pump-only efficiency doesn't show. The key idea here is that the useful boundary for measuring efficiency starts at the electrical input to the variable speed drive, or VSD, and ends at the hydraulic power actually delivered to the water, not just at the pump shaft. We use a vertical inline centrifugal pump with a VSD as our physical reference. Each component contributes its own efficiency. The pump sits around 77%, the motor about 95%, and the VSD approximately 98%. When we multiply these together, we get a wire-to-water efficiency of roughly 71.7%. It's important to measure flow, head, and electrical kilowatts simultaneously to ensure accuracy. We calculate hydraulic power using the formula PHYD equals ρ times G times Q times H, which reflects the actual operating point. This method accounts for real-world factors like motor loading, VSD conversion losses, harmonics, and power quality, which all affect the input energy. Ultimately, acceptance testing should compare these coincident measurements under representative loads to verify true system performance. This approach helps distinguish pump efficiency from overall wire-to-water efficiency and ensures every conversion loss is accounted for. This slide focuses on understanding and calculating the annual energy consumption of pumps in hydronic distribution systems by using a load duration approach. The key point here is that annual pump energy is not simply the design power multiplied by 8,760 hours. Instead, we analyze the actual operation over the year by breaking down the load profile into flow duration bins. For each bin, we determine the pump count, speed, and corresponding input power, then multiply by the hours spent in that bin to get energy use. This method enables us to integrate energy consumption across all operating conditions, including standby, bypass, and auxiliary power where applicable. By building coincident flow and head load bins, mapping pump operations accordingly, and summing the input power times hours, we get an accurate evaluation of annual energy in megawatt hours. Why does this matter? Because the energy-optimal pump selection depends on where the plant spends its time, not just on a single design point. This approach highlights the benefits of differential pressure reset, pump count optimization, and minimizing bypass flow. It drives smarter decisions on controls and equipment choices by comparing real-world annual energy use, not just nameplate efficiency. To summarize, start with measured or modeled load bins, assign pump strategies per bin, read actual input power, integrate energy over time including auxiliary loads, and test alternative strategies. This realistic load profile method ensures decision-making based on actual operating cost and system behavior, leading to better energy savings and system performance. On this slide, we focus on the NPSH calculation framework, which is critical for understanding pump performance in hydronic systems. NPSH stands for Net Positive Suction Head Available, and it represents a system property reference to the pump datum under the worst credible operating condition. Several terms affect NPSH, starting with absolute surface pressure, which effectively adds to the available head. This could be from closed-loop pressurization or an open basin atmospheric condition. Next is the static suction head or lift, where a positive level adds to NPSH, but suction lift subtracts from it, depending on the minimum basin or expansion tank level relative to the pump datum. Suction friction is another factor that subtracts from available head, caused by the resistance from pipes, fittings, isolation valves, strainers, and the fouling state of components. Vapor pressure also subtracts from NPSH and increases with the liquid temperature, so the worst fluid temperature and concentration must be considered. Transient effects such as acceleration or water hammer can temporarily reduce suction pressure, which we evaluate through start/stop and transfer analyses. Finally, an uncertainty or margin is included as a project or OEM margin to protect against variations caused by adopted methods, instrument uncertainty, and test conditions. Understanding these components ensures accurate NPSH calculation and reliable pump operation. Here, we walk through a practical example to prove the suction margin at the worst credible state by calculating the net positive suction head available, or NPSH. First, we start with the absolute suction pressure at the pump datum. We convert the gauge suction of plus 85 kilopascals and atmospheric pressure of 101.3 kilopascals into an absolute head, which comes to about 18.99 meters. Next, we subtract the vapor pressure head, which at 40 degrees Celsius is approximately 0.75 meters of water. Then, we account for suction losses from the strainer, pipe, and fittings at maximum flow, totaling 2.4 meters. After these subtractions, we find the NPSH to be 15.84 meters. We then compare this to the certified NPSH required at the duty point, which is 4.3 meters, giving us an impressive margin of 11.54 meters and a safety ratio of 3.68. Importantly, this calculation is done at the worst credible condition, considering the highest liquid temperature, lowest pressurization, dirty suction elements, maximum flow, and elevation differences. Finally, acceptance involves confirming the project or manufacturer's margin criteria, while also checking factors like vibration, noise, and inlet pressure behavior during various operational conditions, such as ramping and loss of pressurization. This method ensures reliable pump operation and safeguards against cavitation risks. Cavitation is a critical issue that can severely damage a pump even before any low-flow alarms become noticeable. It typically occurs due to factors like low suction pressure, high liquid temperature, a blocked suction or vortex, or operating the pump beyond its approved flow range. You might notice evidence of cavitation through a crackling noise, broadband vibration, degradation in head or flow, or unstable suction pressure. The damage caused includes impeller pitting, stress on seals and bearings, loss of performance, and even the risk of sudden failure. To respond effectively, we must protect the thermal load, reduce or stop the affected pump train within operational limits, restore proper suction conditions, and then inspect and re-baseline the system. Understanding and addressing these points is essential for maintaining pump reliability and system performance. On this slide, we focus on best practices for suction piping in pumping systems, which is crucial for maintaining pump performance and reliability. First, stable, uniform inlet flow is essential because it protects the net positive suction head margin and reduces vibration, ensuring more consistent test results. To achieve this, the geometry of the suction path must be short and direct, avoiding close elbows near the pump inlet, and reducers should be oriented properly according to the layout. Next, air control plays a big role. You want to prevent high-point air pockets by installing accessible vents and air separators, and always maintain system pressurization. Regarding components, use full-open isolation valves, cleanable strainers equipped with differential pressure gauges, and pressure taps installed at a defined datum point for accurate monitoring. Finally, proper installation is key. Provide independent pipe support to reduce stress on the pump nozzles, control nozzle loads, and make sure to flush and clean the piping thoroughly before startup. All of these practices together will help optimize pump operation and extend system life. Here we focus on open intake and basin design, which are critical for condenser water and vertical turbine applications. To ensure optimal performance, we need a stable approach flow with uniform velocity, and we must avoid swirl, pre-rotation, or abrupt geometry. Another key factor is submergence, which involves maintaining a minimum operating level, suppressing vortices, and accounting for wave and drawdown effects to keep everything running smoothly. Water quality also plays an important role, so screens, strainers, blowdown treatments, and cleanout access are essential to prevent solids from causing issues. Finally, proof of proper function comes from monitoring level and suction pressure trends, visually inspecting for vortices, and checking vibration and flow across all pump combinations. In this module, we focus on surge risk in pumping and hydronic distribution systems. The key point to understand is that surge risk is governed by velocity change and event time, not just steady-state head alone. Fast trips, sudden valve closures, and check valve slam events generate transient pressure waves. These waves can exceed positive pressure limits or create vacuum conditions leading to column separation. Using Joukowski's equation, delta P equals fluid density multiplied by wave speed and velocity change. For example, with water's density at 998 kilograms per cubic meter, wave speed at 1,200 meters per second, and a velocity change of 1 meter per second, the transient pressure rise can reach approximately 1.20 megapascals. It's important to interpret this as a rapid event upper bound, not the exact final pressure. To manage surge risk effectively, you must screen both positive and negative transients. Evaluate the potential for surge, vacuum, and column separation, and model the entire system including pipes, valves, pump inertia, and surge vessels. This approach helps ensure a comprehensive understanding of system behavior. The process involves defining the event by identifying rapid trips or valve closures and calculating the velocity change. Next, screen the surge magnitude using the Joukowski estimate. Then, model system responses like wave travel and valve behavior to design proper mitigation measures. Why is this important? Because complying with steady-state curves alone doesn't guarantee transient safety. The relationship between event duration and wave travel time determines whether the full pressure rise develops. Use the screening value to flag risk, then validate with detailed transient modeling to size ramp logic, non-slam checks, surge vessels, or relief valves. To summarize, always define the event, screen for surge, interpret your results carefully, check both pressure extremes, and then validate your mitigation strategy using thorough modeling. This structured approach enables you to recognize fast hydraulic events, assess surge magnitude, identify vacuum risks, and specify appropriate transient analysis and mitigation evidence for safe system operation. In managing pump ramp settings for hydronic distribution, it's crucial that the hydraulic response stays within defined limits for safe and efficient operation. The ramp time we set is just a parameter. The real acceptance depends on monitoring remote pressure, flow, overshoot, minimum pressure, and ensuring critical loads ride through smoothly. We start by defining clear response limits, including maximum overshoot, minimum remote differential pressure, and recovery time, and then coordinate these with isolation valves and non-return valves to ensure proper sequencing. During acceleration, we check to prevent overpressure and motor limits from being exceeded, and during deceleration, we watch for issues like starvation, reverse flow, or slam from check valves. Using synchronized trend data covering speed, branch flow, and remote differential pressure, we can verify that the pump ramps properly through start and stop events without causing instability or risk to critical loads. The key takeaway is that by carefully setting and testing these parameters, then validating performance in the field, we can guarantee safe and reliable pump operation that supports continuous critical load performance without interruption. On this slide, we're focusing on the rapid response outcome hierarchy within a data center MVAC system, specifically related to pumping and hydronic distribution. First, it's important to understand a few key abbreviations. BEP stands for Best Efficiency Point, PUR is the preferred operating region, and NPSH means Net Positive Suction Head. These terms are crucial for optimizing pump performance. Now, looking at the rapid response process. A fast motor alone isn't enough if cooling is delayed elsewhere in the system. The sequence starts with detect, where first-out logic quickly identifies an event without unnecessary delays or sensor confusion. Then comes permit, ensuring power, valves, suction, and other permissives are either already valid or quickly completed. Next, during start and transfer, the local controller and variable speed drive manage the source and pump sequence efficiently. The build flow stage safely ramps up flow, opens check valves, and ensures air-free piping to establish proper header flow. Following this, restored differential pressure means the index branch gets the needed pressure, allowing valves to regain control. Finally, protect thermal ensures that the supply temperature and the thermal envelope of the rack and IT equipment stay within project limits, maintaining safe and effective cooling throughout. On this slide, we're looking at key abbreviations and project response classes related to pumping and hydronic distribution in data center MVAC systems. First, let's clarify some important terms. BEP stands for Best Efficiency Point, which is where a pump operates most efficiently. POR means Preferred Operating Region, indicating the optimal range for pump operation. And NPSH is Net Positive Suction Head, critical for preventing pump cavitation. Now, focusing on project response classes, these define how the system handles different operational states to ensure reliability and safety. Class R1, or ride-through, means the pump either keeps running or maintains control power with no loss in useful flow, often supported by dual or UPS power for seamless operation. Class R2, hot standby, describes a pump that's ready and primed to quickly reach near full flow, usually within a project-defined time frame, with features like automatic start and thermal buffering. Class R3, warm standby, refers to a pump that's stopped but can start after some delay, with validated start sequences and thermal management to prevent damage. Finally, Class R4, cold recovery, involves restoring the hydraulic or power source over minutes and isn't credited for immediate thermal continuity, relying instead on recovery plans. Understanding these classes helps us design systems that meet strict uptime and safety requirements by clearly defining how pumps should respond under various conditions. Here we discuss active-active pumping, a strategy where redundant pump capacity runs simultaneously. The key benefit here is there's no start delay for the surviving capacity if one pump fails, ensuring smooth load sharing and immediate indication of system health. However, this approach comes with risks. Both pumps share a common header and control system, so they're vulnerable to the same events, and efficiency can drop at low loads. To manage these risks, controls must ensure equal load sharing, prevent reverse flow, and maintain fault containment with stable rebalancing. Regular testing involves tripping one pump, measuring residual flow and differential pressure, and verifying the surviving pump's ramp-up and overload margin. This careful balance helps maintain reliable and efficient operation. Let's dive into the concept of hot standby pumping, which is crucial for reliable system operation. Hot standby means the pump is already primed, available, and locally permitted, so its recovery time is predictable. This ensures rapid response when needed. Before a pump can enter hot standby, several prerequisites must be met. The valve lineup must be correct, the power source and control power must be healthy, the suction must be primed and vented, and there must be no maintenance inhibit active. When it comes to start logic, the system relies on fast, validated detection to initiate the pump start quickly. The command is automatic and local, following OEM-compliant ramping procedures, and the check valve must open properly. Acceptance criteria focus on performance metrics such as the time to reach operational speed, achieving at least 90% of header flow, reaching the remote differential pressure set point, and maintaining the thermal envelope throughout. Finally, readiness proof involves periodic exercise of the pump, ongoing permissive supervision, monitoring event buffer health, and ensuring no stale override conditions exist. These steps collectively guarantee that the hot standby pump is ready and reliable when called upon. On this slide, we're focusing on cold standby and recovery in data center MVAC systems. Cold standby refers to having the capacity available for recovery, but it doesn't guarantee immediate thermal continuity. There is typically a delay involved due to several factors like source transfer or breaker closure, valve actuation, priming and venting, and waiting for chiller or tower permissives. Cold standby is useful when you have a longer thermal buffer and plan for recovery ahead of time, serving as a non-immediate contingency capacity. However, there are risks such as unproven readiness, dependency on manual operations, and potential problems like air in the system, seized valves, or stale sequences. To mitigate these risks, it's crucial to implement automated exercises, condition monitoring, clearly defined recovery service level agreements, and regular emergency operating procedures and drills. This helps ensure the system is ready when needed and recovery happens smoothly and efficiently. In this module, we focus on N+1 recovery in pumping and hydronic distribution systems, especially how we define and measure resilience. N+1 recovery is considered complete only when remote pressure stabilizes and the cooling system successfully rides through the event. It's important to understand that standby start is just a single event. True resilience is measured from the moment the running pump trips to when hydraulic conditions return to normal at the critical load. We begin by marking the trip time, or trip, then record the minimum differential pressure and the duration of the dip below acceptable limits. We also verify that the standby pump flow starts and that pressure stabilizes to define recovery time accurately. Recovery ends when differential pressure is stable, not simply when the standby pump starts. Hydraulic and thermal evidence must align, so it's crucial to confirm that cooling units like CRAH, FWU, or CDU operate within thermal limits during the transfer. Testing should simulate failures of power, variable speed drives, pumps, and control sources to ensure the system can maintain critical load conditions without interruption. Ultimately, a successful N+1 test proves more than just automatic start functionality. It quantifies how low pressure falls, how long the critical circuit remains affected, when standby flow becomes effective, and whether thermal conditions remain acceptable. Using one synchronized event record as acceptance evidence provides clear, objective validation of system resilience. Here, we're looking at a worked example of thermal buffer calculation within a data center MVAC system. The key idea is that the buffer acts as a bridge between the loss and restoration of useful cooling, helping to maintain system stability. We start with declared inputs. The system water volume is 18 cubic meters, which translates to about 18,000 kilograms of water mass. The allowable temperature rise is set at 2 Kelvin, and the unserved cooling load is 2 megawatts. Using these values, we calculate the stored thermal capacity by multiplying the water mass by the specific heat capacity of water and the allowable temperature rise. This gives us roughly 150,696 kilojoules of stored energy. Dividing this energy by the cooling load of 2,000 kilojoules per second results in an ideal buffer time of about 75 seconds. It's important to note that this 75-second buffer is idealized, not accounting for real-world factors like mixing, distribution, load constraints, and equipment limits. For actual projects, dynamic modeling or validated testing is essential since pipe travel, local volumes, controls, and thermal limits will reduce the effective usable buffer. This understanding helps us design more reliable and efficient thermal energy storage for cooling systems. Here we have a thermal buffer worked example that shows how to convert a buffer vessel volume into usable ride-through seconds. The key idea is that usable ride-through time is not just the tank's volume alone. It depends on the stored sensible energy divided by the coincident load, then adjusted for factors like mixing, dead volume, and control limits. Starting with an 18 cubic meter buffer vessel, we calculate the mass of water as 18,000 kilograms by multiplying volume by density. Next, we determine the usable energy stored using the specific heat capacity of water and a temperature difference of 2 Kelvin, arriving at about 150.7 megajoules. Dividing this energy by the load of 2 megawatts gives us a theoretical ride-through time of 75.3 seconds. However, we then apply an 80% utilization factor for stratification and mixing effectiveness, which reduces the effective ride-through time to around 60 seconds. This means that the system's standby production and distribution must fully recover within 60 seconds, while maintaining temperature within the service level agreement. Proper hydraulic design is crucial to avoid short-circuiting layers in the tank. This includes dedicated charge and discharge paths, low-velocity connections, air removal, isolation valves, and multiple temperature sensors to accurately monitor conditions. Finally, commissioning involves tripping the production source at a declared IT load, then recording temperatures, pump status, and recovery time to validate the usable energy calculations. This thorough approach ensures the system can reliably provide the required ride-through performance during power interruptions. Here we focus on the key capabilities and design intent for the chilled water system in Data Center MVAC. The system must maintain stable remote differential pressure and valve authority from minimum to peak load during normal variable flow conditions. This ensures optimal flow, pressure differential, valve positions, pump speed, and temperature difference trends. In standby pickup mode, the system is designed to restore the required useful flow and differential pressure within the declared response time, with synchronized event records capturing everything from pump trip to thermal stabilization. At minimum flow, protection of both pump and chiller is critical, preventing chronic bypass waste and ensuring all minimum load and staging combinations are tested. Surge control strategies involve careful ramping and check valve actions to keep pressure within safe limits, backed by high-speed pressure monitoring during start, stop, and load transfers. When sensor or network data is lost, the system resorts to local bounded fallback to maintain safe operation, with injected failure tests confirming correct alarms and a stable residual duty. This comprehensive approach aligns with owner design intent and OEM limits for reliable, efficient operation. On this slide, we're focusing on the CHW system's capability relating to power, resilience, and service. It's important to understand that each requirement should be treated as a testable system property rather than just a feature label. For example, power path separation means that if one declared power source is lost, it should remove no more than the permitted capacity. This is verified through a source loss test and updating the single line or fault domain map. Next, control independence is critical. The local loop must continue operating even if the supervisory network fails, which we test through network isolation and post-recovery reconciliation. Fault isolation ensures that a failure in one drive, pump, or component does not propagate through the common bus or control systems, confirmed by injecting faults and checking residual duty performance. We also emphasize the importance of concurrent maintenance. Pumps, variable speed drives, valves, and sensors can be isolated safely while ensuring the system continues to meet duty requirements, demonstrated through an approved maintenance lineup. Finally, return to service means once the cause of a problem is cleared, settings and configurations are verified, standby status is restored, and post-maintenance functional tests confirm the system returns to baseline performance. Each of these points ensures the system remains reliable, resilient, and serviceable under all conditions. Here we focus on the condenser water system's capability, particularly its hydraulic and heat rejection interface. The key point is that the condenser water pump must operate in harmony with the chiller and cooling tower to ensure the entire system functions optimally. This involves designing the flow based on the evaporator's duty plus the chiller input under governing conditions, maintaining a proper heat balance, and managing entering and leaving water temperatures. The pump must overcome real lift, friction, and equipment losses to maintain performance, and critical measurements like suction and discharge pressure, flow, and water level are continuously monitored. We also pay close attention to the net positive suction head to prevent cavitation, which requires checking minimum basin levels and all pump combinations. Additionally, the coordination of tower cell staging is essential. This means sequencing pumps, towers, and chillers so that flow is neither starved nor excessive. We track valve, fan, and pump states along with chiller approach trends to fine-tune operations. Lastly, maintaining water quality through strainers and chemical treatment is crucial, and we monitor differential pressure across strainers, conductivity, and other treatment records to prevent fouling and sustain system efficiency. On this slide, we're focusing on the condenser water capability and the importance of rapid recovery in the MVAC system. A key point to understand is that a condenser water event can trip a chiller before the chilled water loop has fully used its buffer, so it's crucial to coordinate the entire plant sequence effectively. We look at several required control behaviors, starting with accurate event detection. It's essential to identify pump, source, or intake events without triggering unsafe or nuisance responses. This includes capturing first-out alarms and time-stamped device states for precise diagnostics. When it comes to standby start, the system should only start a pump if it has a healthy suction path and an enabled heat rejection path, which depends on valve and cell permissives as well as speed and suction pressure monitoring. Flow restoration is another critical aspect. Reaching the chiller's minimum and required condenser flow within the project timing ensures stable operation. We monitor flow alongside condenser pressure and temperature to ensure proper recovery. Chiller stability is fundamental. Avoiding condenser high-pressure trips and unstable restart cycling preserves equipment lifespan and reliability. We track chiller limit states, alarms, and approach temperatures closely. Finally, thermal continuity is maintained by keeping the chilled water supply and IT thermal envelope within design limits. All of this is coordinated by monitoring synchronized trends across the plant and white space, which helps maintain smooth, efficient operation. Coordination of these elements is key to preventing downtime and ensuring the system responds effectively to condenser water events. Here we have several important abbreviations to remember. VSD stands for Variable Speed Drive, MCC is Motor Control Center, and EMC refers to electromagnetic compatibility. In this module on pumping and hydronic distribution, we focus on an integrated VSD architecture used within a data center MVAC system. A key point here is that one packaged pump with its VSD can reduce cabling and maintain local control. However, it's crucial that each pump train has independent fault containment to ensure reliability. Each train should have its own power source with an independent feeder and coordinated protection, allowing for safe operation and fault isolation. Local isolation is provided to enable safe lockout and servicing without affecting adjacent trains. The integral drive system ensures tight coordination between the motor and drive, optimized by the OEM to meet environmental requirements. The pump itself is certified within a specific operating curve, with considerations for NPSH and local protection to maintain system integrity. The plant interface manages supervision and control commands, and importantly, local fallback continues to operate even during network loss. Finally, the system is designed to prove conditions such as source loss, network loss, local faults, standby pickup, and concurrent maintenance for each independent pump train, ensuring continuous and reliable operation. Here we have an integrated VSD pump, which combines the pump, motor, drive, and a local keypad into one certified electromechanical package. But even with this integrated setup, it's crucial that the project design thoroughly proves several key points. First, the electrical source must be protected and isolated properly to ensure reliable source transfer and to maintain harmonic performance. Then, on the motor path side, we need to verify the cable length, install the correct output filters, and ensure proper grounding along with bearing protection and thermal limits. Moving on to control strategies, the primary method is using a remote differential pressure transmitter, while sensorless estimation can only serve as a limited fallback. Finally, comprehensive evidence needs to be gathered by trending key parameters like speed, current, power consumption, flow, and both suction and discharge pressure, all aligned on a single time base. Altogether, this approach allows us to verify the certified pump drive envelope, confirm the electrical source quality and harmonic limits, close the remote differential pressure control loop, and monitor hydraulic and power performance in real time. On this slide, we're looking at the separate VSD panel architecture and the critical need to prove every external boundary involved. Having a separate VSD panel definitely adds maintainability options, but it also introduces several external interfaces that demand careful verification. Starting with the source, it's essential to protect and isolate the drive, ensuring the transfer and harmonic performance are thoroughly proven. Then, looking at the motor path, we need to verify cable length, apply output filters, establish proper grounding, and confirm bearing protection along with thermal limits. For the control interface, primary reliance is on remote differential pressure transducers, with sensorless estimation serving only as a bounded fallback. Lastly, the evidence required includes trending speed, current, power, flow, suction and discharge pressure, and remote differential pressure, all measured on a consistent time base. The training outcome here is to define every VSD panel interface, verify motor insulation and electromagnetic compatibility paths, and importantly, prove remote hydraulic control mechanisms, bypass strategies, and fault containment measures. This comprehensive approach ensures robust operation within data center MVAC systems. On this slide, we're focusing on the critical topic of harmonics and how to define the measurement boundary in a data center MVAC system. The key point here is that IEEE 519 limits are applied specifically at the user point of common coupling, or PCC, not automatically at every pump disconnect. This means we need to agree on the PCC location with the utility or engineer, taking into account the system's short-circuit ratio and assessing the aggregate nonlinear load to get accurate measurements. We also look at the drive terminal, which is useful for equipment diagnosis, but is not the same as achieving IEEE PCC compliance. Recording operating load and source impedance at the drive terminal helps in detailed analysis, but doesn't replace the compliance checks at the PCC. Our study cases cover various scenarios including normal and generator or island source conditions, minimum and peak variable speed drive loading, and capacitor or filter switching. Finally, acceptance criteria focus on analyzing the voltage and current spectrum, power factor, true kilowatts, and ensuring the instrumentation bandwidth and measurement windows are appropriate for reliable results. This comprehensive approach ensures harmonic measurements are precise and compliant with standards. On this slide, we explore various harmonic mitigation options for data center MVAC systems. It's crucial to select the right mitigation method based on the system study, source strength, load profile, and resilience requirements. Starting with AC-DC reactors, they offer a simple way to reduce current distortion and improve drive input impedance. But keep in mind that residual total harmonic distortion may remain high, along with potential voltage drop and heat issues. Next, passive harmonic filters deliver good performance near design loading and have a straightforward architecture, though they can be affected by part load behavior, capacitive VARs, and generator interactions. The 12 or 18 pulse solution uses phase shift cancellation, ideal for large drives, but comes with transformer complexity, balance challenges, and a larger footprint. Active front-end drives provide low distortion and regenerative capabilities, but they also involve higher cost, switching emissions, intricate controls, and unique fault behaviors. Lastly, active harmonic filters offer flexible correction for varying loads, whether central or distributed. However, proper sizing, understanding failure modes, source configuration, and dependencies are essential to avoid issues. Each option carries trade-offs, so understanding these design cautions is key to optimal system performance. On this slide, we focus on the coordination between VSD-fed motors and cables, which is crucial for reliable operation. Long motor cables can cause increased reflected wave voltage and common mode current, which can lead to several issues. The main inputs we consider include the motor insulation system, cable length and routing, VSD switching characteristics, and grounding methods. These factors directly influence the risks associated with the system, such as motor terminal overvoltage, bearing currents, electromagnetic compatibility interference, and insulation heating. To mitigate these risks, common strategies involve using DV/DT or sine wave filters, proper shielding and grounding, insulated bearings or shaft grounding, and sometimes reducing the switching frequency if allowed. Lastly, we rely on evidence like OEM cable tables, installed route verification, grounding inspections, and motor terminal testing to ensure everything is correctly implemented and functioning as intended. On this slide, we're focusing on EMC and grounding, which are crucial for a stable sensor and control system. First, let's talk about segregation. It's important to keep power and signal routes separate, including encoder, analog, and network cables. When these cables must cross, they should do so at right angles to minimize interference. Next, bonding involves creating a low-impedance connection between equipment, such as motor and drive enclosures, and ensuring cable tray continuity. This helps maintain effective grounding. Then, termination requires 360-degree shield termination where necessary, avoiding long pigtails, and strictly following the original equipment manufacturer's grounding topology. Finally, verification is essential. Always perform a grounding inspection and check for noise-free analog values, monitor network error counters, and ensure there are no nuisance trips during transfer. These steps are key to maintaining reliable system performance. On this slide, we're focusing on the environment and enclosure considerations for variable speed drives, motors, and sensors in a data center MVAC system. It's crucial to evaluate each component based on the actual installed environment, not just the specifications in the brochure. First, thermal factors play a big role, including ambient and enclosure temperature, heat rejection and ventilation, as well as altitude derating, since these influence performance and longevity. Next, moisture must be considered. Humidity levels, potential condensation, exposure to washdown or spray, and appropriate drainage and heater strategies are all vital to prevent damage. Contamination is another key aspect, with dust, fibers, chemical or corrosive vapors, and water treatment exposure potentially affecting reliability. Finally, serviceability issues like safe clearances, filter and fan access, protection from sun and rain, and clear lifting or replacement routes are essential to ensure maintenance can be performed safely and efficiently. On this slide, we're focusing on the controls hierarchy for hydronic systems, emphasizing that stable variable flow control requires one owner per hydraulic variable. The pump is responsible for establishing the common distribution head, using a remote differential pressure transmitter to reset its speed. Next, the main riser differential pressure control valve, or DPCV, contains the pressure within each main riser zone, preventing pressure fluctuations from propagating. Importantly, there should be no floor-level DPCVs, as their presence can cause multiple interacting pressure controllers, leading to hidden authority conflicts and system hunting. Finally, each terminal electronic pressure-independent control valve, or E-PICV, ensures accurate flow metering and valve position control at the terminal level. By assigning one controller to each hydraulic level and removing redundant floor DPCVs, we achieve coordinated pressure reset and maintain terminal authority, resulting in a more stable and efficient hydronic distribution system. On this slide, we focus on the instrumentation architecture, emphasizing the importance of following the evidence from the field device all the way to the control action. A truly trustworthy control signal depends on a complete measurement chain, starting with the process connection and sensor, moving through range settings, calibration, and scaling, and including quality flags, network paths, and controller actions, all the way through to a verified process response. We begin at the field sensor, which measures key parameters such as pressure, temperature, and flow. Each step in this chain maintains a clear evidence path, ensuring data integrity as signals move to the PLC or BMS. Here, scaling, quality checks, and alarms are applied to maintain reliable operation. Next, the final control stage issues a bounded speed command based on these signals, again maintaining an evidence path. The process response is then measured, including head, flow, power consumption, and recovery, closing the loop to ensure that the control action produces the expected hydraulic outcome. Advanced reading involves tracing the sensor range and tap location, verifying calibration and quality, confirming controller fallback functions, and comparing the commanded action with the actual measured hydraulic response. This comprehensive approach ensures we can always validate the system's performance and maintain trustworthy control. On this slide, we're focusing on the sensor taxonomy, which is all about linking each instrument tag to the actual physical device behind it. This connection is essential because an instrument tag only becomes useful when you can identify the device, understand where it's connected in the process, know what variable it's measuring, and grasp the engineering range and the kind of signal it should provide. For example, a PT tag stands for a pressure transmitter, typically measuring pressure at pump suction or discharge points. A DPT is a differential pressure transmitter, often connected to remote indexes, filters, or coils. Similarly, an FT is a flow transmitter, which you might find on headers, pumps, or branches. Other tags include TT for temperature transmitter, used for heat balance measurements, VS for vibration sensor, which monitors pump condition, PWR for power meter, measuring true electrical kilowatts, and LD for leak detection around the CDU or floor areas. We also have LT for level transmitter that monitors tank or vessel levels, VPS for valve position feedback, verifying terminal valve position, SPD for VSD speed feedback, which helps track pump speed and detect faults, and PLC, a programmable logic controller that handles quality, alarms, and fallback functions. Finally, CV stands for commissioning verification, noting the portable references used during setup. The key training outcome here is to be able to connect each tag with the real equipment and clearly state its measurement purpose, installation dependencies, calibration methods, and what happens if it fails. Understanding these relationships ensures accurate monitoring and control in the pumping and hydronic distribution system. Here we see the distinction between measuring pump header pressure and verifying true terminal authority. The pump discharge to suction differential pressure confirms the pump head, but does not guarantee that the critical circuit downstream has sufficient valve authority to meet its requirements. A header differential pressure transmitter alone is incomplete because it can show that the set point is achieved, even if the remote CRAH, our critical terminal unit, is actually starved of flow. To truly govern the system effectively, a remote differential pressure transmitter must be placed across the entire critical circuit. This setup measures the full pressure drop and ensures the governing system maintains usable valve authority, allowing for a more optimized and often lower pump head. So, the key training takeaway here is to distinguish between local pump head confirmation and remote terminal authority by strategically placing the governing differential pressure transmitter across the full critical circuit. Here we focus on the correct placement of the remote differential pressure transmitter in a multi-story hydronic network. The key point is that the remote DPT should be installed across the supply and return of the entire critical terminal path, not just on a convenient local pipe segment or a single component. This ensures accurate measurement of pressure differences that truly represent the system's performance. During commissioning, it's essential to verify that every active terminal responds correctly to changes in network topology, confirming that the index moves appropriately. By doing so, we can route both pressure references to the same terminal boundary and ensure the selector and fallback behaviors operate as intended, which is crucial for maintaining system stability and efficiency. On this slide, we're focusing on pump differential pressure measurement and the distinction between local proof and remote authority. Locally, the suction and discharge pressures are measured directly at the pump to establish the actual pump head and its operating point. This is critical because it provides a direct proof of the pump's differential head and supports certified curve checks for accurate pump performance validation. However, it's important to note that this local measurement does not determine downstream terminal authority. On the other hand, the remote differential pressure transmitter, or DPT, plays a different role. It spans the hydraulically significant active terminal, capturing pressure after all distribution losses. This remote measurement is the governing distribution signal that controls terminal service and drives bounded variable speed drive reset and recovery acceptance. So, while local proof confirms pump performance, remote authority is essential for managing the overall distribution system effectively. In summary, we calculate the local pump head by subtracting suction pressure from discharge pressure, then reconcile this with flow and the pump's certified curve. Meanwhile, the remote differential pressure is used to govern the distribution, ensuring system balance without replacing the need for local pump proof. This distinction is key to maintaining both accurate pump operation and optimal terminal service. When selecting a flow meter, it's crucial to match the technology to the actual proof objective and installation conditions, rather than relying on a generic preference. This means considering factors like budget pressure loss, required straight pipe runs, grounding needs, turn-down ratios, and access for verification. For example, electromagnetic meters, labeled as MAG here, are ideal for conductive fluids and offer no flow obstruction. Clamp-on ultrasonic meters, like UFM, provide a non-intrusive option for verification without breaking the pipeline. Portable meters serve as commissioning kits for temporary, independent checks, while compact inline meters are suitable for branch-proof setups where maintenance is possible. The key training outcome is to align the meter principle with the fluid and proof duty, verify installation constraints, and understand the uncertainty and calibration methods to maintain accuracy. On this slide, we focus on the strategy for locating flow meters effectively within pumping and hydronic distribution systems. The key idea is to place flow meters exactly where they are needed to prove critical decisions, such as pump sharing and staging, overall plant total flow, minimum flow bypass, zone capacity and heat balance, or commissioning verification. It's important to maintain a valid full pipe flow profile, which means ensuring the pipe remains full and the flow conditions meet the meter's requirements for straight run length, orientation, grounding, and velocity limits. This enables accurate and reliable readings. Additionally, isolation or non-intrusive verification methods should be used, and it's essential to record both the as-found and reference measurements under the same operating conditions. The training outcome here is clear. Assign one proof objective per meter and place it where the flow balance closes. This approach ensures that the flow meter truly confirms the intended flow, whether it's per pump flow, header flow, bypass flow, or zone flow. By following these advanced installation rules, we can achieve precise verification and effective system control. On this slide, we focus on the critical process of temperature measurement and heat balance using paired RTDs on a single time base. The key here is to ensure that the heat balance temperatures are not only paired, but also immersed properly and time-aligned precisely with flow measurements. This alignment is essential because the accuracy and placement of the sensors directly affect the reliability of the calculated thermal duty. We use the heat balance equation shown here. Q equals density times specific heat capacity times flow rate times the difference between return and supply temperatures. To get trustworthy results, we rely on simultaneous and calibrated temperature values. The reading sequence is important. First, confirm the insertion depth and ensure the thermowells have good contact. Second, verify that the RTDs are matched and calibrated. Third, record flow, temperature, and load state together to maintain synchronicity. And finally, compare the calculated waterside duty with the declared equipment capacity and account for any uncertainties. The training outcome emphasizes this process. Pairing calibrated RTDs, verifying immersion and thermal response, synchronizing with flow data, and then accurately calculating and reconciling the waterside thermal duty. This systematic approach is what ensures dependable measurements in data center MVAC systems. On this slide, we focus on protecting the pressure reference in pumping and hydronic distribution systems. Level, static pressure, and expansion instrumentation work together to maintain accurate system pressure references. It's important to understand that low suction protection should reflect the actual pump inlet conditions, rather than just relying on vessel level readings. We use level transmitters to monitor brake tank or vessel levels and suction pressure transmitters to measure absolute pressure and net positive suction head available, or NPSH. Expansion vessels maintain reference pressure and gas charge, ensuring system stability, while air separators remove any entrained gases that might affect performance. Protective logic plays a crucial role by issuing early alarms if there's a drop in level, suction pressure, or expansion pressure. Trip actions should only trigger at validated protective limits and include ride-through and recovery capabilities to avoid unnecessary shutdowns. The key takeaway here is to define the pressure reference and usable inventory accurately, alarm any loss of level or pressure promptly, and ensure pumps are interlocked based on validated suction conditions for reliable and safe operation. On this slide, we're focusing on vibration monitoring and why it's crucial to understand the context behind the data. Vibration data becomes actionable only when several key factors are declared, including the sensor location, axis, mounting method, bandwidth, speed, and an established baseline. Simply receiving a generic alarm value is not enough to make informed decisions. The goal is to interpret vibration signals accurately by recording the axis, location, speed, flow, and load, then comparing these trends and spectral data against a known healthy baseline. This approach allows us to differentiate between potential issues such as imbalance, misalignment, cavitation, or looseness, which a single overall vibration value cannot do. By placing sensors on meaningful bearing locations and correlating vibration with operating parameters, we gain a clearer, more reliable picture to maintain pump and motor health effectively. On this slide, we focus on the importance of monitoring seal and bearing temperatures as an early warning system in pumping and hydronic distribution. The key here is that these temperature readings only become meaningful when a few critical factors are addressed. First, the sensors must be placed at fixed, failure-sensitive points on the equipment. This ensures we capture the most relevant data where problems are likely to begin. Next, it's essential to establish a baseline by documenting normal temperature trends based on operational conditions such as speed, load, and ambient environment. By doing so, we can interpret temperature changes accurately, distinguishing between normal process heating and actual signs of degradation. Recording details like the exact bearing or seal location, load, ambient temperature, and cooling state is crucial for this. Using methods like tracking the rate of temperature rise and comparing paired sensor locations helps separate normal fluctuations from potential failures. Ultimately, this approach allows us to correlate temperature deviations with other indicators like vibration, lubrication status, and hydraulic duty, providing a reliable early warning to prevent unexpected downtime. On this slide, we focus on the importance of reconciling electrical and hydraulic telemetry data, all based on a unified time reference. By aligning voltage, current, true kilowatts, speed, flow, and head measurements captured at the same timestamp and operating state, we gain a clear picture of whether energy is effectively converted into useful water power or lost unnecessarily. We monitor various parameters: true input kilowatts from the power source, speed and current from the variable speed drive, and head and flow responses from the pump. All this information is integrated via the PLC or BMS with scaled trends and alarms for real-time oversight. The key concept here is reconciliation, ensuring that hydraulic power, pump efficiency, motor and VSD efficiencies, and true input kilowatts all align within accepted uncertainty ranges. An important point is that any mismatch is not a signal to override sensors, but rather evidence prompting further investigation. This approach enables us to identify issues such as overload, bypass conditions, fouling, or sensor inconsistencies, ultimately optimizing system performance. On this slide, we're focusing on sensorless control in pumping systems and its limitations. Sensorless pump estimation can serve as a local fallback when sensor data is unavailable, but it cannot directly confirm remote terminal pressure, network changes, branch flow, or actual heat transfer performance. To use sensorless control effectively, it should be treated as a bounded fallback mechanism. This means maintaining minimum and maximum speed and differential pressure limits, while periodically cross-checking estimated head and flow data against local pressure and independent flow measurements. For remote validation, differential pressure transmitters and electronic pressure-independent control valves provide crucial evidence of downstream hydraulic conditions. If this evidence is invalid or lost, the system should revert to a conservative set point and alert operators about the missing validation. The key takeaway here is to understand the boundaries of sensorless models, limit their authority, and always retain remote hydraulic and thermal validation during normal control operations. On this slide, we focus on the limitations of sensorless control in pumping and hydronic distribution systems. It's crucial to keep sensorless operation within verified bounds, considering factors like accuracy, system topology, speed, and time. When control degrades, the system should automatically trigger an alarm and only allow remote control to be restored after the external validation signal is confirmed. Sensorless estimates can fail due to changes in fluid properties, impeller trim, fouling, uneven parallel pump operation, running outside the certified map, or a failed check valve. This highlights the need for remote validation using devices like the differential pressure transmitter and electronic pressure-independent control valves to confirm hydraulic adequacy downstream. If validation fails, the system switches to a conservative fallback set point and signals an alarm to indicate the loss of reliable evidence. The training outcome here teaches us to clearly define sensorless operation limits and timeouts, detect any disagreements in the model, safely revert to fallback operation, and then smoothly restore remote control once validation is confirmed. This slide outlines the sensor validation workflow, which is essential to ensure the complete measurement chain is accurate and reliable. Validation must cover everything from the process connection and the reference standard, all the way through transmitter scaling, network quality, controller interpretation, and finally, authorization to return the system to service. The process begins with connecting safely and using a test port, while recording the condition as found and as left. Next, we use a traceable portable reference standard to check measurements and again record results. Then comes calibration, where we adjust the range, zero, and span, documenting all changes. After calibration, verification of network scaling and quality ensures the system operates properly. Finally, we restore normal control functions, prove system alarms and control actions, and record the final authorized state. This thorough workflow guarantees that every step is documented and that the entire measurement chain, from pressure transmitters to flow transmitters, performs optimally within the hydronic distribution system. On this slide, we focus on sensor redundancy and voting in real devices, emphasizing the importance of true independence among sensors. Redundancy only improves system integrity when each sensor has independent taps, power sources, network paths, and maintenance isolation. This setup ensures that any disagreement among sensors is meaningful and deterministic, allowing for reliable detection of faults. We discuss two main voting strategies: 1 out of 2 selection, or 1002, and 2 out of 3 majority voting, 2003. The 1002 selection picks a validated channel, but requires careful handling of alarm disagreements and fallback strategies. The 2003 majority voting can outvote a single bad input, but this only works if taps, power, network, and calibration are truly independent across all sensors. The training outcome we aim for is to distinguish between mere duplicate labels and true sensor independence. This helps us define robust selection and voting logic, ensuring maintenance and failure events don't compromise control of the system. Understanding these concepts is critical for maintaining integrity in data center MVAC systems. On this slide, we focus on the concept of plausibility and virtual checks, which are essential for reconciling pressure, flow, heat, and power in our hydronic distribution systems. The key idea here is to use plausibility checks that compare independent physical measurements, such as pressure, flow, temperature, power, and valve position, to identify data that might be believable but actually incorrect. This helps prevent unsafe control decisions. We perform cross-checks on the same time base for various parameters. For flow, we look at the flow rate labeled as Q. For heat balance, the temperature difference represented as delta T. For pump head, the pressure difference delta P. And for electrical measurements, the true kilowatt consumption. We also consider terminal-specific data, like valve position combined with flow. An important example to highlight: if the pump speed increases but flow and the remote differential pressure do not change accordingly, that signals an inconsistency. In this case, you need to examine the suction conditions, valve positions, check valve openings, and sensor quality. It's critical not to accept just one convenient signal when the independent physics disagree. Our training outcome here is to build robust cross-signal physical checks, establish tolerances and persistence criteria, alarm on contradictions, and ultimately protect the control system with bounded fallback strategies. This ensures the system operates safely and reliably despite potential measurement errors. Remember, using these cross-verified measurements helps maintain system integrity and avoid unsafe control actions. In this module, we focus on the concept of differential pressure, or DP reset, in pumping and hydronic distribution systems. The key idea is that DP reset should find the lowest set point that preserves terminal authority, meaning it maintains control over the important terminal valves. This reset acts like a constrained optimizer. It lowers pressure when the system's valid valves are satisfied, but it must also respond quickly to avoid losing useful terminal flow, preventing any device from starving for flow. We work with a physical reference setup that includes a vertical inline centrifugal pump equipped with a variable speed drive, or VSD. The reset logic takes several inputs such as a remote differential pressure transmitter, validated representative PICV positions, and minimum and maximum delta pressure bounds. It also includes sensor loss fallback to maintain reliability. Our control objective is to maintain the lowest stable differential pressure set point that keeps the critical terminal controllable. To achieve that, we only use qualified demands by excluding isolated, frozen, or non-communicating valves. The reset process involves 3 steps. First, we validate inputs, ensuring active differential pressure transmitters and representative valves are accounted for. Next, we trim or respond by lowering the set point slowly when demand is satisfied, but raising it quickly if the system experiences starvation. Finally, we apply bounds so the set point stays within defined minimum and maximum limits. Why is this important in the field? A fixed set point can waste energy by providing excessive pressure at part load, while an aggressive reset can cause critical terminals to starve. Therefore, the controller must carefully qualify valve demand inputs, apply bounded trim and respond logic, and verify the results by monitoring terminal flow, valve positions, remote pressures, pump speed, and electrical power consumption. So the takeaways are: validate your demand inputs, trim pressure set points carefully to maintain control, respond swiftly to signs of starvation, apply safeguards including bounds and hysteresis, and always prove performance through detailed trending of all key parameters. Ultimately, this method enables lowering pump head without sacrificing flow, ensuring energy efficiency and system reliability through sound validation, fallback, and proof strategies. This slide focuses on the concept of trim and respond control in pumping and hydronic distribution systems. The key to success here is to react fast, trim slowly, and reject bad signals. When the system responds quickly to valve starvation by raising the differential pressure set point, it prevents underperformance. Then it trims the pressure down gradually once stability is achieved, avoiding unnecessary fluctuations. Stable valve demand feedback is essential to reduce pump energy without causing hunting or persistent valve saturation. To achieve this, the system uses several control ingredients like a high open starvation threshold, low open trim threshold, separate enter and exit values, hydraulic settling dwell, and the exclusion of bad signals. It's crucial that the demand data is trustworthy, so frozen, noisy, isolated, or failed valve signals must be excluded. The control cycle involves qualifying valid valve demands, responding with fast increases and slow decreases in pressure set point, followed by a dwell period allowing hydraulic settling. Why does this matter? Because only real active loads should influence the system. Otherwise, noise or bad communication can cause unnecessary set point shifts. The process uses asymmetric response, hysteresis, and stability proofs to confirm there's no hunting or hidden low-flow loads. In summary, define when to trim by lowering pressure when all valves are satisfied, respond promptly to any valve starvation by increasing pressure, add dwell times for stability, exclude bad data, and confirm stable operation with no hunting. This approach preserves control authority while minimizing pump energy consumption in data center MVAC systems. On this slide, we focus on pump staging with real trains, matched speed, and proven forward flow. The key challenge here is that the state machine must carefully control physical isolation, check valves, drives, and pumps in a sequence designed to avoid reverse flow and pressure shock. This sequencing involves 5 critical steps. First, we detect a validated field condition and ensure it meets the declared acceptance criterion. Following that, we decide using bounded logic and alarms, again confirming the declared acceptance criterion. Next, we command the system to ramp, stage, or fallback, ensuring all actions meet the acceptance criteria. Then, we act to maintain forward flow and the proper system head pressure. Finally, we prove success with an independent response record, verifying that every declared acceptance criterion is satisfied. The most important aspect is the sequence proof, which integrates physical isolation, validated sensors, controller quality, commanded actions, measured process responses, alarms or fallbacks, and stable recovery. Without this coordinated sequence and verification, the entire process risks failure. Advanced acceptance involves time-aligning commands with device positions, pump speeds, branch flows, local pressures, remote differential pressure, terminal valve positions, and thermal responses to ensure every command results in a successful process response. If the process response does not happen, that step fails, highlighting the importance of this thorough and validated control system in data center MVAC pumping and hydronic distribution. On this slide, we're focusing on local control and the behavior of the system during network loss within a data center MVAC system. First, it's important to understand that loss of supervision should degrade optimization, not disable the essential safe pumping functions. When the network is operating normally, speed control relies on plant differential pressure reset and staging optimization. However, if the network is lost or degraded, the system switches to a local bounded differential pressure or curve set point to maintain function. In terms of protection, local protection stays fully active, complemented by supervisory alarms in normal conditions. For standby starts, the plant controller coordinates the event during normal operation, but if the network is down, hardwired or local peer logic will start the standby pump as needed. Set points during supervision follow approved limits. If the network is down, the system uses the last safe or predefined fallback settings, which are time-limited to prevent issues. Alarm and event data are sent in real time to the building management system or energy management system, while a local buffer stores the first-out event and trend data for later reconciliation. Finally, recovery involves a bumpless transfer back to normal control after validation, ensuring we do not overwrite the local first-out information. This approach ensures safe and reliable pumping even in the face of network disruptions. On this slide, we're diving into the alarm philosophy for the Data Center MVAC system, focusing on how alarms are managed to ensure system reliability and safety. The key approach is to separate protection, process deviation, and maintenance advisory alarms, so we can suppress alarm floods that often mask the initial root cause. Alarms are prioritized into 3 levels. P1 critical alarms indicate serious issues, such as loss of required duty or multiple train failure. These trigger immediate automatic responses to protect equipment and escalate to emergency operating procedures without delay. P2 high priority alarms relate to conditions like standby system unavailability or source degradation. Here, the goal is to maintain system duty and prevent unsafe transitions while working to restore resilience within the site's service level agreement. Lastly, P3 maintenance alarms, such as vibration trends or seal leaks, do not cause trips unless safety limits are met, but prompt planned corrections to avoid escalating risks. Every event is thoroughly recorded with data like trip cause, commands, speed, and flow, enabling a detailed root cause review with synchronized timestamps. This comprehensive alarm strategy supports reliable operations and efficient troubleshooting. On this slide, we're focusing on condition monitoring and predictive indicators in pumping and hydronic distribution systems. The goal here is to use trend degradation data at matched operating conditions so that maintenance is evidence-based rather than reactive. We categorize indicators into 4 key areas. First, hydraulics. We monitor deviations in head flow performance, signs of cavitation through NPSH indicators, pressure drops across strainers and components, and issues like low delta T or bypass flow. Next, mechanical indicators include vibration spectrum analysis, bearing and seal temperatures, leak rates, and shifts in alignment or baseline conditions. For electrical monitoring, we observe power consumption at matched duty points, current or torque imbalances, thermal and fault counters and variable speed drives, and insulation or bearing current indicators. Finally, control system indicators track behaviors such as hunting and saturation, sensor drift or disagreement, stage frequency variations, and the duration of fallback or override conditions. Together, these indicators enable us to predict and prevent failures efficiently. Commissioning is the critical step that closes the proof chain by connecting real equipment with traceable records. It starts with validating field conditions against declared acceptance criteria, then moves to decision-making through bounded logic and alarms. Next, commands are issued with ramping, staging, and fallback strategies, all verified against set criteria. The system then acts, delivering forward flow and head while meeting those criteria. Finally, commissioning proves success by independently recording responses to ensure the system performs as intended. Without this aligned verification, any command lacking a physical process response is a failed step. This thorough approach validates sensing, controls, commands, responses, and alarm handling, establishing complete confidence in system readiness. On this slide, we focus on the performance acceptance matrix for pumping and hydronic distribution systems within a data center MVAC setup. The matrix outlines key tests and acceptance criteria to ensure the system functions reliably and efficiently. First, we specify the boundaries, initial states, instruments, tolerances, and pass/fail values for every test to maintain consistency and accuracy. Starting with hydraulic duty, we measure flow, suction and discharge pressure, speed, and fluid state, ensuring the duty point falls within the specified tolerance and approved operating region. Next is wire-to-water performance, where we look at the true input power in kilowatts alongside flow and head. The system must meet project KPIs at declared operating points, guaranteeing efficiency. Staging tests examine commands, speeds, check valves, flow, and remote differential pressure, confirming stable transitions without hunting, reverse flow, or any limit violations. Standby pickup involves measuring the trip-to-speed, flow, differential pressure, and thermal timeline. The system should meet the declared response class and maintain the thermal envelope. For source or network loss scenarios, we assess the electrical and control states plus hydraulic duty to ensure the required residual duty remains and any degraded state is clearly enunciated. Finally, protection tests cover low suction, overload, vibration, and leak situations. The goal is to verify that correct first out and safe actions occur without unauthorized bypass, safeguarding both equipment and system integrity. Overall, this matrix provides a comprehensive framework to validate pumping performance and ensure the data center's cooling system operates smoothly and safely. Here we have the essential steps of a rapid response integrated system test, or IST, which is critical for ensuring the reliability of pumping and hydronic distribution systems. The test process must cover the entire timeline, starting with fault detection, qualification, control action, standby transfer, hydraulic recovery, thermal protection, and stable return without oscillation. First, we detect by validating field conditions against declared acceptance criteria. Next, we decide using bounded logic and alarms to confirm the situation fits those criteria. Then, commands are issued in stages such as ramping up or fallback, again meeting predefined acceptance points. The act phase checks for expected forward flow and head pressures, while the prove step independently records the system's response. This recording is crucial because a command without a matching process response indicates failure. The advanced acceptance criteria require precise time alignment between commands, device positions, pump speeds, flow rates, pressure readings, valve positions, and thermal reactions. This detailed synchronization ensures the system operates seamlessly through all stages. Ultimately, the training outcome here is to declare the initiating event and limits, time every detection, action, and response, and verify service continuity, alarm quality, and stable recovery. This rigorous process helps maintain system integrity and performance in critical data center environments. On this slide, we're focusing on the failure matrix and degraded modes within the Data Center MVAC system, specifically around pumping and hydronic distribution. It's critical that every event has a predicted automatic response, a safe residual state, and a clear operator action. For example, if the lead pump trips, the system automatically starts a hot standby pump and isolates the failed train as designed, ensuring required flow and differential pressure continue within the response class. Another key scenario is a remote differential pressure sensor failure, where control transfers to a validated redundant system, preventing pump trips and overpressure. In case of network loss, the system retains local control and falls back to a safe set point, maintaining required duty with only optimization degraded. For a loss of source A, the system switches to source B to meet resilience objectives, ensuring continuous operation. Lastly, when there's a low suction or basin level, the system protects the affected chilled water pump and only starts an alternate if conditions are healthy, preventing dry running or cavitation damage. These responses are validated through proofs like flow timelines, alarms, and protection tests to guarantee safety and reliability. Here we focus on troubleshooting the Data Center MVAC system by moving from symptom observation to identifying evidence and taking safe action. First, understanding the abbreviations is crucial. DP stands for differential pressure, PLC means programmable logic controller, and BMS is building management system. When we see a symptom like low flow at normal speed, likely causes include closed valves, fouling, air in the system, wrong rotation, or curve mismatch. To confirm, we check pressures, valve states, differential pressure across components, and rotation direction. The key here is to protect the load, restore the approved flow path, and isolate the system before any work begins. For symptoms such as low suction or noise, potential causes could be low fluid level, blocked suction, vortex formation, high temperatures, or air ingress. Evidence comes from measuring absolute suction pressure, fluid level, vibration, and intake conditions. In those cases, reducing or stopping the affected pump train within operational limits is necessary. If we encounter high power consumption, it often points to excess flow, mechanical drag, incorrect speed or impeller selection, or fluid density issues. We rely on data like flow, head, speed, electrical current, temperature, and alignment to diagnose. Maintaining operation within system limits and unloading or isolating equipment ensures safety. Differential pressure hunting indicates sensor faults, aggressive PID tuning, or interactions between pumps and valves. High-resolution monitoring of these parameters helps stabilize control. In this scenario, applying a stable fallback and stopping rapid cycling is essential. Lastly, slow system recovery might be caused by issues like transfer delays, permissive logic, ramp rates, check valves, or air bottlenecks. Analyzing the timeline from event to hydraulic and thermal response guides corrective action. Always maintain system buffer and resolve bottlenecks before retesting to ensure reliable operation. On this slide, we're focusing on the normal operating procedure, which crucially follows the real hydraulic path to maintain proper pressure, flow, and temperature control throughout every phase, from startup to shutdown. The process is broken down into 5 key steps. First, we detect by validating field conditions against declared acceptance criteria. Next, we decide using bounded logic and alarms to confirm conditions meet those criteria. Then, we command actions like ramping or staging the system, again ensuring acceptance criteria are met. The fourth step is to act by forwarding flow and maintaining head pressure. Finally, we prove by independently recording responses to verify the actions taken. It's important to emphasize that advanced acceptance requires time-aligning commands with device position, pump speed, branch flow, local pressure, differential pressure, valve position, and thermal response. Without this coordinated process response, the step is considered a failure. This procedure ensures safe transfers and a stable final state in the system, which is essential for reliable data center MVAC operation. Let's talk about the emergency operating response for the data center MVAC system outlined in this module. First, the priorities during any emergency are clear. Protect people and equipment first, then preserve the thermal duty, and finally, restore system resilience only after controlling the root cause. In case of a loss of flow, it's crucial to confirm the actual flow and differential pressure, execute an approved standby path, monitor the thermal envelope closely, and escalate load risk actions early to prevent damage. For leak or rupture events, protecting electrical exposure is paramount. You should isolate the smallest safe segment, use an alternate flow path if available, and carefully manage water and pressure control to minimize impact. When dealing with electrical events, always respect lockout/tagout and arc flash boundaries. Verify the alternate power source before proceeding, avoid repeatedly resetting faults which can cause further issues, and continually track the hydraulic impact to ensure system stability. Finally, during recovery, confirm that the first out alarm and cause are known, have an independently checked lineup, restore standby systems, and conduct retests as assigned to ensure everything is back to full operational status. Remember these steps to maintain safety and system integrity under emergency conditions. Here we focus on some key abbreviations that will come up frequently in this module. DPCV stands for Differential Pressure Control Valve, E-PICV means Electronic Pressure Independent Control Valve, and DPT refers to the Differential Pressure Transmitter. These components are fundamental to advanced hydronic distribution systems in data center cooling. In multi-story setups, managing pressure control, ensuring terminal flow independence, and integrating staged fit-outs are essential for reliable operation. Each valve and sensor is carefully designed to safeguard a specific hydraulic outcome, following the process from design through control, measurement, testing, and operation. This approach ensures mission-critical cooling remains effective and stable. Here we have a design assurance map for the data center MVAC system, which relies on 4 coordinated layers to keep every active phase stable, while pumps respond to the actual hydraulic demand. First is the plant layer, featuring VSD pump trains, minimum flow protection, and synchronized timestamps for proof and monitoring. Next, the distribution layer manages pressure zones and main risers, with a differential pressure control valve, or DPCV, installed at each controlled main riser. Note that no DPCVs are used on horizontal or floor branches. The terminal layer ensures precise flow control with pressure-independent control valves, or PICVs, at every CRAC, CRAH, FCU, and FWU, as well as at each CDU facility water branch. This layer provides data on flow, temperature difference, and leakage evidence. Lastly, the control layer incorporates critical point differential pressure transmitters, or DPTs, employs differential pressure reset and most open valve logic, and includes sensor failure fallback to maintain system reliability. Importantly, the main riser DPCV, terminal PICV minimum differential pressure, and remote DPT pump setpoint must all be checked together at every operating state to ensure stable and efficient performance. On this slide, we focus on the real equipment hydronic legend, which is essential for understanding pumping and hydronic distribution systems. The key here is how real equipment images help us quickly recognize components in the field. Each component is identified by its common engineering name, its flow direction, and its specific function. This approach ensures that we don't confuse these training visuals with the official PNID drawings. For example, the isolation valve, or 4, is used for safe equipment isolation, while the non-return valve, NRV, prevents reverse flow in the system. The Y strainer, labeled as YSTR, protects devices by filtering out debris and includes a blowdown feature for cleaning. We also have the automatic air separator, AV, which removes entrained gas that could affect system efficiency. On the control side, the electronic pressure-independent control valve, or E-PICV, manages terminal flow precisely, and the differential pressure control valve, DPCV, is typically used in the main riser zones to maintain stable pressure. Motorized control valves, MCV, handle modulating duties or bypass functions, while manual balancing valves, MBV, are used for fixed flow measurement and balance. Other important components include the flexible connector, FC, which helps with alignment and vibration isolation, and the expansion tank, ET, which provides a reference pressure to accommodate system volume changes. The filter/degassing skid, FDS, combines water quality protection with gas removal, and the commissioning kit, KIT, offers portable proofing tools during system startup. The ultimate training outcome we aim for here is to confidently identify each component by its engineering name, know the direction of flow and duty, and relate what we see in the field to the approved PNID symbols. This knowledge is crucial to effective operation and maintenance in complex MVAC systems like those in data centers. On this slide, we focus on the real equipment instrumentation legend, which is crucial for understanding our hydronic distribution system. Each instrument is linked to a tag, a full engineering name, the variable it measures, and its evidence purpose. This approach helps you recognize and verify the actual device instead of just memorizing symbols. For example, PT stands for pressure transmitter, which monitors pump or header pressure. Similarly, DPT is a differential pressure transmitter used for applications like remote indexes, filters, or coils. FT stands for flow transmitter, measuring header or branch flow. Other key instruments include TT for temperature transmitters, LT for level transmitters, and VS for vibration sensors that monitor pump condition. We also cover devices like leak detection sensors, power meters for true electrical kW, valve position feedback devices, and programmable logic controllers for system quality, alarms, and fallback. The training outcome here is to confidently connect each tag to its physical device, understand what it measures, and be able to state the calibration, quality, and fallback requirements involved. This ensures practical, hands-on knowledge that goes beyond just theoretical symbols. On this slide, we focus on multi-story hydraulics in pumping and hydronic distribution systems, specifically how to separate static pressure from pump head. Elevation sets the static pressure envelope, meaning it determines the pressure range we need to maintain throughout the system. In a closed-loop system, the pump's main job is to overcome dynamic losses, not the elevation. For the static envelope, it's important to keep positive pressure at the highest point to avoid issues like cavitation or air ingress. We also need to check the pressure rating at the lowest point to ensure components can handle the pressure there, and coordinate the locations for expansion and pressurization to maintain system stability. Dynamic head accounts for losses due to pipes and fittings, as well as coil, heat exchanger, and valve losses. We also include measurement allowances and factors for fouling over time, which can impact the system's efficiency. Pressure zoning comes into play when component pressure classes or control ranges are exceeded. This can be managed through hydraulic separation methods, such as heat exchangers or dedicated zone pumps, to protect the system during transient conditions and maintenance operations. Finally, remember not to add building elevation to the closed-loop pump head calculation, but always calculate static pressure at every component to ensure accurate system design and operation. On this slide, we're focusing on a system with one pressure zone that remains stable when managed correctly. The key here is having a single main riser differential pressure control valve, or DPCV, which contains the entire pressure zone. At the same time, each terminal uses an electronic pressure-independent control valve, or E-PICV, to regulate its own flow independently. This setup means the pump only needs to supply the common head required across the system, improving efficiency. It's crucial during commissioning to verify that each terminal's E-PICV maintains authority over its flow, especially as the network topology changes. This ensures stability and proper control. Ultimately, the pump reset controller uses information from the remote differential pressure, PICV demand, and specified bounds to adjust the pump head accordingly, maintaining the system's balance and performance. In this slide, we focus on independent pressure zones and the use of one differential pressure control valve, or DPCV, per main riser. Independent main riser DPCVs should be used only when risers have significantly different pressure needs or operating limits. Each zone created this way must be hydraulically and operationally testable, ensuring it can function and be controlled independently. The key to effective design is to justify each pressure zone, assign one DPCV per riser, and then demonstrate independent isolation, terminal authority, and coordinated pump reset. This approach helps maintain stable system performance and efficient pump operation in complex hydronic distribution setups. Here, the key point is that the differential pressure control valve, or DPCV, should be installed only at the main riser boundary. This placement defines one clear pressure zone, which is essential for system stability. Adding DPCVs at the floor branches is not recommended because those branches depend on terminal electronic pressure independent control valves, or E-PICV. Introducing another pressure controller in series would cause unwanted interaction and complexity. So, by locating the DPCV at the riser inlet and removing any floor-level DPCVs, we ensure that the terminal E-PICV maintain their control authority and diagnostic clarity. This approach preserves the system's efficiency and simplifies troubleshooting in the Data Center MVAC system. On this slide, we're looking at the hydraulic control hierarchy, which is key to converting terminal demand into plant action in a clear, one-directional flow. At the core, the E-PICV, or electronic pressure independent control valve, controls the flow at the terminal level. Moving up, the riser DPCV, or differential pressure control valve, maintains and contains the system pressure within its zone. Then we have the remote differential pressure transmitter, or DPT, that helps qualify and verify the service by providing independent measurements. Finally, the pump's variable speed drive, or VSD, supplies the necessary head pressure to support the entire system. Understanding this hierarchy allows us to follow the cause and effect chain from terminal demand through to the pump response, ensuring that every control boundary is accurately monitored and maintained. Here, we're focusing on the correct placement of the remote differential pressure transmitter, or DPT, across the entire governing terminal. It's crucial to position the remote DPT so it measures the residual service pressure after all distribution losses have occurred, rather than just the pump room pressure or the pressure drop across a single component. This ensures accurate feedback for controlling the system effectively. As we commission each active terminal, we need to verify that the selected index responds appropriately when the network topology changes, confirming that our signal is reliable for pump reset control. By bounding the critical circuit with supply and return taps, and checking tap zones and polarity, we can confidently qualify the signal for the pump reset function. This process is essential for maintaining system balance and efficiency in hydronic distribution. On this slide, we're focusing on the remote DPT installation and its critical components for a reliable system. First, it's essential to have accessible taps and root valves along with a real manifold, ensuring the system is both serviceable and trustworthy. The impulse lines must be correctly routed with continuous slope to avoid any trapped air pockets, and vent or drain points should be provided for maintenance. Labeling is another key point here. Use stable static pressure locations and clearly mark the true high and low sides to maintain accuracy. We also need to verify zero and polarity by equalizing and opening roots, confirming the sensor's positive response with a known state. Finally, consider the failure action plan. On any implausible readings, the system should freeze to a safe fallback and trigger an alarm. This approach ensures ongoing safety and reliability by eliminating trapped air, blocked paths, and maintaining proper calibration and isolation. On this slide, we're focusing on handling multiple critical circuits in hydronic distribution systems. When several circuits can become critical, it's important to select either the farthest valid differential pressure transmitter, or DPT, or the highest qualified valve demand signal. This selection process must account for any signal disagreements, exclude poor quality data, and provide a bounded fallback option to ensure reliability. The key here is that every active terminal needs to be commissioned carefully, and the selected index must change appropriately as the network topology shifts. This approach ensures we can identify changing critical paths, validate each signal thoroughly, and deterministically select the governing demand. Additionally, it allows for thorough testing of disagreements and fallback mechanisms, which is crucial for maintaining stable and efficient operation in a data center's MVAC system. On this slide, we're looking at the trim and respond differential pressure reset strategy, which involves real differential pressure transmitters, controllers, drives, and pumps. The key idea here is that the system lowers the differential pressure set point slowly whenever there is valve margin available, and raises it quickly if there's validated starvation detected. This approach helps maintain system stability by using rate limits and fallback mechanisms. The reset logic operates in a sequence. First, it trims down with small downward steps only when all critical valves show margin. Then it detects if the remote differential pressure is below a set bound and whether the electronic pressure-independent control valves are near saturation. When starvation is confirmed, it responds with a larger upward step and a dwell period to observe the system's reaction. If the differential pressure transmitter data becomes invalid, the system falls back to a conservative bounded set point and triggers an alarm to ensure safety. Lastly, it proves that there's no hunting or sustained valve saturation or thermal excursions, ensuring reliable operation. Overall, this method qualifies demand carefully, trims conservatively, responds rapidly to starvation, and enforces bounds, persistence, and fail-safe fallback, which is crucial for maintaining optimal performance in data center MVAC systems. On this slide, we're focusing on the CRAH branch, which is considered a fully maintainable service circuit. That means all key elements like isolation valves, strain removal, and controls for flow, pressure, and temperature need to be fully accessible at all times. It's crucial to ensure air removal, proper drainage, and reliable electronic pressure independent control valve, or E-PICV, functionality within this branch. When commissioning, follow a specific order. First, verify the coil is clean and vented and the isolation valve is open. Next, command the E-PICV to 100% and confirm the design flow. Then, check that the PICV minimum differential pressure is as expected at the valve ports. Record the entering and leaving water temperatures, along with the declared fan or load state, and only then trim the flow after thermal stability is achieved. By carefully tracing the entire CRAH branch and verifying component orientation and accessibility, you can prove the flow is correct, the valve has the right authority, the temperature differential matches the design, and the system's thermal duty is properly met. This thorough approach ensures reliable and efficient operation of the data center's hydronic distribution system. This slide focuses on the fan wall unit branch, which uses a pressure-independent control method similar to CRAH service. The key point here is that this system requires synchronized verification across 4 critical factors: high airflow, water flow, coil temperature difference, and the active fan state. When commissioning, you follow a specific sequence starting with proving the coil is clean and vented, then opening isolation valves. Next, the electronic pressure-independent control valve, or E-PICV, is commanded to 100% to verify design flow. It's important to confirm the minimum differential pressure at the valve ports and measure both entering and leaving water temperatures along with the fan or load state. The final step is trimming the flow, but only after thermal stability has been achieved. This rigorous approach ensures accurate control of the fan wall unit's hydraulic performance, ultimately resulting in stable air and water conditions, precise duty calculations, and proper E-PICV authority and recovery. This process is essential for reliable operation in data center MVAC systems. Here we are focusing on the CDU facility water branch and its role in controlling heat rejection flow. It's important to understand that this branch manages only the heat rejection flow, while the CDU's internal technology loop independently maintains critical factors like rack flow, pressure, chemistry, filtration, expansion, and leak response. This separation ensures precise control and reliability. On the slide, you see real equipment details with flow rates and temperatures, such as the 600 kilowatts CDU operating at 14.33 liters per second with a 10 Kelvin temperature difference. The commissioning sequence is very specific, starting with confirming a clean, vented coil and open isolation valves, then commanding 100% electronic pressure-independent control valve, or E-PICV, flow to verify design parameters. You also check the minimum differential pressure at valve ports and record temperatures along with the declared fan or load state before trimming flow after the system reaches thermal stability. The key outcome here is to define the chilled water service boundary clearly, prove the facility-side E-PICV and heat transfer performance, and preserve independent thermal control system hydraulic operation. Understanding these procedures ensures efficient and stable operation of the data center's mechanical cooling infrastructure. On this slide, we focus on the CDU branch control boundary and how it assigns ownership to real devices within the system. The key idea here is that every device, whether it's related to facility water duty, heat exchanger supervision, or technology loop hydraulics, has a clear and unambiguous owner. This means no signal or actuator is left without defined responsibility, which is crucial for system reliability and safety. For example, the facility water valve demand is never allowed to directly control the technology loop pump speed, maintaining clear operational boundaries. Each device, such as the electronic PICVs, N+1 pumps, filters, and expansion components, has assigned ownership along with alarms and proof testing to ensure proper function. This segregation allows for independent flow, pressure, temperature, chemistry, and failure tests on both sides of the boundary, reinforcing system security. By establishing these ownerships and control boundaries, we can confidently assign device responsibilities and prove the effectiveness of interlocks, alarms, redundancy measures, and safe leak isolation within the data center's MVAC system. Here we have the control hierarchy involving the pump, main riser differential pressure control valve, and terminal electronic pressure independent control valve, or E-PICV. Each controller operates on different variables and timescales to ensure stable terminal service, even as demand, staging, or failures change. At the plant level, the pump variable speed drive adjusts to maintain a common head pressure within a measured acceptance boundary. Moving down to the main riser, the DPCV controls the differential pressure across the riser zone, with one valve per main riser, keeping pressure steady within its own acceptance limits. Finally, at the terminal level, the E-PICV manages the flow to individual coils or heat exchangers, ensuring accurate thermal duty delivery. Testing this hierarchy means changing one controller at a time and verifying its response variable, making sure no two valves react to the same pressure disturbance. Otherwise, control boundaries would overlap or be misplaced. The goal is a coordinated dynamic response across all layers, verified by separated control variables and bandwidths, which guarantees consistent and efficient system performance throughout the data center's MVAC system. Here we have a complete multi-story hydronic riser that integrates several critical functions into one clear and traceable hydraulic path, from the pump header right through to the essential circuit. This design consolidates pressure zoning, terminal control, remote sensing, isolation, and acceptance points, making it easier to manage and monitor the system efficiently. You'll notice the system is structured across multiple levels, with real equipment and acceptance points clearly defined at each stage. The pump reset controller plays a key role here by adjusting based on remote differential pressure, PICV demand, and system bounds. Importantly, the engineering interpretation guides us to accept the system only after all terminal valves can reach their design flow, and the standby pump successfully recovers remote differential pressure in the event of a failure. This ensures reliability and performance throughout the riser. By tracing this full riser path, we can identify pressure zone boundaries, locate key measurements that govern system function, and confirm terminal service and isolation capability at every level, providing confidence in the system's operation. Here, we're looking at the Phase 1 baseline where the future tie-in remains positively isolated. This means that any future expansion starts with a tie-in that is fully drained, capped, and documented to ensure it is completely separated from the live system. The goal is to prevent any contamination, depressurization, or accidental control during ongoing operations. Establishing a safe baseline isolation is critical. This involves documenting the state of valves, blinds, drains, and control elements thoroughly before construction begins. By doing so, we protect the current operating service while ensuring future phases can connect smoothly and safely. This approach maintains system integrity and avoids disruptions during the tie-in process. Here we focus on the critical process of connecting Phase 2 while maintaining the integrity of the live network through double isolation. The goal is to construct and thoroughly test the new phase without exposing the existing system to debris or uncontrolled flow. This involves cleaning, flushing, pressure testing, drying, venting, and proving every subsystem behind 2 isolation points. By doing this, we ensure that Phase 1 remains live and accepted, while Phase 2 is completely isolated and independently verified. The temporary loop with its own flush pump and filters allows for this safe and controlled testing. Ultimately, this approach preserves live isolation, completes mechanical cleaning and pressure tests, and proves new controls independently before full integration, safeguarding the entire network throughout the process. In Phase 2 pre-integration commissioning, our focus is to prove each real subsystem independently. This means we test mechanical, electrical, controls, and terminal subsystems on their own before moving on to the final integration. The goal here is that the final opening tests only need to evaluate the interface between systems, not uncover any unresolved component defects. We follow a clear, step-by-step process, starting with isolating the subsystem within a lockable boundary and applying a declared acceptance criterion. Next, we conduct tests such as flushing, pressure checks, and calibration to ensure everything meets standards. After testing, we integrate the components while monitoring scaling, quality, and maintaining the ability to roll back if needed, again confirming each step against declared criteria. Then, we energize the system by matching command inputs with actual startup results, proving flow, and ensuring all parameters align. Finally, the subsystem is accepted based on terminal authority and documented evidence. The advanced acceptance includes time-aligning vital controls and responses like pump speed, branch flow, and valve positions. Remember, if a command does not result in a process response, that is a failed step. The training outcome ensures complete FAT and SAT evidence, validating sensors, drives, valves, and terminals, so integration proceeds only from a known and ready state. This rigorous process is key to successful commissioning in data center MVAC systems. Here we focus on the controlled Phase 2 opening process, which is crucial for maintaining system stability. First, we only open the new phase once pressure equalization has been achieved and control states are matched. This prevents sudden shocks or disturbances to the system. Then, we stroke the valves slowly while monitoring the live system margins. It's important to watch for any deviations from the predefined limits and be ready to stop or roll back if necessary. This process includes 5 key steps: isolate, test, integrate, energize, and accept, each with declared acceptance criteria to ensure quality and safety. The advanced acceptance step involves time-aligning command signals, device positions, pump speeds, and pressures to verify the entire system's response. Remember, a command without a process response is a failed step. By following this approach, we ensure a smooth transition and reliable performance in our data center MVAC system. On this slide, we focus on the post-integration proof for Phase 2 of the data center MVAC system's pumping and hydronic distribution. Acceptance criteria are based on the combined system performance and preserving the existing phase baseline. Key areas assessed include hydraulic stability, ensuring flow and differential pressure remain within agreed deviations, with every terminal reaching its preset flow and critical DP transmitters maintained without excess head. We also examine thermal duty, making sure there are no unacceptable temperature excursions in CRAH, FWU, or CDU units, while confirming new phase capacity and delta T remain acceptable. Valve behavior must show stability, with both existing and new PICVs and DPCVs operating without hunting or saturation and proper use of most open valve reset candidates. Pump staging criteria require no nuisance staging or minimum flow violations, and pumps must respond appropriately to new demand under both normal and faulted conditions. Finally, water quality checks confirm no contamination or strainer differential pressure events, and that chemistry limits for the new phase are met, with accepted post-integration samples and filters. This comprehensive set of criteria ensures the system integrates smoothly and operates reliably. Here we focus on future phase flushing, which is crucial to protect the operating network. The key point here is that flushing must be done using a dedicated temporary loop or an isolated route. This is important because it prevents debris from being pushed through operating coils, PICVs, heat exchangers, sensors, and other critical production equipment. The diagram illustrates two phases. Phase 1 with live, accepted equipment, and Phase 2 as new and isolated. Temporary filters, degassers, and flush pumps are used in this independent loop to achieve the required velocity and cleanliness. The training outcome emphasizes designing an isolated flush path, verifying chemistry and clarity, and protecting live boundaries to ensure the system remains safe and efficient. On this slide, we're focusing on the water chemistry boundary for phased expansion in a Data Center MVAC system. The key idea here is that the new phase only becomes part of the live system after compatible chemistry and cleanliness are confirmed. This involves monitoring several important parameters. For example, conductivity and treatment concentration matter because they ensure corrosion protection and chemical compatibility, matching the project's treatment window before tying in the new phase. We also look at pH and inhibitors to protect different materials like steel, copper, aluminum, and seals, which requires confirming material-specific limits. Suspended solids and turbidity are monitored to protect sensitive components such as PICV cartridges, strainers, meters, and heat exchangers. This involves temporary filtration and setting acceptance limits, along with regular filter inspections and sampling trends. Microbiology is also critical to manage biofilm, fouling, and corrosion risk through an appropriate biocide and monitoring plan. Lastly, dissolved oxygen and corrosion indicators help us identify oxygen ingress and active corrosion risks. The treatment must be stabilized and oxygen ingress eliminated before the new phase is integrated, with trends, samples, and corrective actions documented thoroughly. Altogether, these controls ensure a smooth and safe expansion of the water system. In this module, we're focusing on how to integrate controls for a new phase using real devices with a bounded rollback approach. The integration process follows a clear, step-by-step sequence to ensure reliability and safety. First, we isolate the devices within a lockable boundary, setting declared acceptance criteria to define success. Next, we perform various tests like flush, pressure, and calibration, again with specific acceptance criteria to meet. Then comes integration, where we scale, ensure quality, and plan for rollback if needed. Following that, we energize the system, matching and starting components, and proving flow to meet our declared standards. Finally, acceptance is granted with terminal authority based on solid evidence. A critical aspect here is advanced acceptance, where we time-align commands with device positions, pump speeds, branch flows, pressures, valve positions, and thermal responses. Remember, any command that doesn't provoke the correct process response is a failed step. The training outcome emphasizes integrating points before granting authority, verifying quality and fail states, enabling control layers one at a time, and proving rollback and recovery capabilities. This staged approach helps maintain system integrity throughout the process. Here we have a critical failure scenario where the selected differential pressure transmitter, or DPT, remains stuck in the old phase even after the system expands. What happens is the pump reset continues to rely on this outdated DPT, causing the new phase to potentially starve of flow while the controller mistakenly reports everything as successful. This highlights the importance of ensuring selector coverage follows the current hydraulic critical path, not an outdated one. The key takeaway is that we must recognize this false success condition and expand validated DPT and valve demand coverage. Then, by testing changes in the critical path and fallback, we can avoid isolated new phases and maintain proper system health and performance. On this slide, we're focusing on a critical failure scenario where the main riser differential pressure control valve, or DPCV, sensing is either reversed or isolated. This mistake can completely disrupt riser pressure control, even if the valve and actuator themselves are functioning perfectly. The key point is that reversed, equalized, or isolated impulse lines essentially destroy the control system's ability to regulate pressure properly. Before making any adjustments to set points, it's crucial to thoroughly verify the tap zones, confirm correct polarity, and check the manifold lineup. This step is essential to accurately diagnose the sensing path failure and restore proper riser pressure control, which helps maintain system stability and efficiency. On this slide, we're addressing a common failure mode involving a floor DPCV installed in series with terminal E-PICV. When these two pressure controllers operate together, they create competing control loops that lead to unstable flow and hidden valve authority. This often manifests as symptoms like valve hunting, unexplained valve saturation, or excessive pump head, which can be quite puzzling. To diagnose the problem, it's important to monitor and trend the controller positions, terminal pressure differentials, remote differentials, and the flow in the branch. The recommended correction is to remove or bypass the floor controller, then recommission the main riser DPCV and electronic PICVs to restore proper pressure zone boundaries. By doing this, you eliminate unnecessary control conflicts and restore system stability. This approach aligns with our training outcome goals: identifying interacting series controllers, verifying terminal minimum differential pressures, removing redundant floor DPCVs, and retesting to confirm hierarchy and stable operation. On this slide, we focus on the factory acceptance test, or FAT, which is critical for verifying both component capability and control integration before the hydraulic system is installed on site. The FAT ensures that everything functions correctly under the required conditions, reducing issues during field installation and startup. Key elements covered in the FAT include the pump and variable speed drive, where we check curve points, speed control, protections, alarms, and communication protocols. We also examine riser differential pressure control valves and terminal PICVs, verifying valve identification, actuator stroke, settings, and leakage. For the control panel, simulations of input-output sequences, sensor failures, and fallback operations are tested to ensure robustness. The CDU's heat duty, flow, redundancy, and leak detection functions are validated with OEM test reports. Instruments undergo rigorous checks for range, calibration, protocol scaling, and certification, with as-left calibration documented to maintain traceability. Any missing data or unresolved interface capabilities are marked as open items, emphasizing the importance of completeness and accuracy in this acceptance process. On this slide, we're focusing on the tab and hydronic verification checklist, which is crucial for ensuring the system operates as designed. Tab, or testing, adjusting, and balancing, verifies the installed flow distribution and pressure control hierarchy rather than just providing a list of design point readings. This approach confirms that the system functions reliably under different conditions. We look at several key activities, starting with the normal state of the system, then assessing a disturbed state, such as when one pump or train is unavailable. We must deliver certified operating points and trends for parameters like pump duty, flow, head, speed, and power consumption at each stage. Critical components include the riser differential pressure control valve, where we verify the set point and protected differential pressure and observe the system stability through changes in neighborhood load phases. Terminal electronic pressure independent control valves are checked for preset flows, stroke operation, and design flow adjustments, ensuring flow independence within allowable tolerances. Also important is the calibration and verification of differential pressure transmitters, focusing on their range, zeroing, scaling, and sensor reliability, with clear evidence of calibration and fallback capabilities. Finally, phase integration activities, such as baseline measurements before tie-in and reports on existing phase preservation, help maintain system integrity as the system evolves. All of these elements work together to provide a clear picture of system performance, stability, and reliability in maintaining the desired hydronic distribution and pressure control. On this slide, we're looking at functional performance tests for the Data Center MVAC system, specifically focusing on pumping and hydronic distribution. These tests are designed to link a specific stimulus with the expected hydraulic response, thermal outcome, and synchronized evidence to validate system performance. For example, during a differential pressure reset, we check that representative valves are properly below or above reset thresholds, and that setpoint trims respond within acceptable bounds. We verify this by monitoring differential pressure transmitters, valve positions, pump speeds, and temperatures. Another key test involves sensor transfer, where we simulate a failure or bias in a critical differential pressure transmitter and expect a seamless fallback or switching to an alternate sensor without disruption. We confirm this by observing quality flags, selected values, and alarms. Additionally, the main riser differential pressure control valve protection test ensures that opening or closing a large terminal or an adjacent riser does not destabilize the protected riser's pressure or flow. Flow independence and stability are also verified by sweeping available branch pressure and monitoring that the preset flow is maintained within specified ranges, using pressure or temperature ports and flow transmitter readings. Throughout all these tests, we continuously check that temperatures and flows remain within the OEM or project envelopes, and the data is tracked through synchronized trending of flow, temperature, and control system parameters to provide comprehensive pass evidence. These detailed tests ensure the system operates reliably and efficiently under various conditions. This slide highlights the integrated systems test focused on a staged expansion event using real equipment. The test ensures a complete live transition through several critical steps. First, we start with isolate, establishing a lockable boundary and meeting specific acceptance criteria. Then, we move to test, where flushing, pressure checks, and calibration are performed to declared standards. Next is integrate, focusing on scaling, quality verification, and the ability to roll back if necessary. Energize follows, where matching, starting, and proving flow are essential, all validated against acceptance criteria. Finally, accept involves terminal authority providing evidence to confirm successful completion. The key takeaway here is that time alignment across commands, device positions, pump speeds, flow rates, pressures, valve positions, and thermal responses is vital. A command that doesn't trigger a process response is considered a failed step. This rigorous approach verifies expansion readiness, integrates systems mechanically and logically in stages, introduces intentional failures, and proves service continuity, rollback capability, and stable recovery. This ensures the MVAC system operates reliably in a demanding data center environment. On this slide, we're focusing on the maintenance of the main riser differential pressure control valve, or DPCV, and terminal pressure independent control valve, the PICV. The key point here is that before returning any valve to service, the assigned hydraulic boundary must be fully reproven to ensure system integrity. Maintenance tasks include isolation and servicing of the valves, followed by recommissioning with required evidence, such as verifying the riser DPCV diaphragm and spring condition, and protecting the capillary and main riser boundary to avoid affecting adjacent risers. We also need to confirm correct valve operation by checking direction, sense lines, settings, and differential pressure response, as well as performing a protected riser disturbance test. For PICVs, it's critical to drain and vent branches properly to prevent debris ingress, confirm preset settings, actuator stroke, and minimum differential pressure, and assess flow across pressure sweep. Additional tasks include actuator replacement, where we record the fail position and control signal, calibrate end stops and feedback scaling, and monitor trends in command, position, and leakage. The strainer must be cleaned carefully to capture debris without bypassing filtration, recording differential pressures before and after cleaning. Finally, sensor and test ports require safe depressurization and capping, followed by comprehensive leak checks, measurement cross-checks, and detailed calibration or service records to complete the maintenance process. This thorough approach ensures optimal performance and reliability of the hydronic distribution system. On this slide, we focus on using a compact set of hydraulic KPIs to monitor the MVAC system effectively. These key performance indicators help us detect control drift before it impacts cooling performance. We start by looking at the critical differential pressure margin, which should remain above minimum with a small controllable reserve. If we see a persistent high margin or valve saturation, that's a sign to investigate sensor bias, reset bounds, or potential new critical paths. Next, we examine the PICV position versus flow. Ideally, flow should follow the command within the differential pressure range. Unexpected position changes without corresponding flow indicate issues such as strainer blockage or actuator problems. Riser DPCV stability is also vital. The protected differential pressure should stay steady during neighbor changes, so any oscillations or drift require checking the sense lines, capillary, and upstream pressure. We also track phase flow preservation, ensuring the existing phase stays near the baseline, while step changes after tie or staging events point to adjustments in tie lineup or pump selector settings. Finally, the wire-to-water KPI verifies that power consumption aligns with required flow and head. If speed or power is high at low load, it may suggest wrong DP transmitter placement, sensor bias, excessive set points, or valve losses. Together, these KPIs give us a clear picture to maintain optimal hydronic system performance and avoid unexpected cooling issues. On this slide, we're focusing on the critical concept of the system readiness gate for multi-story hydronic distribution in a data center MVAC system. The system is considered ready only when design, controls, installation, commissioning, and operations are all aligned on the same hydraulic intent. Starting with the design phase, it's essential to have defined pressure zones and index paths, clearly established main riser differential pressure control valves and terminal PICV ranges, as well as accounting for both current and future phase cases. Then, during installation, proper valve orientation and accessibility, correct sensor tap and impulse routing, and appropriate flushing, venting, draining, and ensuring water quality are paramount. Moving to controls, the system must include a critical point selector, DP reset bounds and fallback strategies, and mechanisms for phase enable and rollback. Proof for commissioning ensures that normal and faulted hydraulic duties are tested, existing phases are preserved, and thermal outcomes are analyzed with synchronized trend data. Finally, a complete handover package is vital. This includes editable PNIDs, detailed settings, calibration records, baseline data, test records, standard operating and emergency operating procedures, and clear rules for integrating future phases. Together, these steps create a comprehensive framework to ensure the system performs reliably and as intended. On this slide, we're focusing on the essential components of the handover evidence package for the data center MVAC system. Operational readiness depends on having a comprehensive and controlled record set that accurately matches the installed configuration. First, the design record includes the fundamental basis and calculations, approved curves and schedules, the power and control architecture, and a resilience matrix to ensure system robustness. Next, the configuration details cover VSD and protection settings, sequences and set points, network and source mapping, as well as valve lineups and labels for clear identification. Moving on to test evidence, it encompasses factory and site acceptance tests, functional and installation tests, instrument calibration, event trends with timestamps, and documentation of defect closure with retesting as needed. Finally, the operations section ensures proper procedures are in place, including standard, maintenance, and emergency operating procedures, alarm response protocols, availability of spares and special tools, and preventive maintenance schedules with baselines to maintain optimal performance. On this slide, we're focusing on key abbreviations and standards critical to understanding pumping and hydronic distribution in data center MVAC systems. First, the abbreviations. DPCV stands for Differential Pressure Control Valve, E-PICV is Electronic PICV, and DPT means DP transmitter. These components play vital roles in controlling and monitoring fluid flow. The standards and readiness criteria listed here are essential for ensuring reliable and efficient system operation. For example, ENSI/TIA 942C deals with uptime tier criteria, making sure capacity and distribution paths are independent as required. Then we have ASHRAE standards focused on energy, controls, and measurement frameworks, which define how efficiency, sequences, sensors, and tests are explicitly determined. We also look at ANSI/HI pump standards that emphasize testing within operating regions, and IEEE 519 alongside NEMA and IEC standards that govern harmonics and motor drive coordination. Each standard ensures that safety, performance, and reliability measures are verified. Lastly, the owner project specification verifies event responses, timing, and thermal acceptance, making sure the entire event can be demonstrated with synchronized evidence, so no required cooling is lost during any declared event. This comprehensive register guarantees a strong foundation for system readiness and fault tolerance. On this slide, we have an important glossary covering abbreviations from A to C that you'll encounter in the context of pumping and hydronic distribution. First, an active harmonic filter, or AHF, is used to reduce drive input harmonics, which helps improve power quality in motor drives. Then, the allowable operating region, or AOR, defines the outer manufacturer-approved pump range, ensuring safe and efficient pump operation. An automatic air vent, abbreviated AV, plays a crucial role by removing collected or entrained air from piping systems to maintain system efficiency. The best efficiency point, or BEP, indicates the pump speed and diameter at which maximum efficiency is achieved. This is a key parameter when selecting and operating pumps. Next, the Building Management System, or BMS, provides supervisory monitoring and control over HVAC and other building systems. The Coolant Distribution Unit, CDU, serves as the interface between the facility and technology for liquid cooling applications. Chilled water, labeled CHW, is the primary hydronic cooling medium circulating through the system, with CHWR referring to the warm chilled water return heading back to the plant, and CHWS denoting the cold chilled water supply from the plant. The Computer Room Air Handler, CRAH, is a critical air cooling terminal specifically for data halls. Commissioning Verification, CV, involves independent field checks to ensure systems are installed and operating correctly. Lastly, the Chiller, or CH, is the mechanical machine responsible for producing chilled water. Remember, these definitions should be used alongside your project specifications and manufacturer documents, as exact terminology can vary. Understanding these terms will help you navigate and implement hydronic systems effectively. Here we have an important glossary of abbreviations ranging from D to H that you'll encounter in pumping and hydronic distribution systems. Starting with DP, which stands for differential pressure. This is essentially the pressure difference between 2 points in the system. Then there's the DPCV, or differential pressure control valve, which acts as a main riser pressure zone regulator to maintain system stability. The DPT, or differential pressure transmitter, measures and transmits that pressure difference to help control system operations. Another key term is the E-PICV, the electronic pressure independent control valve, which manages terminal flow with electronic feedback for precision. EMC stands for electromagnetic compatibility, referring to how well equipment resists interference and controls emissions. The ET, or expansion tank, serves as a system pressure reference and allows for expansion volume to maintain proper pressure. Flow meters and flow transmitters, abbreviated FM and FT, measure volumetric flow within the system to ensure correct operation. The FWU, or fan wall unit, is a high airflow fan array cooling terminal providing efficient air movement. FWS stands for Facility Water System, essentially the facility side of a CDU or heat exchanger. The term H refers to head, which is the fluid energy per unit weight, usually measured in meters. The HQ is the head flow curve, a graph showing pump head plotted against flow, critical for pump selection and system analysis. Finally, HX, or heat exchanger, transfers heat between fluids, playing a crucial role in thermal management. Remember, these definitions support understanding, but always refer to your project specifications and manufacturer documents for exact terminology. Here we have a comprehensive glossary covering important abbreviations from I to M that you're likely to encounter in the context of pumping and hydronic distribution systems. For instance, FOR stands for isolation valve, which is used for maintenance isolation purposes. LD refers to leak detection, involving sensors or controllers that monitor for any liquid release. Flow measurements include L/S, meaning liters per second, and M superscript 3/H, or cubic meters per hour, both key volumetric flow units. Level transmitter, abbreviated as LT, enables continuous level measurement. Valves play a critical role here, with MVV being a manual balancing valve used for fixed balancing or measurement, MCV representing a motorized control valve that modulates or acts as a bypass, and MIV standing for Motorized Isolation Valve, which offers automated positive isolation. The MCC, or Motor Control Center, handles electrical motor feeders and protection. Then, in terms of building systems, MVAC stands for Mechanical Ventilation and Air Conditioning, a core mechanical discipline. Units like kPa or kilopascal measure pressure, while kW or kilowatt measures power, both essential for understanding system specifications. Remember that these definitions provide a foundation, but exact terminology is always governed by project specifications and certified manufacturer documents. Let's go through some key abbreviations relevant to pumping and hydronic distribution systems. First, N+1 refers to having duty capacity plus one standby unit, representing a single unit redundancy criterion to ensure reliability. Next, NPSH stands for net positive suction head, which is the absolute suction energy above vapor pressure, crucial to avoid cavitation. We also have NPSHA, or NPSH available, which represents the site's suction margin, and NPSCHAR, the NPSH required, which is the manufacturer's minimum for proper performance. Moving on, NRV is a non-return valve that prevents reverse flow, an important safety feature. OEM means original equipment manufacturer, the certified source of equipment data. PNID stands for Piping and Instrumentation Diagram, which is the issued schematic used in system design and operation. PICV is a pressure-independent control valve, a flow regulator that works regardless of available differential pressure. PLC, or Programmable Logic Controller, provides deterministic control logic to automate system operation. POR means Preferred Operating Region, indicating a reliable pump range around the best efficiency point. PT stands for Pressure Transmitter, used for continuous pressure measurement. Finally, PUE, or Power Usage Effectiveness, is a critical energy metric for data centers, measuring the efficiency of power use throughout the facility. These definitions provide a solid foundation for understanding the terms you'll encounter in project specifications and manufacturer documents. Here we have an overview of key abbreviations used in pumping and hydronic distribution systems, specifically for terms starting with the letters Q through S. It's important to remember that these definitions serve as a general reference, but the precise terminology for any project should always be confirmed with the project specifications and certified manufacturer documents. Starting with Q or Q, this refers to the flow rate, which means the volumetric flow, and the exact meaning depends on the context in which it's used. Then there's Q, representing the heat transfer rate or thermal duty, usually measured in kilowatts. RDHX stands for Rear Door Heat Exchanger, a rack-mounted liquid-to-air cooling terminal commonly used in data centers. Next, RTD is a resistance temperature detector, a type of precision temperature sensor. SOC indicates the state of charge, which measures the usable fraction of thermal storage. SPD means speed feedback, a signal indicating the pump or variable speed drive operating speed. We also see SPLC, short for StatePoint liquid cooling, which refers to an indirect evaporative or adiabatic production network. STR is a strainer, a debris protection device used in the system. TT means temperature transmitter, combining a temperature sensor with a transmitter for accurate readings. Moving on to control configurations, 1002 is a 1 out of 2 selector arrangement with validated channels, while 2003 is a 2 out of 3 voting or majority voting arrangement used for system reliability. Finally, SI denotes the International System of Units, which is the standard engineering unit convention used throughout these systems. Understanding these abbreviations is crucial for navigating the technical documentation and communication in advanced pumping and hydronic distribution projects. On this final slide, we have an overall abbreviation glossary covering terms from T to Z, along with important symbols used throughout this module. These definitions are meant to be used alongside the page-specific footer line, and it's important to remember that project specifications and certified manufacturer documents ultimately govern the exact terminology. Here we see key abbreviations like TCS, which stands for Technology Cooling System, crucial for the rack or server side of a CDU. TS refers to thermal energy storage, representing a sensible or latent energy buffer. VFD, or variable frequency drive, controls electrical frequency or speed, and VSD, variable speed drive, manages variable speed motor control. We also have VPS, the valve position signal, which gives actuator feedback, and VPF, variable primary flow, related to chiller plants with variable evaporator flow. VS stands for vibration sensor, an input used for condition monitoring. YSTR or Y strainer is an inline debris strainer with blowdown. Symbols include delta T, the temperature difference defined as return temperature minus supply temperature. The symbol eta represents efficiency and is context-dependent, often related to pumps, motors, or drives. The Greek letter rho defines density, meaning fluid mass per unit volume, and finally, CP stands for specific heat capacity, the heat required per mass per Kelvin. Understanding these terms and symbols is essential for clear communication in pumping and hydronic distribution systems.